Michelin plants in the United States appeared in 1975, when the company opened its first facility in Greenville, South Carolina. Since then, Michelin has become one of the leaders in the tire industry in America, establishing 19 modern production sites in 16 cities. Today, they produce tires for cars, trucks, agricultural machinery, and even aircraft, combining French engineering with American scale. Let's go take a look. This started long before American drivers knew how to pronounce Michelin without an accent. Long before the internet, before electric cars, before all these smart tires with chips, when cars still hummed and smoked with real gasoline, and a road trip felt like a journey, not a commute to the office. The French brand Michelin, with its smiling rubber man, known here as Bib the Michelin Man, had been dreaming of America since the early 20th century. But this dream took a long time to ripen. Everything changed in 1973 when the oil shock shook the United States. Drivers started looking for savings, automakers for efficiency, and in this new game, a high-quality radial tire from Europe suddenly became not just a novelty, but a real breakthrough. Michelin, which had invented radial technology back in 1946, understood. The moment had arrived. Greenville, South Carolina. It was here, among the hills, pine forests, and reddish clay soil, that the first Michelin plant in the US opened in 1975. Not in Detroit, not in Los Angeles, but in Greenville, a quiet city with plenty of land, little noise, and enough working hands. It was a relocation of engineering culture across the ocean. French specialists worked alongside American technicians. Documents were translated from the metric system to inches, gallons, and pounds. And yet, day by day, machine by machine, shop by shop, the plant came to life. Back then, they produced radial tires for passenger cars, and it seemed like some kind of magic. American brands were still mass-producing diagonal models, which were loud, stiff, durable, but not long-lasting. Michelin showed something different. Tires that worked softly, quietly, and for a long time. They seemed to listen to the road. 1977, a second plant. 1981, another one. Then logistics centers, testing grounds, scientific laboratories. Everything was gradual, calm, without advertising. Michelin wasn't clamoring for the front pages. It was just doing its job. Under the wheels of American cars, past farms, cities, canyons, what was rolling was no longer just tires, but a philosophy of the tire, made with understanding and love for the road. Today, that first plant in Greenville is not just operational. It has become a training hub, an R&D center, the heart of Michelin's entire presence in the US, and the company itself is one of the largest employers in South Carolina. And if you stop somewhere on an interstate in Tennessee or Texas, get out of your car and look at the tread. It's quite likely that it was born right there, in the quiet workshops of Greenville, where rubber smells of warmth and the past. To manufacture tires today, it all begins far across the ocean, in places where the air is dense, humid, and smells of earth, trees, and latex. Natural rubber, one of the main components of tires, grows in the bark of Hevea brasiliensis, mostly in Southeast Asia, Thailand, Indonesia, Malaysia. Michelin has long-term contracts with these countries, as well as its own plantations in Brazil and Africa. On the plantations, a milky liquid, latex, is collected from the trees. It is poured into barrels, thickened, dried, and pressed into blocks of raw rubber weighing 77 pounds each. Then they are packaged, labeled, and prepared for their journey. These blocks don't fly on airplanes. They sail on container ships across the Pacific Ocean, through the Panama Canal or the Atlantic. Michelin has its own logistics chains, with transshipment points, warehouses, and quality control systems right at the ports. One of the main American ports for rubber delivery is Charleston, South Carolina. Upon arrival, the rubber blocks are loaded onto trucks or railway platforms. They go directly to the plants, including to Greenville, Anderson, and Lexington, where large Michelin USA centers are located. In parallel with natural rubber, synthetic rubber is supplied to the plants. It is produced in the US, in Texas, Louisiana, and Ohio. This is a petrochemical product, stable, predictable, with precise properties. And so, when both components, natural and synthetic rubber, are in the workshop, they are inspected. Density, elasticity, moisture content, color, even smell. Because each type of tire requires its own unique composition. This is how the journey of rubber begins, before it becomes part of that very tire that speeds between Charlotte and Miami. When the blocks of rubber, natural from the tropics and synthetic from US chemical plants, arrive at the Michelin factory, they are still wild. They need to be tamed, combined, and endowed with strength, flexibility, and resistance to heat, rain, cold, and time. For this, there is the alchemy of mixing, the heart of tire production. At the factory, it's simply called rubber mixing, but in essence, it's an industrial kitchen where, instead of spoons, there are steel mills, and instead of ovens, giant drums with spiral-shaped shafts. First of all, an operator, usually an experienced specialist, loads precisely weighed ingredients into the mixer. Blocks of rubber, typically 70 to 150 pounds per batch, as well as carbon black, which gives the mixture strength and a rich black color. Silica is added to it. It improves the tire's grip on wet roads. Oils and resins are essential, responsible for elasticity and flexibility, as well as sulfur. It will become a key element of the future vulcanization. All this together creates a recipe, precise to the gram, which depends on the type of tire. Passenger, sports, truck, or even aviation. Each requires its own special composition. Sometimes a mixture can contain up to 200 components, each with a clear function, each tested by time and the laboratory. A Banbury mixer, which is a giant steel cauldron with rotating blades. The mixture in it is heated to 350 degrees Fahrenheit. The blades rotate with incredible force, 40 revolutions per second, tearing and kneading the rubber, mixing it with fillers. Inside, a dull roar is heard, a creak and a smell of hot, living rubber. The mixture becomes black, sticky, dense, thick like molten chocolate. The smell, however, is not at all like chocolate. When the mixing is complete, the hot mass is discharged in the form of thick black sheets, which are rolled through steel rollers, resulting in rubber sheets up to 0.5 inches thick. These sheets are then cooled, labeled, each type having its own code, and sent to the area for forming the tread, sidewalls, and inner layers of the tire. After mixing, the rubber is still just black sheets, each with a future, but not yet a form. To become a tire, it needs to be assembled, layer by hand and machine at the same time. This process is called tire building and takes place on a special building drum which rotates like a potter's wheel, only under computer control. The inner liner is an airtight, very thin layer that holds air inside the tire. It is unrolled first, as a base on which the rest will be laid. Without it, the tire would simply breathe and lose pressure. In modern radial tires, this layer is made of synthetic rubber that doesn't let air escape even under a pressure of 50 psi. Next, the carcass. Textile or polyester cords are laid on the inner liner, thin but extremely strong threads that run diagonally. They create a frame that holds the tire's shape during rotation. Then, steel reinforcing belts are applied, thick steel wires woven at an angle. They give the tire rigidity, stability at speed, and resistance to punctures. Thicker layers of rubber on the sides are responsible for flexibility and protection. At the bottom of the tire, beads are formed, with built-in steel rings. These are the beads that will later sit tightly on the wheel rim. They must withstand the weight of the car, from 2,000 to 7,000 pounds, and not slip off even during a sharp turn. Finally, the tread layer is applied on top, a thick strip of rubber compound with a deep pattern. It's not carved out immediately. The pattern will appear later, during vulcanization. The tread is the tire's contact with the road, and almost everything depends on it. Grip, braking, wear, noise. Next comes vulcanization and tread stamping, and that's it. The tire is ready to become part of your car. Every hour, Over 1 billion square feet of glass are produced worldwide. But only one of them has clothed a giant that pierced the sky. Imagine a building taller than 3 Eiffel Towers, covered in glass with an area equal to 5 football fields. This is the Burj Khalifa, a symbol of human ambition. But what if I told you that it all started with sand, and a secret recipe that is still kept under wraps? Watch until the end, because something will be revealed that you've never heard of before. A property that turns glass into a source of life in the very heart of the desert. Imagine this. Dubai, a city that grew out of the desert, decides to surprise the world. Sheikh Mohammed bin Rashid Al Maktoum, the ruler of Dubai, sought to transform his country into a global tourist destination and reduce its dependence on oil revenues. And so, among ambitious projects, the idea of building a tower taller than anything humanity had ever seen was born. Construction began in 2004, and on January 4th, 2010, the world held its breath as the Burj Khalifa, originally named Burj Dubai, officially opened its doors. The height? A staggering 2,717 feet. That's almost 3 Eiffel Towers stacked on top of each other. 163 floors piercing the sky. The cost of this giant, about $1.5 billion. And now let's get to the main point. It's glass attire. How do you dress such a colossal structure? After all, the exterior surface of the Burj Khalifa is covered with glass and metal, and the area of this glazing is, imagine this, equal to the area of 5 football fields, or, to be more precise, about 1,528,000 square feet. That's an incredible number, and each panel had to be not just beautiful, but also functional. Have you ever wondered what it's like to live and work behind glass in a place where the air temperature can reach 122 degrees Fahrenheit? It's a real challenge. Therefore, the architects and engineers from the American company Skidmore, Owings and Merrill faced an incredibly difficult task. They had to create glass panels that would protect from the scorching sun and unbearable heat, yet allow enough light to pass through, and offer incredible views of the Persian Gulf. This is a true engineering feat. So, how did they do it? Each glass panel of the Burj Khalifa is a complex multi-layered sandwich. The outer layer is glass coated with a thin layer of metal. This coating reflects the sun's rays, preventing them from heating the interior. The next layer is an air gap, which serves as additional thermal insulation. And finally, the inner layer is strong laminated glass for safety. Imagine how well thought out every detail had to be. The production process of these panels is a story in itself. The glass for the tower was manufactured at specialized factories, particularly in Syria. Each panel underwent strict quality control. It was tested for strength, resistance to temperature fluctuations, and wind loads. And the winds up there, at that height, can be quite strong. Engineers developed a special window frame design capable of withstanding the extreme weather conditions of the desert. So, how does the creation of one of the more than 26,000 glass panels for the Burj Khalifa begin? It all starts with fire and sand. At the core of everything is ordinary quartz sand of the highest quality, soda ash, and limestone. But don't think it's that simple. The proportions of these components are a trade secret, the first step towards creating super strong and functional glass. This mixture is loaded into a giant melting furnace, the size of a small house. The temperature inside? Over 2,700 degrees Fahrenheit. It's a real inferno, where the loose mixture turns into a red-hot, viscous, dazzlingly orange lava. And then, one of the most spectacular stages begins. The float glass process. The molten glass mass is continuously poured from the furnace onto a perfectly flat surface of molten tin. Yes, you heard that right. A huge bath filled with liquid, silvery metal. The glass, being lighter than tin, spreads over its surface like oil on water, forming a perfectly smooth, impeccably flat sheet of a given thickness. No distortions, no defects. It's like a fiery river, slowly flowing and solidifying. Then this endless glass ribbon enters a long tunnel for controlled cooling, or annealing. This is a critically important stage. If the glass cools too quickly, internal stress will simply shatter it into pieces. Therefore, over a few hundred feet, the temperature gradually and very slowly decreases. This relieves the stress and makes the glass stable. Now we have a giant sheet of transparent glass. But for the Burj Khalifa, this is not enough. It's time to give it superpowers. The panels are sent to vacuum chambers for the application of a special coating. This is the heart of the technology. In an almost complete vacuum, using a process called magnetron sputtering, the thinnest layers of metals, most often silver, are applied to the surface of the glass. Layer by layer, atom by atom. The thickness of these layers is measured in nanometers. It's thousands of times thinner than a human hair. It is this coating, invisible to the eye, that will reflect solar radiation and ultraviolet rays, protecting the tower's interior from the desert heat. Incredible, isn't it? But the glass must also be safe. Therefore, it undergoes a tempering process. The glass sheets are heated again to a temperature of about 1,150 degrees Fahrenheit, almost to the softening point, and then sharply cooled with powerful streams of cold air. This thermal shock creates incredible internal stress. The surface is compressed, while the inner layers remain in a state of tension. As a result, the glass becomes 5 times stronger than ordinary glass. If such a panel does break, it will shatter into thousands of small, safe crumbs without sharp edges. And that's not all. Remember the sandwich? Now it's time to assemble it. They take 2 sheets of glass, one tempered with a solar control coating. Every year, over 150 million cubic meters of plywood are produced worldwide, a volume that could circle the Earth several times in train cars. But few people stop to think that behind this lies a unique technology where wood is literally unrolled into a continuous ribbon and then assembled into a super strong material that can withstand colossal loads. How do ordinary logs, after spa treatments in giant pools and a dance with knives, turn into perfectly smooth sheets, ready to serve in furniture, ships, and even skyscrapers? Watch until the end, and you'll discover one hidden secret of this production that isn't talked about publicly. It all starts in the forest, where the best specimens are selected for plywood production. You need perfectly straight, cylindrical trunks without a large number of knots or defects, preferably from birch, alder, pine, or other species. After being delivered to the factory, the logs go through the first and very important stage of preparation hydrothermal treatment. They are submerged in giant pools of hot water, where they spend several hours, and sometimes up to a day. This sort of spa for logs has a purely practical purpose. The hot water softens the wood, making it more plastic and pliable. Without this, further processing would be impossible, as cold wood would simply crumble and break. After their bath, the logs are fed to a line where their bark is stripped off. Special machines quickly and efficiently clean the trunk, leaving a smooth, light surface. Then the logs are sawn into standard lengths, ready for the main stage of transformation. The heart of the entire plywood production process is the peeling lathe. This is where something incredible happens, something that contradicts our usual understanding of wood processing. The prepared log, clamped at both ends, begins to rotate at a huge speed around its axis. A long, razor-sharp knife, installed parallel to the axis of rotation, is slowly brought towards it. As it cuts into the wood, it begins to peel off not shavings, but a continuous, seamless ribbon, just 1 or 2 millimeters thick. It's like unrolling a giant roll of paper towels. The machine literally unrolls the trunk, like a scroll of ancient papyrus, turning a three-dimensional cylinder into a flat, long ribbon. This ribbon is called veneer. The long sheet of veneer moves further down the conveyor, where giant clippers chop it into sheets of standard size. All that's left of the log is a thin central cylinder, the so-called pencil, which is then used for other purposes. Freshly made veneer contains a lot of moisture, which is an enemy of the strength and stability of the future plywood. Therefore, the next mandatory stage is drying. The veneer sheets are fed into long, multi-tiered drying chambers. Inside them, as if on the shelves of a giant cabinet, the sheets slowly move on a conveyor, while hot air intensely blows on them from all sides. The temperature and speed of the air are strictly controlled to dry the veneer evenly and avoid cracking or warping. In a few minutes, the damp and flexible sheets turn into light, slightly brittle, and perfectly dry blanks, ready for gluing. At this stage, the dried veneer sheets are sorted by quality. Then they pass through a glue spreading machine. Special rollers, dipped in a bath of synthetic glue, usually based on phenol formaldehyde or urea resins, apply a uniform, sticky film to one side of every other sheet. Next begins the process of forming the layup. A dry sheet of veneer is placed on a table. On top of it, a sheet coated with glue is placed. And here lies the main secret. Each subsequent sheet of veneer is laid so that the direction of its grain is perpendicular to the previous one. If the first sheet's grain runs lengthwise, then the second's runs crosswise, the third's lengthwise again, and so on. This cross-grain structure is the key to plywood's strength. It paralyzes the wood's natural tendency to split along the grain and evenly distributes the load over the entire area of the sheet. That's why plywood is equally strong in all directions. The number of layers in the layup is always odd, so that the structure is symmetrical, and the outer layers have the same grain direction. The formed layups of veneer are fed to the most powerful section of production, the hot press. This is a giant multi-level structure, between whose plates several dozen future plywood sheets are loaded simultaneously. When the press is loaded, the plates begin to close. With an enormous force, reaching tens of kilograms per square centimeter, the plates compress the veneer layups, turning them into dense, thin blocks. At the same time, the plates are heated to a temperature of 302 degrees Fahrenheit. Under the influence of high pressure and temperature, the glue polymerizes, penetrating into the pores of the wood and permanently bonding the layers into a single, incredibly strong monolith. The pressing process lasts for several minutes, after which a finished plywood board is born. Hot sheets of plywood come out from under the press and are stacked for gradual cooling. This is important to avoid internal stresses in the material. After cooling, the sheets undergo final processing. Powerful circular saws trim the edges, giving the sheets precise geometric dimensions. Then comes sanding. The sheets pass through sanding machines with endless abrasive belts, which make their surface perfectly smooth and even. After this, each sheet undergoes strict quality control. Inspectors check it for defects, delaminations, knots, cracks, glue spots. Depending on the surface quality, the plywood is assigned a certain grade, and a corresponding marking is applied to it. The finished, sorted, and packaged stacks of plywood are sent to the warehouse, to later become part of furniture, houses, ships, and countless other structures, demonstrating to the whole world how human intellect can improve upon nature itself. The global scale of production is also impressive. Annually, over 150 million cubic meters of plywood are produced worldwide. If you were to load all of this quantity into railway cars, the resulting train would circle our planet at the equator several times. The pencil that remains after peeling the veneer is a vivid example of how modern production strives for maximum waste-free efficiency. It is not waste, but a valuable raw material for which there are several clearly defined paths. Its future fate depends on the thickness and quality of the wood. If the cylinder is massive enough, it is sent to a sawing line, where it gets a second life in the form of lumber. Small boards and bars are cut from it, which are ideal for creating the invisible but strong frames for sofas and armchairs, legs for chairs, elements of children's beds, or wooden pallets. Every year, thousands of tons of fiberglass rebar are produced worldwide, a material that's throwing down the gauntlet to steel. Imagine hundreds of spools of fiberglass, thinner than a human hair, merging into a single river, passing through sticky resin baths, red-hot dyes, and scorching ovens to be born as a rod that's 4 times lighter than steel, twice as strong, and completely immune to rust. This rebar is capable of doubling the lifespan of concrete structures and changing cities forever. But the most interesting part is hidden in the very heart of this process. If you watch until the end, you'll discover a secret that will completely change your understanding of the future of construction. It all begins at one end of a massive workshop, where a structure resembling a giant library for threads stands. This is called a creel. On a wall several yards high, hundreds, and sometimes even thousands, of huge bobbins are installed in neat rows. On each of them is wound the finest glass thread, or roving. This isn't the kind of glass that windows are made of. This is a special fiberglass, produced by melting glass and drawing it through microscopic holes. The result is threads thinner than a human hair, but with incredible tensile strength. These will be our skeleton, our internal army that will give the rod its insane strength. From each of these hundreds of spools, its own separate thread is drawn, and they all come together into one thick, fluffy strand. It's like thousands of small streams merging into one large river. This dry, white strand is the soul of the future rebar. Next, this river of fiberglass begins its journey. It passes through a system of guides and tensioning devices. This is a very important, though inconspicuous, stage. Every one of the thousands of threads must be tensioned with the same force. If one thread sags, while another is too tight, the load in the final product will be distributed unevenly, and it will lose its strength. Therefore, the machine carefully aligns them, preparing them for the most important moment: a baptism in resin. The dry glass strand is slowly submerged into a bath filled with a thick, sticky liquid, similar to honey or syrup. This is a polymer resin, our meat that will grow on the glass skeleton. It's a complex chemical cocktail. The base is usually a polyester, vinyl ester, or epoxy resin. A hardener is added to it, a catalyst that will trigger a chemical reaction and force the liquid to turn into a solid plastic. Various additives can also be added here. Pigments to add color, ultraviolet inhibitors so the rebar isn't afraid of sunlight, and flame retardants for fire resistance. The task of this bath is to saturate every single, even the tiniest fiber. The strand must be completely submerged in this resin so that no dry spots remain. The saturated strand, heavy with sticky resin, exits the bath and heads to its point of birth, the forming die. This is the heart of the whole process. Imagine a thick steel plate with a perfectly round polished hole, the diameter of which exactly matches the diameter of the future rod. The die is heated to a certain temperature. When the wet strand is pulled into this hole, several things happen at once. First, the die, like a press, squeezes out all the excess resin, leaving only the necessary amount. Second, it tightly compresses all the fiberglass strands together, forming a perfectly round rod. Third, the heat from the die initiates the initial stage of the chemical hardening reaction, or polymerization. The resin begins to transform from a liquid into a gel. At the exit of the die, we can already see the familiar shape of the rod, but it is still soft and vulnerable. But how does it get its famous ribbed surface to hold well in concrete? Immediately after exiting the die, while the rod is still hot and soft, a special strand of the same fiberglass is wound around it. A thin, resin-saturated thread is wound in a spiral on the surface of the rod, creating a relief pattern. Sometimes, for even better adhesion, fine quartz sand is sprinkled onto the sticky surface, which adheres permanently to the resin. Now, our rebar has not only strength, but also teeth with which it will hold onto the concrete. The formed and wrapped rod enters the longest part of the machine, the curing tunnel or polymerization oven. This is a long chamber that can extend for tens of feet, inside which a high temperature is maintained, usually 400 degrees Fahrenheit. Here, the final transformation takes place. This is not just drying. Under the influence of heat, the resin molecules begin to actively bond with each other, forming a strong, rigid three-dimensional network. The liquid, sticky syrup turns into an extremely strong and hard composite material that permanently binds millions of glass fibers into a single monolith. It's like baking a pie. As the rod slowly moves through this hot tunnel, it acquires its final, rock-solid hardness. But what pulls it through this entire long journey, from the spools to the oven? At the end of the line stands a special pulling device, which gives the whole process its name. Usually, it's two caterpillar-like mechanisms, similar to tank tracks, located one above the other. They gently but very firmly clamp the already finished hard rod with their rubber pads and pull it towards themselves at a constant, precisely calibrated speed. It is they that create the force that pulls the fiberglass through the resin bath, through the forming die, and through the oven. The speed of this movement is one of the most important parameters that controls the quality of the final product. And so, from the other end of this long conveyor, an endless, perfectly straight, hard and hot fiberglass rod emerges. The final cord is cutting. An automatic saw is installed across the line. It synchronizes with the speed of the rod's movement, at the right moment makes a quick forward motion, and with a sharp zzzt, cuts a piece of standard length, for example 20 or 40 feet, from the endless ribbon. Then it returns to its starting position, waiting for the next section to arrive. The finished, still warm rods roll onto a cooling table, and then they are collected into bundles, tied, and sent to the warehouse. And just like that, before our eyes, thousands of fragile glass threads and a barrel of sticky liquid, having passed through baths, presses, and ovens, have turned into a lightweight, but incredibly strong building material of the future, ready to challenge rust and time in the concrete jungle. The fiberglass rebar market is not yet a giant like the steel market, but it's the coolest and most audacious newcomer at the party, rapidly gaining popularity. The global market for this material is already valued at hundreds of millions of dollars, and the forecasts are just insane. It's expected to grow by 10 or 12% annually. This means that more and more engineers and architects are looking at rusting steel and saying, "Dude, we can do better." And now for the main features that make steel rebar nervously smoke in the corner. The first and most obvious is weight. Fiberglass rebar is about 4 times lighter than steel of the same diameter. Sound boring? Now imagine this in real life. Imagine a truck carrying rebar to a construction site. It can bring 4 times more length of fiberglass rebar in one trip than steel, because it's limited by weight. Or for the same amount, it will take 4 times fewer trips, which saves fuel and time. On the site itself, 2 workers can easily carry whole coils or bundles of fiberglass rods, whereas moving steel requires a crane. This is a colossal saving in logistics and labor. Second is strength. And here, fiberglass just steps into the ring and knocks out steel in the first round. Its tensile strength is about twice as high as that of standard steel rebar. So you understand, to break a fiberglass rod, you need to apply twice as much effort as for a steel one of the same diameter. This means that in some structures, rebar of a smaller diameter can be used, saving even more weight and volume. It's like comparing a regular rope with a climbing rope. At a smaller thickness, it can withstand much greater loads. But the main trump card, the real superpower of fiberglass, is its war against rust. The main enemy of any reinforced concrete structure, from bridges to parking garages, is not the load. It's rust. Water and salts penetrate through micro cracks in the concrete, reach the steel rebar, and it begins to rust. The rust expands in volume and literally tears the concrete apart from the inside. Annually, the US spends billions of dollars on repairing bridges, parking garages, embankments, and tunnels destroyed by rebar corrosion. And fiberglass? It just laughs in the face of rust. It is chemically inert. It is completely indifferent to water, salt, acids, and alkalis. This means that the service life of the structure increases dramatically. A concrete structure reinforced with steel is designed for more than 50 years. And a structure with fiberglass rebar is easily designed for more than 100 years.
Every second, jet engines spinning at 12,000 revolutions per minute thrust hundreds of passengers across continents. But here's what defies physics. Inside those engines, turbine blades made of nickel alloy operate at 3,000 degrees Fahrenheit, temperatures exceeding their own melting point by 200 degrees. Picture holding ice cubes in boiling water without them melting. That's the metallurgical miracle happening 35,000 feet above your head. How does metal survive temperatures that should liquefy it? How do engineers grow crystals larger than your hand from molten metal? Stick around till the end, you'll discover the jaw-dropping secret of single crystal manufacturing that eliminated metal's greatest weakness, and why a single turbine blade costs more than your car, yet lasts 20 years in literal hell. The story begins in specialized foundries where clean room standards rival semiconductor fabs. These facilities maintain air purity of less than 100 particles per cubic foot, 10,000 times cleaner than normal atmosphere. Even microscopic dust particles cause catastrophic flaws in turbine blades spinning at speeds where centrifugal forces generate stresses exceeding 70,000 pounds per square inch. That's pressure crushing steel like aluminum foil. Workers suit up in full-body cleanroom gear before entering casting halls. Inside, massive vacuum furnaces standing 2 stories tall and weighing 80 tons create environments replicating outer space. Vacuum pumps evacuate air until pressure drops to 1/1,000,000th of atmospheric pressure. At these conditions, materials behave differently. Impurities vaporize instantly. Gases trapped in metal escape, leaving behind purity impossible at normal pressure. Processing single batches costs $50,000 in electricity alone. Next comes mold preparation, where ceramic shells, think pottery on steroids, get built layer by microscopic layer. Technicians dip wax patterns shaped like turbine blades into ceramic slurry 10 times, waiting hours between coats. Each layer adds thickness thinner than human hair. After 20 days of coating and drying, workers melt wax away in autoclaves, leaving hollow ceramic molds with internal channels more complex than human circulatory systems. These molds contain passages narrower than spaghetti strands, designed to cool blades from inside during operation. Some channels measure just 0.08 of an inch across, thinner than credit cards. Manufacturing these passages requires such precision that lasers verify every dimension. One blocked cooling hole means blade failure at 300 degrees lower temperature. That's difference between safe flight and catastrophic engine disintegration at cruise altitude, scattering turbine fragments through fuselage like shrapnel.
Giant crucibles containing nickel-based superalloy. Mixtures of nickel, chromium, cobalt, aluminum, titanium, plus 6 other elements in exact proportions. Heat to 2,700 degrees Fahrenheit. Picture liquid metal glowing white like miniature stars captured in ceramic containers. This superalloy, developed through decades of research, contains more expensive elements per pound than fine jewelry. A single turbine blade uses materials costing $800 before any manufacturing begins. Robotic arms lower ceramic molds into this molten inferno with precision measured in thousandths of inches. Timing matters critically here. Pour too fast, turbulence creates defects. Too slow, metal solidifies prematurely. Furnaces tilt at exactly 2 degrees per second, filling mold cavities in 17 seconds. During this pour, metal temperature drops 300 degrees, requiring computer-controlled heating to maintain consistency. One temperature fluctuation of 5 degrees ruins the casting, wasting months of preparation.
Now comes the magic, directional solidification. The filled mold sits atop a water-cooled chill plate at 70 degrees Fahrenheit while surrounded by heating elements maintaining 2,400 degrees above. This creates the steepest temperature gradient in metallurgy, over 2,000 degrees difference across 6 inches. That's transitioning from Arctic to volcanic conditions in the space between your thumb and pinky. Slowly, incredibly slowly, a computer-controlled mechanism lowers the mold through the furnace at speeds of 6 inches per hour. Picture watching paint dry, then slowing that down tenfold. As the mold descends, metal solidifies from bottom upward in a razor-thin freezing front. This directional cooling forces crystal growth in one direction only, upward, eliminating horizontal grain boundaries where cracks normally form. The process takes 14 hours for a 4-inch blade. Rush it by even 10% and polycrystalline grains form, destroying blade strength. But here's where physics becomes art. At the mold bottom sits a grain selector, a corkscrew-shaped passage so narrow only one crystal nucleus fits through. As metal solidifies upward, countless tiny crystals form at the chill plate. They compete, growing upward like metallic trees racing toward sunlight. Most hit the spiral walls and stop. Only the perfectly aligned crystal, the one matching the spiral's orientation, passes through this metallurgical gauntlet. This step is critical because it ensures the entire blade, every atom from root to tip, belongs to one continuous crystal lattice. No grain boundaries exist anywhere. Normal metals contain millions of grain boundaries per cubic inch. Single crystal blades contain 0. Without boundaries, there are no weak spots where atoms slip past each other under stress. The crystal structure extends uninterrupted through the entire blade like a 3-dimensional molecular Kevlar vest, with atoms locked in perfect geometric formation. After solidification, blades undergo solution heat treatment at 2,200 degrees Fahrenheit for 2 hours, then quench in inert gas. This locks crystal structure permanently and precipitates microscopic strengthening phases throughout the lattice. Next comes aging heat treatment, multiple cycles at precisely controlled temperatures that cause nanoscale particles to form. These particles, called gamma-prime precipitates, occupy 70% of the alloy's volume. Picture this. Imagine a 3-dimensional checkerboard where hard particles pin the crystal lattice, preventing atoms from sliding. These precipitates remain stable at temperatures where other metals liquefy. They're the secret allowing nickel alloys to maintain strength at 3,000 degrees, temperatures where aluminum vaporizes, titanium melts, and even steel becomes taffy. The heat treatment process takes 96 hours of precise temperature control. Deviate by 15 degrees at any point and mechanical properties drop 40%. Coating application transforms already sophisticated blades into thermal protection systems. First, a metallic bond coat, aluminum-rich alloy, gets applied via high-velocity plasma spray at 20,000 degrees Fahrenheit. Metal particles accelerate to twice the speed of sound, impacting the blade surface with such force they cold weld instantly. This creates a rough surface for subsequent layers while providing oxidation resistance. Then comes the thermal barrier coating, yttria-stabilized zirconia ceramic applied atom layer by atom layer using electron beam physical vapor deposition. In vacuum chambers, electron beams vaporize ceramic ingots. The vapor condenses on rotating blades, building up a coating 0.08 of an inch thick with a columnar microstructure full of microscopic pores. These pores act like thermal insulation, trapping air pockets that reduce heat transfer. The ceramic coating lowers blade temperature by 400 degrees, the difference between survival and meltdown. Modern engines couldn't exist without this coating technology. This wasn't always possible. Back in 1940, early jet engines used cast iron turbine blades lasting 20 hours before failure. Temperatures barely reached 1,400 degrees Fahrenheit. The breakthrough came when Pratt & Whitney researcher Frederick Vierling invented directional solidification in 1966, eliminating transverse grain boundaries and doubling blade life overnight. The true revolution arrived in 1982 when General Electric and Pratt & Whitney independently perfected single crystal casting. Turbine inlet temperatures jumped from 2,000 degrees to 3,000 degrees Fahrenheit, a 50% increase enabling massive efficiency gains. Modern turbofan engines achieve fuel efficiency triple that of 1960s designs. Today, advanced engines like the GE9X powering Boeing 777X aircraft operate at 3,200 degrees, with pressure ratios reaching 60:1. These engineering advances cut aviation fuel consumption by 65% per passenger mile over 50 years. Carbon emissions dropped by 12% when replacing older turbine blades with modern single-crystal versions in existing engines, equivalent to removing 18 million cars annually from global fleets. Airlines save over $47 billion yearly through improved fuel efficiency. Maintenance costs drop 58% because single-crystal blades last 3 times longer than conventional ones. So here's the secret promised. These blades don't actually survive above their melting point through material strength alone. They're actively cooled by air bled from the compressor, flowing through those microscopic internal channels at supersonic speeds. This cooling air, already compressed to 400 degrees Fahrenheit, seems hot by human standards but runs ice cold compared to the 3,000-degree combustion gases outside. Combined with ceramic coatings reflecting heat like mirrors, the actual metal temperature stays below 2,000 degrees, hot enough to glow orange but survivable. From molten metal to flying miracles, cycle completes. Single crystal turbine blades represent humanity's most sophisticated metal casting achievement. Objects where every atom's position matters, where crystal orientation determines survival, where manufacturing tolerances make computer chips look crude. We've engineered metal to survive in conditions nature never intended, creating materials that work at their physical limits. That's not just manufacturing, that's molecular architecture enabling the modern world's ability to shrink distance itself. Every day, somewhere in China, a machine generates force equivalent to stacking 200 fully loaded aircraft carriers vertically. This hydraulic press, rated at 80,000 tons, stands 10 stories tall and weighs more than the Eiffel Tower. Picture this. Under its ram, 300-ton steel billets, weight of 60 elephants, flatten like modeling clay in seconds. The ground shakes for miles when it operates. Windows rattle in villages 8 miles distant. How does humanity create machines powerful enough to reshape mountains of metal? Why did Cold War superpowers race to build ever larger presses? Stick around till the end. You'll discover the jaw-dropping reason these monster machines dominate aerospace and defense, the shocking physics of what happens when 80,000 tons compress glowing steel, and why welding became obsolete for the world's most critical components. The story begins at China Erzong Group in Deyang, Sichuan Province, home to the world's most powerful forging press. This colossal machine, commissioned in 2013, towers 120 feet tall. Picture a 12-story building dedicated to squashing metal. The press frame alone weighs 22,000 tons, constructed from steel beams thicker than telephone poles, bolted together with fasteners weighing 500 pounds each. The facility consumes electricity equivalent to 40,000 homes during operation. 8 separate hydraulic power units, each the size of shipping containers, pump oil through pipes 16 inches in diameter. These hydraulic systems generate pressures reaching 10,000 psi, enough to blast water through concrete like tissue paper. When all systems activate simultaneously, the combined oil flow measures 3,000 gallons per minute. That's emptying a backyard swimming pool every 10 minutes continuously through hydraulic cylinders generating incomprehensible force. Next comes the press bed, a foundation descending 60 feet below ground level, deeper than 6-story buildings are tall. This isn't merely concrete, it's a geological anchor. Engineers excavated solid bedrock, then poured 8,000 cubic yards of reinforced concrete mixed with steel rebar, forming 3-dimensional cages. The foundation weighs 45,000 tons, more than 4 nuclear submarines combined. Why such extreme engineering? Because when 80,000 tons of force compress metal, Newton's third law demands equal reaction force pushing downward. Without this massive foundation, the press would crack bedrock and sink into earth like a nail hammered into butter. Seismographs detect vibrations from press operations 12 miles away, not from noise, but from actual ground displacement. The Chinese government prohibited residential construction within 2-mile radius specifically because repeated press cycles could damage building foundations through accumulated seismic stress over years. Giant overhead cranes, rated at 600 tons capacity and spanning widths exceeding football field lengths, position workpieces beneath the ram. These cranes represent engineering marvels themselves, structures where every rivet matters because failure means dropping cargo worth millions. Control rooms, protected by 18-inch thick reinforced concrete walls and bulletproof glass windows, house operators controlling machinery from safe distances. The press ram, the actual crushing surface, measures 40 feet by 30 feet, larger than most studio apartments. Made from tool steel hardened to withstand pressures that would pulverize normal steel, this ram surface gets replaced every 18 months despite costing $2 million. Replacing it requires 3 weeks of round-the-clock work using specialized welding techniques and stress relief treatments. Even with hardened steel, repeated impacts against 300-ton billets create microscopic cracks propagating until failure becomes inevitable. Now comes forging, industrial violence at physics-defying scales. Workers heat steel billets to 2,400 degrees Fahrenheit in furnaces consuming natural gas at rates measured in tons per hour. At these temperatures, steel glows brilliant orange and becomes plastic, deformable under pressure but not liquid. Picture clay that weighs more than locomotives and requires forces exceeding aircraft carrier displacement to reshape. Overhead cranes lower glowing billets onto the press bed with precision measured in inches, despite handling weights where inches of error cause catastrophic collisions. The ram descends at speeds reaching 20 inches per minute. Sounds slow until you realize 80,000 tons moving at any speed generates momentum requiring precise hydraulic control. One malfunction, one stuck valve, one pressure spike, and the ram becomes an uncontrollable projectile carrying enough energy to demolish the entire facility. The compression itself defies description. As the ram contacts glowing steel, metal begins flowing, literally flowing despite being solid. Under 80,000 tons of pressure, crystal structures collapse and reorganize. Grains elongate perpendicular to compression direction, creating oriented microstructures impossible to achieve through casting. The billet spreads outward, metal squeezing into die cavities with force sufficient to emboss details smaller than human hair thickness. This step is critical because forging aligns crystal boundaries, eliminates porosity, and creates grain flow patterns following component geometry. Cast parts contain random crystal orientations and microscopic voids. Forged parts exhibit continuous crystal structures and zero internal defects. That's the difference between components failing under stress versus components exceeding design specifications. Hydraulic systems monitor pressure continuously. Deviations exceeding 1% trigger automatic shutdown, because overpressure shatters dies costing millions, while underpressure produces weak forgings requiring scrapping. After initial compression, the workpiece requires reheating and multiple press cycles. Large forgings need 20 to 40 separate compressions, each reshaping metal incrementally. Between cycles, manipulators, robotic arms capable of rotating 300-ton workpieces, reposition the forging. These manipulators exert forces exceeding 500 tons merely to rotate incandescent metal safely. Picture this: the forging process for a single large component spans 2 weeks. Workers cycle the workpiece between furnace and press 40 times, gradually transforming a rectangular billet into complex shapes: bulkheads for aircraft fuselages, rocket motor casings, pressure vessel heads. Each press cycle compresses the forging 3 to 6 inches, permanently deforming metal through controlled violence. Temperature control matters critically. Too hot, metal oxidizes excessively. Too cold, it cracks under pressure. Operators monitor color constantly, making decisions affecting millions in material value based on visual assessment of orange to red glow transitions. Quality control begins before forging even starts. Ultrasonic inspection systems scan billets, searching for internal defects invisible to naked eyes. Even microscopic inclusions, slag particles, oxide stringers, sulfide formations, become stress concentrators, causing catastrophic failure in finished components. Rejected billets return to steel mills for remelting. After forging, dimensional inspection using laser scanning creates three-dimensional models accurate to thousands of inches across components 30 feet long. Metallurgical testing cuts samples from forging edges, examining grain structure through electron microscopy. Grain size, orientation, boundary spacing, all must meet specifications tighter than semiconductor manufacturing tolerances. Modern aerospace forgings require grain sizes smaller than 0.005 inches, with elongation ratios exceeding 10 to 1. Without precise microstructure control, components fail unpredictably during service, potentially causing catastrophic accidents. This technology race began during Cold War paranoia. In 1955, the Soviet Union commissioned a 75,000-ton press at Novokramatorsk specifically for forging submarine hulls and missile casings. American intelligence discovered this capability through spy satellite photographs showing the massive building housing it. President Eisenhower immediately authorized construction of matching presses. The Air Force Heavy Press program built 12 presses between 1956 and 1959, including twin 50,000-ton giants at Alcoa and Wyman Gordon. These presses enabled Boeing 707 and later jumbo jets. Without them, aircraft manufacturers couldn't produce wings large enough. The strategic logic was brutal. Whoever controlled large forging capacity controlled aerospace dominance. Nations without heavy presses bought components from competitors, creating national security vulnerabilities. China entered this arena late but decisively. Their 80,000-ton press, exceeding any Cold War relic, announced intentions clearly: aerospace independence. Today, China produces aircraft landing gear, rocket stages, and turbine components previously imported from America and Russia. The press paid for itself within 5 years through import substitution alone. Carbon emissions drop by 43% when forging replaces welded assembly in aircraft structures, eliminating welding energy and reducing weight through integrated designs. Industry saves over $32 billion annually through large forgings versus machining components from solid billets, which waste 90% of material as chips. Processing costs drop 61% because one forging operation replaces dozens of machining hours. So here's the secret promised: these monster presses exist because physics favors size. Larger presses forge larger components in single operations, eliminating joints where failures initiate. Every weld introduces heat-affected zones with altered crystal structures becoming crack paths. Every bolted joint adds weight and complexity. Seamless forgings eliminate these vulnerabilities entirely. That's why the Airbus A380's wing ribs come from single forgings. No welds, no joints, just continuous metal flowing across 20-foot spans. From Cold War arms race to commercial aerospace dominance, cycle completes. The 80,000-ton press represents more than manufacturing capability. It's geopolitical leverage. Nations with these machines build aircraft, rockets, submarines independently. Nations without them remain customers, technologically dependent, strategically vulnerable. We've learned that industrial capacity determines global power hierarchies as surely as nuclear arsenals. That press standing in Sichuan doesn't just forge metal, it forges national sovereignty.
Every year, billions of square feet of drywall are produced worldwide. In the United States alone, over 27 billion. That's enough to lay a 3-foot wide path from the Earth to the Moon, and still have enough for halfway back. Imagine millions of tons of stone being transformed into the smooth walls of our homes. But the real secret begins where ordinary gray stone becomes a thirsty powder, a material that can miraculously turn back into stone. Watch closely. At the end, you will discover a secret that most people have never even guessed. The numbers behind drywall production in the United States are not just big, they are astronomical, and they tell a story of how the country builds, renovates, and breathes. In a recent year, factories in the US produced approximately 27 billion square feet of drywall panels. This number is so colossal that it's hard to comprehend. Try to imagine, if you were to lay out all this amount of drywall, you could create a continuous 3-foot wide path that would stretch from the Earth to the Moon and almost halfway back. Or, with this number of sheets, you could completely cover the entire territory of the state of Delaware twice, and still have some left over. This endless stream of building material is not only a physical product, but also a powerful economic indicator. The market for these panels in the US is valued in the tens of billions of dollars, reflecting not just the cost of the material itself, but also thousands of jobs in mines and factories, in logistics and construction. It all begins not in a workshop, but much earlier, in a quarry where gypsum is mined. This is a natural mineral, a stone that formed millions of years ago from ancient seas. It can be white, grayish, sometimes with pink veins. Huge excavators dig into the gypsum deposits and load dump trucks with boulders of this stone. These trucks bring tons of gypsum to the factory and dump it onto the raw material yard, creating entire mountains waiting for their transformation. The first stage inside the factory is coarse crushing. The gypsum boulders fall into the giant steel jaws of a primary crusher. With a deafening roar and grinding, the machine breaks the large stones into smaller pieces, the size of a fist. This is just the beginning. Then this crushed gypsum is fed by a conveyor belt to secondary mills. Here, dozens of steel hammers, rotating at an insane speed, break these pieces into even smaller fractions, turning them into something like coarse gravel. But even this is not enough. The final stage of grinding turns the gypsum into a fine, powder-like dust. It becomes so fine that it resembles flour or dust. This powder is the main raw material, but it still hides a secret that needs to be revealed. The next step is one of the most important and interesting. It's a process called calcination, and in essence, it's the controlled drying of gypsum. The thing is, in the crystalline structure of natural gypsum, water molecules are locked in. For drywall to be able to harden, this water must be temporarily driven out. To do this, the white powder is fed into a huge, slowly rotating kiln. It looks like a giant drum, tilted at a slight angle. Inside this kiln, a very precise temperature is maintained, around 300 degrees Fahrenheit. The gypsum powder, slowly tumbling inside the drum, heats up, and the water bound to it turns into steam and evaporates. Chemically speaking, gypsum turns into calcium sulfate hemihydrate, but to put it simply, it becomes thirsty. Now this powder, which is now called plaster of Paris or stucco, has a unique property. If you add water to it again, it will greedily absorb it and turn back into a hard gypsum stone. It is this property that lies at the heart of the entire production process. The resulting hot powder is cooled and stored in giant silos, resembling towers, from where it will be fed to the main production line. And now the most spectacular part begins, the creation of the sheet itself. In the workshop, there is a huge conveyor, hundreds of feet long. At its beginning stand two giant rolls of special dense paper, or paperboard. One roll is for the face side. It is perfectly smooth and white. The other is for the back side. It can be a bit darker and grayish. The ribbon from the bottom roll, the face side, is unwound and laid on the conveyor, forming an endless track. In parallel with this, in a giant mixer resembling an industrial food processor, the core is prepared. Our thirsty gypsum powder, water, and a whole cocktail of various additives are continuously fed into it. Each additive plays its own role. Foaming agents make the gypsum mass lighter and more porous, like whipped cream, to reduce the weight of the sheet. Plasticizers make the mixture more fluid, so it spreads evenly. Accelerators or retarders allow engineers to perfectly control the time it takes for the gypsum to set. Starch helps the gypsum core to better adhere to the paper covering, and fiberglass adds strength. This mixture, called a slurry, resembles a thick grey porridge. It is poured in a continuous stream directly onto the paper ribbon, moving on the conveyor. Special devices evenly distribute this mass across the entire width of the paper. The edges of the bottom sheet of paper are neatly folded upwards, forming the sides of the future sheet. And at this moment, the second ribbon of paper from the back roll is laid on top, like a lid. The result is an endless, perfectly even sandwich. Paper, gypsum mass, paper. This sandwich immediately passes between two rollers or under a forming plate, which compress it to a precisely specified thickness, for example, ½ inch. The newly formed, still soft and wet sheet of drywall continues its journey on a very long conveyor, which is called the setting line. Its length can reach several hundred feet. As the sheet slowly moves, a real miracle happens inside it. The gypsum powder reacts with water. The rehydration reaction takes place. The gypsum turns back into a hard stone, releasing heat in the process. If you touch the sheet at this stage, it will be warm. In a few minutes, the loose mass becomes hard enough to hold its shape. At the end of this long line stands a flying knife. This is a huge blade that moves in sync with the belt, and at the right moment makes a quick, precise cut, slicing the endless sandwich into sheets of standard length, for example, 8 or 12 feet. This happens so quickly that the conveyor doesn't stop for a second. The cut sheets are now hard, but still very wet. They contain excess water that did not take part in the chemical reaction. It needs to be removed. Therefore, a special device flips the sheets and feeds them into the most large-scale structure in the factory, a multi-level drying kiln. This is a giant labyrinth consisting of several levels, each of which is a conveyor. The drywall sheets slowly move along these levels back and forth, traveling a path of several hundred feet inside this huge furnace. Hot air circulating inside gently evaporates the excess moisture from them. The temperature here is controlled very carefully. Only the free water needs to be removed without damaging the crystal structure of the gypsum itself. This process can take about an hour. At the exit of the dryer, the product we are familiar with appears, a perfectly dry, light and strong sheet of drywall. But this is not the end. The final stage is finishing. Two finished sheets are stacked face to face. Their edges are perfectly trimmed to be even and clean. A paper tape with information about the manufacturer and product type is glued to the ends. After this, robotic manipulators with superhuman precision and grace lift the finished sheets and stack them in perfectly even piles on pallets. Each stack is wrapped in protective film, labeled, and sent to the warehouse. From there, it will travel to construction sites to become part of someone's home, having transformed from a simple gray stone mined from the earth into a smooth and cozy wall. Drywall production is like a barometer of the construction industry's health. When the economy is on the rise, people actively build new houses and renovate old ones, and the demand for drywall skyrockets. The factories that produce this product operate at full capacity, and the flow of trucks delivering the finished sheets across the country becomes endless. The heart of this production beats in unison with the rhythm of the real estate market. Geographically, this industry also has its centers. Although drywall manufacturing plants are located throughout the country to be closer to large construction markets, the mining of the main raw material, gypsum, is concentrated in certain states. The leaders here are states like Texas, Oklahoma, Kansas, Nevada, and Iowa. Every year, the world cranks out over 100 million cubic meters of medium-density fiberboard. That's such a massive amount that you could build a road around the entire planet with it, every single year. Imagine this. What was once trash, sawdust, wood chips, and scrap paper, is now transformed into a material worth over $25 billion. China controls half of the entire volume, while Europe and the US add millions of cubic meters each year. But what's really going on behind the factory walls, where wood dust goes from being waste to perfectly smooth panels? If you stick around to the end, you'll learn a secret that's usually kept hidden. The foundation for medium-density fiberboard isn't whole logs, but what used to be considered rubbish: sawdust, wood chips, offcuts, and even old scrap paper. It's a triumph of smart resource use. These mountains of wood waste are brought to the plant and first get a thorough cleaning. Powerful magnets pull out any metal contaminants, nails, staples, while screening systems remove sand and stones that could damage the expensive equipment. After that, the raw material goes into a huge vat where it's washed and steamed with hot steam. This isn't for cleanliness. It's done to soften the lignin, the natural glue that holds the wood fibers together. Now comes the most important step, the one that separates medium-density fiberboard from its rougher cousin, particle board. The prepared, softened wood chips are fed into a machine called a defibrator, or refiner. Imagine two giant metal plates, like millstones, spinning towards each other at enormous speed. On their surfaces is a complex pattern of sharp ridges and grooves. The wood mass gets caught between these discs, and they literally comb it apart into its tiniest components, tearing it into individual wood fibers. This isn't shavings anymore. It's something like a fluffy, moist cotton or wood flour. We've just deconstructed the wood down to its basic building blocks. Next, this fibrous mass needs to be dried. But it has to be done very quickly before the fibers start to stick together. So they're blown into a long, hot tube dryer. A stream of hot air picks up the fibers, and as they fly through this tube, all the excess moisture evaporates from them. And right here, while the fibers are still hot and flying in this whirlwind, the next key stage happens: resination. A fine mist of a binding agent is sprayed into the airstream through special nozzles. This is urea resin, our glue. This mist envelops every tiny fiber, coating it with a thin, sticky film. It's a very efficient method that guarantees a perfectly even distribution of the glue. Now this resin-soaked, dry, and light as fluff mass is ready to become a board. It goes into a forming machine. The stream of fibers settles onto a wide, moving conveyor, forming a thick, fluffy, and perfectly uniform mat. Special rollers slightly compact it, and giant knives cut off pieces of the required length. It's already starting to look like a future board, but for now, it's just a thick, soft mattress of wood fluff. And now comes the climax: hot pressing. This fluffy mat rolls into a giant press. This can be either a multi-opening press that squeezes a whole stack of boards at once, or a continuous press that looks like giant moving tracks. And here, our mat is hit by two powerful forces at the same time. First, colossal pressure. The press plates squeeze our fluffy mattress with hundreds of tons of force, reducing its thickness several times and squeezing out all the air. The wood fibers are pressed tightly against each other, forming an incredibly dense structure. Second, a high temperature of 400 degrees Fahrenheit. That's 200 Celsius. This heat does two things. It activates the resin, causing it to polymerize and permanently glue the fibers into a single solid block. And at the same time, it evaporates any remaining moisture, which escapes from the board as hissing steam. After a few minutes in this steel embrace, the fluffy mat transforms into a hard, dense, perfectly flat, and still very hot board of medium density fiberboard. After the press, the hot boards can't just be stacked. They need to be cooled to relieve internal stresses. They're placed in a special fan cooler, which looks like a giant filing cabinet, where they slowly cool while being fanned with air. Once the boards have cooled, it's time to give them a finished look. First, they're stacked in high piles and left to rest for a few days. This stabilizes their internal structure. Then, each board goes through a sanding machine. Imagine a giant belt sander with several heads. Wide abrasive belts remove a thin surface layer from both sides, bringing the board to a perfectly precise thickness, for example, 16 or 18 millimeters, and creating that famous smooth as paper surface. And the final touch, cutting. Huge saws cut the large industrial boards into standard commercial formats. After this, each batch goes through strict quality control. Its density, strength, thickness, and surface quality are checked. The finished, perfectly smooth boards are labeled, packaged, and sent to furniture factories, where they will become the foundation for elegant and stylish items in our homes, silently demonstrating the noble path that ordinary wood dust can travel. The global market for medium-density fiberboard is a giant machine that turns over more than $25 billion a year. And this machine has no plans of stopping. Forecasts say it will grow by 6% every year. That means the demand for this smooth material is just insane. So who's the head chef in this kitchen? The undisputed king is China. It produces over 50% of all the medium-density fiberboard in the world. But Europe is no slouch either, with powerful players like Germany, Poland, and Turkey producing millions of cubic meters of high-quality board. Now for the volume. Every year, about 100 million cubic meters of medium-density fiberboard are produced worldwide. That number is so huge, it's impossible to imagine. Let's try. Picture a road. If you took all that medium-density fiberboard and built a road 10 meters wide and 25 centimeters thick, you could wrap that road around our entire planet at the equator every single year. It's an endless stream of material being turned into furniture, doors, and panels for our homes. Imagine this, a single piece of steel that can hold the weight of 100 fully loaded semi-trucks. How? It's all about a shape engineers call the I-beam. This isn't just metal, it's the backbone of our cities, born from rusted scrap and forged in lightning, fire, and thousands of tons of pressure. But here's the kicker. Why are brand new I-beams almost entirely made of the past? Cars from the 70s, rails from the 30s, even armor from World War II. All of it could be holding up a modern skyscraper. Stick around and you'll learn a secret that will change the way you think about the power of steel. The genius of the I-beam is its shape. The real heavy lifting is carried by the top and bottom parts, so that's where most of the metal is packed, in the flanges. The thin web in the middle just keeps them locked in place. This gives you maximum strength for minimum weight. And that strength is just insane. A single heavy I-beam, set up right, can handle loads of hundreds of thousands, sometimes even millions of pounds. Picture a whole line of fully loaded semi-trucks, all parked on one single piece of steel. That's real power. This story doesn't start in some shiny workshop. It starts in a massive, rusty, noisy yard that looks like a graveyard for metal giants. This is a scrap yard. Mountains of old cars, chopped up rail cars, building frames, and industrial junk are all waiting for a second chance. A giant crane with a powerful electromagnet drops down on the pile, and with a metallic groan, tons of old iron leap up to meet it. This scrap is the main ingredient. It gets loaded into a huge steel basket and sent to the melt shop for its trial by fire. Steel is the undisputed champion of recycling. The recycling rate for structural steel in the US is a whopping 98%. That means nearly every piece of steel from torn down buildings, old bridges, and scrapped ships gets put back to work. On average, a new I-beam made today is 90% recycled metal. This creates an incredible, endless loop. A skyscraper going up today could have a piece of a 70s muscle car, a 1930s railroad track, and even armor from a World War II battleship inside it. This isn't just a hunk of steel. It's concentrated history, melted down and reborn for a new tour of duty. So these numbers aren't just stats. They're the silent language our cities are built on, a language of strength, efficiency, and the almost endless life of metal. Every year, the United States cranks out over 5 million tons of structural steel, and the lion's share of that is I-beams. That's a number so big, it's hard to get your head around. Let's try. The steel in the famous Golden Gate Bridge weighs about 83,000 tons. That means, in 1 year, American mills produce enough beams to build over 60 Golden Gate bridges. The heart of the plant is the electric arc furnace, a giant kettle, the size of a small house, where our scrap metal is dumped with a thunderous crash. 3 massive graphite electrodes, thick as ancient trees, are lowered in from the top. And then the operator hits the juice. An electric arc, basically a man-made lightning bolt, erupts between the electrode tips and the metal with incredible force. The shop fills with a deep, bone-rattling roar, and the light from the arc is blinding. The temperature inside instantly shoots up to 3,000 degrees Fahrenheit. The metal doesn't stand a chance. It starts to melt, turning into a boiling, blazing lake of steel. Special additives are tossed into this molten bath to get the exact grade of steel needed, strong but flexible enough to handle massive loads. When the steel is ready, it's time to turn this liquid river into something solid. The molten metal is poured into a continuous casting machine. The blazing liquid flows into a special, water-cooled copper mold. As it passes through, the outer layer of steel freezes, forming a thin skin. Next, this still mushy on the inside ingot is continuously pulled downwards through a chamber of water spray where hundreds of nozzles blast it, forcing it to solidify all the way through. What crawls out of the machine is an endless, glowing red, massive steel billet. This is called a bloom. Automated torches hiss to life and slice off pieces to the right length, say 20 or 30 feet. This is our blank, our piece of dough that we're about to shape into a beam. These hot, but now solid blooms are sent to the next furnace, the reheating furnace. It's like a giant tunnel with a fire roaring inside. The blank moves slowly through it, where its temperature is cranked back up to the perfect working heat, around 2,200 degrees Fahrenheit. It becomes soft and pliable, like clay, ready for the most important step, rolling. And this is where the real show begins. The bloom, glowing a brilliant orange, rolls out of the furnace and hits the rolling mill. This is a series of giant steel rollers, like massive rolling pins, lined up one after another. But these rollers aren't flat. They have special grooves cut into them, shaped to gradually form an I-beam. The bloom slams into the first set of rollers. They squeeze it with thousands of tons of force, making it a little thinner and longer. Out the other side, it's grabbed by the next set, which squeezes it from a different angle, starting to form the flanges and the web of the future beam. And so, step by step, passing through dozens of these roller sets, our shapeless billet is stretched and molded, taking on that familiar I shape right before your eyes. It's an incredible sight. A piece of glowing steel that started at 20 feet long gets stretched into a fiery ribbon hundreds of feet long. The whole mill is filled with a symphony of bangs, screeches, and the hiss of water keeping the rollers cool. When the beam exits the final, finishing roller, it has the perfect shape and dimensions, down to a fraction of an inch. Hot, long, like a fire serpent, it travels down a roller conveyor to a massive cooling bed. This is a giant rack where the beam slowly cools, letting its heat radiate into the air. As it cools, the metal shrinks a bit, and sometimes the beam can get a slight warp. To fix that, after it's cooled down, it's sent to a straightener. This thing is like a giant steel chiropractor, passing the beam through a set of rollers that align it until it's perfectly straight. So, we have a perfectly straight, long beam, but it's not ready to ship yet. Time for the finishing touches. First, it's cut to the specific lengths the customer ordered. This is done by giant saws with blades 6 or 7 feet across. With a deafening scream and a shower of sparks, the saw cuts through the thick steel in seconds. Then, every single beam goes through a tough quality control check. Inspectors measure its geometry, and special ultrasonic machines scan the metal to make sure there are no hidden cracks or flaws inside. Only then does the beam get its marking, its birth certificate, with the steel grade, size, and batch number. The finished inspected beams are picked up by giant cranes and stacked in the yard, or loaded directly onto special rail cars or trucks. And just like that, this steel backbone, born from rusty scrap, forged through fire and pressure, is ready to ship out to a job site, to become the silent but incredibly strong skeleton for a skyscraper that will scrape the clouds, or a bridge that will connect two shores. Standard beams on a construction site can be anywhere from a few inches to 3 feet tall. But then there are the real monsters, the so-called jumbo sections, used in the most critical spots of skyscrapers. Their height can be over 4 feet, and their weight is something else. The heaviest ones can weigh over 800 pounds per foot. Think about that. Every foot of that beam weighs as much as 3 grown men. And a standard length for these things is 60, 80, or even 120 feet. A single one of those beams can weigh as much as a battle tank. Every year, billions of square feet of concrete are born in the world, but only a few know about the material that has turned construction on its head. Imagine this. In a single shift, one machine can create almost half a mile of slabs, and the annual output in North America is over 200 million square feet. That's the area of 30 pentagons. How do these lightweight slabs, weighing thousands of tons less, support entire buildings? The secret is hidden in their steel muscles and the mysterious voids inside. Watch till the end, and you'll discover something most people don't even have a clue about. The slip former machine crawls along a 600-foot casting bed at a speed of about 4 feet per minute. Doesn't sound too quick? Well, let's do the maths. That's 200 feet an hour. That's almost the length of an Olympic swimming pool, born from concrete in less than an hour. In a single 10-hour shift, one of these beds can churn out nearly half a mile of perfectly formed concrete slab. And a big plant might have several of these beds. This isn't just building, it's a conveyor belt running at a speed unthinkable for traditional pour on-site concrete. And now for the main trick, the hollow cores. These holes inside aren't just for looks. They slash the slab's weight by almost 50% compared to a solid slab of the same thickness and strength. What's the payoff? Picture this. You're building a 100,000 square foot office block. If the floors were made from standard, solid concrete, they'd weigh about 5,000 tons. But with hollow core slabs, just 3,000 tons. We've just stripped 2,000 tons of dead weight from the building. That's the weight of about 500 adult elephants that the foundations, columns, and beams no longer have to carry. This allows the entire structure to be lighter, more slender, and most importantly, a whole lot cheaper. But how can such a light slab be so strong? The secret is in those tensioned steel muscles. The concrete used in these slabs isn't what you'd find on the footpath. It's high-strength concrete that can handle pressures over 8,000 pounds per square inch, while standard concrete manages only 3,000 or 4,000. And the steel strands inside are tensioned with such force that they create a constant state of compression within the slab. Because of this, a hollow core slab can easily span 60 feet with no intermediate support at all. 60 feet. That's the width of a professional basketball court. Imagine a huge open space with not a single column in sight. That's exactly why these slabs are a favorite for building car parks, supermarkets, and open-plan offices. Every year, over 200 million square feet of hollow core slabs are produced in North America. The number is just staggering. It's enough area to build 30 colossal buildings like the Pentagon. Every single year. This isn't just a building material. It's an entire industry built on speed, efficiency, and clever use of resources. So these figures aren't just dry data. They're proof that sometimes, to get stronger, you just have to get rid of the unnecessary stuff on the inside. It all starts not in a concrete mixer, but on a massive, perfectly flat runway inside the workshop. This is the casting bed. Imagine a perfectly smooth, polished steel track a few feet wide, but 600 feet long. That's longer than 2 footy fields, end to end. Beneath this track run pipes circulating hot water or steam to keep it warm. This is the perfect cradle for the birth of our future giant. At both ends of this track stand massive steel abutments, anchored into a thick concrete foundation. They're like steel teeth sunk into the earth, and their job is to withstand simply inhuman loads. Between these two abutments, high-strength steel strands are stretched. This isn't your average wire. It's several steel filaments twisted together, each capable of holding the weight of a car. They are laid out along the entire 600-foot length of the bed, forming the slab's future skeleton. One end of each strand is securely fixed in an abutment. The other is hooked up to a giant hydraulic jack, and this jack starts to pull. It tensions each of these steel strands with a force of 30 or 40,000 pounds. That's like hanging 3 full-sized utes off each thin strand. The steel muscles tense up, becoming as taut as the strings of a giant guitar, storing a colossal amount of energy. This is secret number 1, pre-stressing. When the steel skeleton is strained and singing with tension, the star of the show appears, the slip former. This is one of the most incredible machines in the construction world. Imagine a strange, low-slung, self-propelled creature, slowly crawling on rails along our long bed. It has a large hopper on top, which is filled with concrete. But this isn't your typical liquid concrete. It's what's known as zero-slump concrete. It's so dry it looks like damp earth. If you picked it up, it wouldn't flow through your fingers. And so, this machine begins its slow journey. Inside, a real marvel takes place. Firstly, the concrete from the hopper is fed downwards, enveloping our tensioned steel strands. Secondly, special vibrators and compactors ram this dry mix with incredible force, making it unbelievably dense. And thirdly, and most importantly, inside the machine are special forming tubes, or mandrels, which vibrate as they push through the concrete, leaving behind perfectly round, smooth voids. The machine, like a giant concrete snail, slowly crawls forward, leaving in its wake a perfectly formed, endless concrete slab with hollow cores inside and tensioned steel muscles hidden within its body. Because the concrete is so dry, it holds its shape instantly and doesn't sag. This is secret number 2. The voids, which make the slab 50% lighter than a solid one while barely reducing its strength, as the top and bottom sections do most of the work. Once the machine crawls to the end of the 600-foot bed, its job is done. But our slab is still green and weak. It's time for a spa treatment. Workers cover the entire length of this concrete ribbon with huge insulating tarps, like blankets. Hot steam is then pumped under these blankets. This creates a sauna effect, which dramatically speeds up the chemical reaction of the concrete curing. Under normal conditions, concrete needs weeks to reach its full strength. But in this hot, humid atmosphere, it achieves the required strength of over 5,000 pounds per square inch in just 12 to 24 hours. When the concrete has set and become hard as rock, it's time for the release. Workers slowly let off the pressure on the hydraulic jacks. The tensioned steel strands, now permanently bonded to the concrete, try to shrink back to their original length. But the concrete won't let them. As a result, this massive compressive force is transferred to the concrete slab itself. Now it's not just a concrete slab, it's pre-stressed or compressed. This means that when a load from above tries to bend it, it first has to overcome this built-in compressive force. This is what allows it to span huge distances without extra support. And the final act of this performance, the cutting. A giant saw travels on rails along our long concrete ribbon. It's a monster with a massive blade coated in industrial diamonds. With a deafening roar and a spray of sparks and cooling water, this saw cuts the slab with incredible precision into sections of the required length, according to the order. The finished, perfectly flat, lightweight, and incredibly strong slabs are then picked up by giant cranes and loaded onto trucks. And just like that, after a journey from a tensioned steel string to the slow crawl of a concrete snail and a final diamond cut, this brilliant piece of engineering is born, ready to become the fast, efficient, and reliable flooring in the buildings where we live, work, and play.
The metal that protects all other metals from rust. Picture this. 70% of the world's steel is covered with a thin layer of zinc. Bridges, skyscrapers, cars, ships, everywhere zinc stands guard, taking the hit from corrosion. Every second, the world produces 1.5 tons of zinc, 14 million tons per year. It's the 4th largest metal by production volume on the planet, after iron, aluminum, and copper. But they extract it unusually. Zinc is vaporized at 1,800 degrees Fahrenheit, and the vapor is collected. Yes, the metal turns into gas. How do they turn gray ore, mined a mile underground, into a bluish-silver metal that sacrifices itself for others? You'll learn why the ore burns in furnaces, how they collect metallic vapor, and why without zinc, the entire infrastructure of the planet would collapse. Watch till the end. The finale will show what's behind every galvanized beam. This is the story of the bodyguard metal that took on the corrosion of the entire world.
A mile underground. Darkness. Explosion. Tons of rock crash down. This is a zinc mine, one of hundreds around the world where ore for the guardian metal is extracted every day. Underground dump trucks with 50-ton capacity haul ore to the mine shaft. An elevator the size of a house lifts the rock to the surface. The ore is dark, almost black. This is sphalerite, zinc sulfide. Crystals with diamond-like brilliance, but the metal content is only 10 to 15%. The rest is waste rock. Trucks carry the ore to the processing plant. The transformation from stone to metal begins. Massive cone crushers as tall as a 3-story building grind ore chunks the size of cars. The noise is deafening. The rock is crushed into gravel the size of fists. Then the gravel goes into ball mills, rotating steel drums 16 feet in diameter, filled with steel balls the size of watermelons. The drum rotates, balls fall, grinding the ore into fine powder. After 8 hours of grinding, you get gray dust, particles the size of sand grains. The ore powder is mixed with water, creating gray liquid slurry called pulp. It's pumped into huge flotation machines, tanks with volumes of 3,500 cubic feet. Chemical reagents are added, foaming agents and collectors. Mixers are turned on and air is fed from below. The magic of flotation begins. Millions of air bubbles rise through the pulp. Particles of sphalerite, zinc ore, stick to the bubbles and float up. A gray foam forms on the surface, 20 inches thick. This foam contains zinc. Waste rock settles to the bottom and is drained off. The foam is collected, filtered, dried. The result is concentrate, powder containing 50 to 60% zinc. From 100 tons of ore, you get 10 to 15 tons of concentrate. This concentrate is loaded into rail cars and shipped to the smelting plant. There begins the real alchemy, turning powder into molten metal. And this is a process where metal turns into vapor. At the plant, concentrate is loaded into fluid bed roasters, massive steel cylinders 66 feet tall. Hot air under pressure is blown in from below. The concentrate powder lifts up, floating in the air like dust. Gas burners are ignited. Temperature rises to 1,650 degrees Fahrenheit. The zinc sulfide ignites. Yes, the ore burns. Sulfur oxidizes, releasing enormous amounts of heat. Sulfur gas flies up the stacks. It will be captured and turned into sulfuric acid. And zinc sulfide transforms into zinc oxide, a gray-white powder. The temperature in the furnace is so high that the walls glow red. The roasted concentrate, zinc oxide, is cooled and mixed with coke, crushed coal. The proportion, 3 parts oxide to 1 part coke. This mixture is loaded into vertical retort furnaces, steel towers 50 feet tall, lined inside with refractory silicon carbide. Heating begins. Temperature starts climbing. 1,800 degrees, 2,000 degrees, 2,200 degrees. At 2,200 degrees Fahrenheit, carbon begins taking oxygen away from zinc oxide. A reduction reaction occurs. But something amazing happens. Zinc doesn't melt. Its boiling point is only 1,665 degrees, but the furnace is at 2,200. So zinc immediately turns into vapor, metallic vapor. Inside the furnace, atoms of gaseous zinc are flying around. The vapors rise up and exit the furnace through piping. They enter a condenser, a special cooled chamber. Temperature in the condenser is around 840 degrees, below boiling point but above melting point of zinc. The vapors condense. Drops of molten zinc settle on the condenser walls, glowing orange. Liquid metal flows down the walls and collects in a receiver. This is crude zinc, contains impurities of lead, cadmium, iron. Purity around 98%. Each furnace produces up to 100 tons of zinc per day. The metal is cast into molds. The result is ingold bars weighing 55 pounds each, silver gray with a bluish tint. For some applications, pure zinc is needed. Then it's refined, purified by distillation. Crude zinc is heated to boiling in a vacuum furnace. Under reduced pressure, boiling point drops to 1,300 degrees. Zinc vaporizes while impurities remain solid. Zinc vapors are condensed in a cooler. The result is refined zinc with 99.99% purity. This zinc is cast into ingots. On the ingot surfaces, a characteristic pattern forms, crystalline designs resembling frost flowers on glass. This is called zinc flowers. Ingots are stacked. Zinc is ready for use. But its main application awaits in hot-dip galvanizing baths. There, steel products will receive corrosion protection. The process looks impressive, like baptism of metal by fire. A steel beam 40 feet long is immersed in a bath of molten zinc. Temperature 840 degrees. The beam completely disappears in the silvery liquid. Chemical reaction begins instantly. Zinc reacts with iron on the steel surface, forming a layer of intermetallic compounds, a solid alloy of zinc and iron. This layer bonds permanently to the steel. On top, a layer of pure liquid zinc. The beam is held in the bath for 1 to 2 minutes. Then it's pulled out. Excess molten zinc drains back. In air, the coating quickly solidifies. The surface becomes silvery, matte, with the characteristic pattern of crystals, zinc flowers. Coating thickness from 2 to 8 thousandths of an inch. That's just fractions of an inch, but it's enough. The galvanized beam won't rust for 50 to 70 years. Even scratches aren't scary. Zinc continues protecting. It's about electrochemistry. Zinc is more active than iron. When corrosion begins, zinc oxidizes, not steel. Zinc sacrifices itself, protecting iron. This is called cathodic protection. World production of galvanized steel, 55 million tons annually. This uses 6 million tons of zinc. Without zinc, modern cities would be impossible. 70% of zinc goes to protecting steel. But there are other applications. Brass, an alloy of copper and zinc, has been known for thousands of years. Contains 15 to 45% zinc. Golden, strong, easily worked. Brass is used for plumbing fixtures, musical instruments, cartridge cases, decorative items. Zinc die casting, a method for manufacturing complex parts for automotives and electronics. Molten zinc is injected under pressure into steel molds. The result is complex-shaped parts accurate to tenths of thousandths of an inch. Zinc batteries, still used by the billions. Zinc powder in chemical industry. Zinc oxide in rubber industry, cosmetics, medicine. Zinc ointment heals wounds. World zinc mining, 14 million tons per year. China produces 40%, 5.5 million tons. Peru, Australia, USA, India, other major producers. Zinc price, around $3,000 per ton. The history of zinc as a separate metal began late. Europeans knew brass since ancient Rome, but couldn't obtain pure zinc. The problem, zinc evaporates when heated. Indian and Chinese metallurgists in the 16th century learned to condense zinc vapors in closed retorts. In Europe, pure zinc was obtained by German chemist Andreas Markgraf in 1746, but mass production began in the 19th century. Revolution happened in 1836 when French engineer Stanislas Sorel discovered the hot galvanizing process. He found that immersing steel in molten zinc protects from corrosion. This changed construction forever. Before galvanizing, steel structures rusted within years. With galvanizing, they serve for decades. The Eiffel Tower is painted, but many bridges from that era are galvanized and still standing. Today, without galvanized steel, skyscrapers, bridges, power lines, ships are impossible. Zinc, the invisible guardian of infrastructure.
And so, having traveled from explosions a mile deep through giant crushers and flotation tanks, through fluid bed furnaces at 1,650 degrees and retort towers at 2,200, through transformation into metallic vapor and condensation, zinc emerges, the bodyguard metal of modern civilization. The silvery metal that sacrifices itself, protecting steel from rust. the fourth largest metal by production on the planet, without which all infrastructure would collapse. Every time you see a steel bridge beam, a roofing sheet, or a car body, know they're protected by a thin layer of zinc as thick as a human hair. A layer that takes on corrosion, oxidizes instead of steel, slowly destroys itself, saving the structure. This is a story of nobility at the atomic level, how one metal protects another, sacrificing itself. From underground explosions to silvery skyscraper beams, zinc's journey spans several weeks and 2,200 degrees. The metal that vaporizes to protect, that oxidizes so others don't rust. The invisible shield of 14 million tons annually, standing between steel and corrosion. Zinc. This is why bridges don't collapse, roofs don't leak, and cars don't turn to dust in 5 years. The guardian metal, the sacrificial metal, the metal without which the modern world would simply fall apart from rust.
Every year, humanity creates over 10 million tons of this soft stone. It's as light as air, but as strong as steel. Its birth is a spectacular dance of flame and steel, where stone is transformed into billions of fibers. However, behind the impressive footage lies a technological trick that makes this material unique. Wait until the end, and you'll find out how this inconspicuous insulator can change the future of our civilization. At the core of this magical transformation lies a raw material gifted by nature itself or by industry. To create the most well-known type, stone or basalt wool, exclusively rock types are used: basalt, gabbro, dolomite, and limestone, which make up to 98% of the finished product's weight. In another case, for the production of glass wool, the main components are quartz sand, soda ash, limestone, and, importantly from an environmental perspective, up to 80% recycled glass cullet. There is also slag wool, which is made from blast furnace slag, a byproduct of metallurgical production. It all begins at the raw material yard, with a stage of careful preparation. Rocks are crushed and sorted to obtain fractions of the required size and the ideal mineral composition. The components for the future glass or stone are dosed with pharmaceutical precision, because the key properties of the future fibers, their strength, durability, and temperature resistance, depend on the correct proportions. Next, the prepared mixture, which professionals call the batch, is sent to its fiery heart, the melting furnace. This could be a vertical cupola furnace, where the raw material is melted by the heat from burning coke, or a huge tank furnace. Here, at a temperature between 1,400 and 1,500 degrees Celsius, the solid components are transformed into a homogeneous, viscous melt. This process is under constant control, as the slightest temperature deviation can change the viscosity of the mass and thus affect the thickness and length of the future fibers. When the stone has finally submitted to the fire and turned into a liquid mass, the most responsible and spectacular stage begins: fiber formation. The melt is fed in a thin stream onto the rollers of a centrifuge, which rotate at an insane speed. Under the influence of colossal centrifugal force, the red-hot mass is stretched and torn into millions of microscopic threads. To make them even thinner, a powerful stream of heated gas or steam is additionally directed at them. This whole process is very reminiscent of making cotton candy, only instead of sugar here, it's molten rock. Right in the process of forming these fibers, a special binding agent is sprayed on them, usually based on safe resins. It is needed to bind billions of individual threads into a single whole. Along with it, hydrophobic additives are added, which give the future insulation water-repellent properties. A cloud of these newly created fibers, already treated with a binder, gently settles on a wide, moving conveyor. A special pendulum mechanism evenly distributes them across the entire width, forming a primary, still fluffy and soft mat. It is here that the future structure of the material is laid, chaotic or layered, on which its mechanical characteristics will depend. For this fluffy mat to acquire strength, resilience, and its final form, it is sent into a long polymerization chamber. Here, under the influence of hot air with a temperature of about 250 degrees Celsius, the binding resin hardens, securely bonding the fibers together into a three-dimensional structure. Excess moisture evaporates, and a strong and stable mineral wool web emerges from the chamber. After such a hot hardening, the material needs cooling. Fans blow room temperature air through it, preparing it for the final stage. The endless ribbon of mineral wool enters the cutting line. Sharp circular saws and milling cutters cut it lengthwise and crosswise into slabs or rolls of clearly defined sizes. The most modern productions use robotic systems with water jet cutting for this, which ensures perfect accuracy and a complete absence of dust. The final stage before the installation is sent to construction sites is packaging. Since 99% of the volume of mineral wool is air, it is compressed for ease of transport and storage. Powerful machines compress the product, reducing its volume several times and hermetically pack it in durable film. But don't worry, thanks to the extraordinary resilience of the fibers, after unpacking, the material fully restores its original thickness and all its unique properties in a matter of minutes, ready to serve for decades, keeping our homes warm and cozy. It's important that modern factories have turned production into a virtually waste-free process. All trimmings and material residues are collected and returned to the very beginning of the cycle, into the melting furnace, saving natural resources and energy. The scale of this industry and its real impact are impressive. The mineral wool market in Europe is a giant industry, with annual production exceeding 10 million tons. According to expert calculations, over 50 years of operation, every ton of mineral wool produced helps prevent the emission of over 200 tons of carbon dioxide by saving energy on heating and air conditioning. This colossal contribution to the fight against climate change makes the material not just a building material, but also strategically important for the future. Although mineral wool seems soft in its overall mass, each individual fiber is a microscopic needle of glass or stone. Its diameter is only from 3 to 7 micrometers, which is about 10 times thinner than a human hair. Upon contact with the material, especially when it is cut, some of these tiny but brittle fibers break. The sharp fragments get on the skin and mechanically irritate its upper layers, causing a tingling or itching sensation. This sensation is not a chemical or allergic reaction, but purely a mechanical irritation, similar to touching thousands of microscopic splinters. Because of this, when working with mineral wool, it is necessary to use personal protective equipment: gloves, long-sleeved clothing, goggles, and a respirator. Modern manufacturers have significantly improved the quality of the fiber, making it more elastic and less brittle. Higher quality binders better hold the fibers within the slab, which reduces the amount of dust and free particles. Therefore, today's mineral wool is safer and more comfortable to work with than its counterparts from 20 years ago. Every year, over 65 million tons of aluminum are produced worldwide, but only 4% of it is born in the heart of the desert, at the Emirates' global aluminium plants. Here, amidst heat exceeding 1,200 degrees and power greater than that of small nations, metal travels a path from a gleaming ingot to the facades of the legendary Palm Jumeirah. Tens of thousands of tons are transformed into bridges, panoramas, and a light that never goes out. But behind this brilliance lies a story you haven't heard yet. Watch until the end. and you'll find out how this silver metal changed the face of Dubai forever. First and foremost, aluminum was used in the facade structures of hotels and residential complexes located on the fronds of the palm. It was chosen for its anti-corrosive properties. Unlike steel, aluminum naturally forms an oxide film that protects against moisture, salt, and ultraviolet light. The surfaces were treated using the anodic method, or powder coating was applied, creating textures that imitate marble, sand, or even mother of pearl, all to combine modern aesthetics with inspiration from nature. Emirates Global Aluminium is like an invisible engine that drives not only the industry, but also the landscape of Dubai itself. Their plant in Jebel Ali produces 1 million tons of aluminum annually, and the power station's capacity there exceeds 2,300 megawatts, like that of a small country. And the facility in Al Tawila in Abu Dhabi is even a third larger, 1,300,000 tons, and electricity, more than 3,100 megawatts. Together, these two giants produce almost 2,400,000 tons a year. That's approximately 4% of the entire global production. Palm Jumeirah, with its luxurious facades and bridges, literally lives on this metal. Some estimates suggest tens of thousands of tons were used just for the exterior surfaces, railings, lighting, and even balcony structures. It all starts with aluminum ingots, which arrive at the processing shop weighing 5,000 or 6,000 pounds each. These ingots from the smelters undergo an initial cleaning, where their surface layers are removed and they are prepared for melting. The melting furnaces operate at a temperature of 1,200 degrees Fahrenheit to turn the aluminum into a liquid, homogeneous mass. The liquid metal is poured into molds to create slabs approximately 6 inches thick, 20 feet long, and about 3 or 4 feet wide. The story of Emirates Global Aluminium is not just about numbers, it's also about over 330 different products, from sheet aluminum to forging billets. Aluminum with a purity of up to 99.96% goes into aviation, electronics, and architecture, as in the case of Palm Jumeirah. This island doesn't just consume metal, it demonstrates how it can be transformed into an environment where aesthetics and functionality go hand in hand. In addition to decorative elements, aluminum was actively used in window and balcony systems. The lightness of the material allowed for the creation of panoramic glass structures that offered views of the sea without overloading the building's foundation. Its thermal stability and ability to reflect solar rays helped reduce cooling costs, critically important in a climate where summer lasts almost all year round. After cooling, the ingots are cut into pieces convenient for rolling. Alloying elements are added to this: silicon, magnesium, manganese, to obtain alloys capable of withstanding ultraviolet light and sea salt spray for many years. Aluminum also became an integral part of infrastructure projects. Bridges between the fronds of the palm, service platforms, railings on the embankment, all of this is made from high-strength aluminum alloys. Its lightweight allowed for using fewer supports and assembling entire blocks faster without the need for additional cranes or heavy machinery. The next stage is rolling. The ingot is fed into rolling mills, where, under the pressure of rollers, it is formed into sheets with a thickness from 1/4 of an inch to 1 inch, as well as into profiles and extruded structures. These aluminum sheets can reach 15 feet in length and 4 or 6 feet in width, weighing up to 4,500 pounds for a single element. The roller of the rolling mill creates a hum. The metal is thinly drawn out and emerges as a smooth, shiny surface. Now, anti-corrosion treatment. Aluminum has a natural protection in the form of an oxide layer, but for a marine environment, additional anodic oxidation is applied. The sheets are immersed in acid baths with a temperature of 100 degrees Fahrenheit, under a voltage of up to 25 volts. Thanks to this, a thick, transparent oxide layer forms on the surface, which makes the aluminum even more resistant to salt, scratches, and ultraviolet light. After this, powder coating is applied, especially on facade panels. A stream of powder heats the sheet to 350 degrees Fahrenheit, where the powder polymerizes, creating a matte or glossy finish that can withstand 5,000 hours of salt spray. Aluminum panels and profiles, each weighing 2,500 pounds, are packed onto special ramps inside containers. To protect against temperature and moisture, the container is maintained at a temperature of 75 degrees Fahrenheit. When the cargo is ready, trailers take it to the port, where it is carefully loaded into large volume containers. One container can hold 5 tons of aluminum in various components. The sea journey lasts 2 or 3 nights, and when the container arrives at the island, it is unloaded in special thermal zones. There, the panels are carefully removed, unpacked, and the markings are checked, namely the serial number, production date, and coating thickness. Installation. Aluminum facade panels, roofs, and decorative elements are attached to steel frames. For this, stainless steel bolts, rivets, or geodetic fasteners with an allowable deformation of 1/16 of an inch are used so that the panels can breathe under temperature changes. Workers at a height above the sea install HVAC guides, gutters, skylights, and ventilation openings, all made of lightweight aluminum. Special attention is paid to lighting. Almost the entire system of street lighting and decorative illumination is aluminum. Thin posts, transparent luminaire housings that do not heat up, have a long service life, and maintain their appearance even during sandstorms. Thanks to its electrical conductivity, aluminum allowed for the integration of intelligent elements, motion sensors, brightness changes, and synchronization with the overall smart city system. The installation schedule is impressive. 15 to 20 panels are installed daily, each 200 square feet. In total, approximately 9 million pounds of aluminum are used on the project. According to expert estimates, Palm Jumeirah required tens of thousands of tons of aluminum, especially for facades, balconies, lighting, and bridge structures. The exact figures are not disclosed, but considering the scale of the island, it is one of the largest projects in the region where aluminum was a key material. What truly makes Emirates Global Aluminium special is their approach to ecology and technology. They were the first in the United Arab Emirates to license their own smelting technology abroad. In their data centers, artificial intelligence has reduced energy consumption by 50%, and data processing speed has increased 35 times. They haven't forgotten about recycling either. At Al Tawila, they launched the Aluminium Recycling Coalition initiative to reduce their footprint and create a closed-loop production cycle. And all this so that the metal used to make beer cans can become the foundation for the most ambitious urban dreams in the world. In the evening, the surface area of the panels reflects the sunlight in such a way that the island appears almost crystalline. The aluminum shines with silvery planes, while the steel remains a stern foundation. It all began with a melting furnace and ingots, and ends with an architectural shell that both protects and impresses. Every year, over 30 million tons of bamboo are harvested worldwide. But did you know that this seemingly ordinary grass can transform into steel, silk, and even concrete? It grows faster than any tree, absorbs more carbon dioxide than a forest, and doesn't require replanting. But the most interesting part is what's hidden inside its fibers. In this video, we'll show you how giant green stalks travel from plantations to ultra-durable flooring and delicate fabric. And if you watch until the end, you'll learn one shocking fact that will change your perception of the future of ecology. It all begins on vast bamboo plantations, covering millions of acres around the world. These are not chaotic thickets, but carefully managed farms. Unlike forests, bamboo does not require replanting. When one stalk, or kulm, is cut, its extensive root system, called a rhizome, immediately sends up new shoots. This makes it one of the most sustainable resources on the planet. One plantation can yield harvests for decades without harming the soil. Moreover, a bamboo forest absorbs 35% more carbon dioxide and produces 35% more oxygen than an equivalent area of trees. Harvesters, armed with simple machetes or handsaws, selectively cut only mature stalks, whose age can be easily determined by color and texture. Young shoots are left to grow further, ensuring the continuity of the cycle. One such mature stalk can reach 60 feet in height and weigh over 100 pounds, making its transportation from the plantation to the primary processing plant a complex logistical task. When these green towers arrive for processing, their radical transformation begins. First, the long stalks are cut into manageable sections. Then, they are fed into a special machine that, with a deafening crack, splits the round sections into long strips. The next step is to remove the outer green skin and inner nodes, leaving clean, light bamboo planks. But inside these planks still lurks an enemy of durability: starch and sugar, which are a favorite food for insects and mold. To get rid of them, the planks are submerged in huge vats of boiling water or a hydrogen peroxide solution for several hours. This hot bath not only sterilizes the bamboo, but also washes out all the nutrients. After this, the planks are sent for drying. Some producers dry them in the open air, but for industrial scales, they are loaded into giant kiln dryers, where they spend several days until their moisture level drops from 50% to an ideal 8 or 10%. This stage is critically important, as any residual moisture can lead to warping and cracking of the finished product. But the journey from a 60-foot pole to a smooth floorboard requires even more impressive engineering. The dried planks pass through milling machines that give them a perfectly rectangular shape. Then begins a process similar to making industrial lasagna. To create horizontal flooring, the planks are laid in a single layer and glued under pressure. For vertical flooring, the planks are placed on their edge and pressed from the side, creating a denser pattern. But the real marvel is the strand woven technology. Here, the bamboo planks are not just glued together, but completely shredded into long fibers, mixed with an environmentally friendly resin, and loaded into huge steel presses. Under infernal pressure, reaching 3,000 pounds per square inch, and high temperature, this mass transforms into an extremely dense, monolithic block. The hardness of such flooring on the Yanka scale can exceed 5,000 units, making it more than 3 times harder than oak, and more resistant to scratches and dents than most traditional wood species. However, hardness is only one of bamboo's facets. Its other superpower is the ability to transform into something incredibly soft and silky. The process of creating bamboo fabric is a true industrial alchemy. The most common method, known as the viscose process, begins with grinding the bamboo raw material into a cellulose pulp. This pulp is then submerged in a sodium hydroxide solution and then carbon disulfide, which turns it into a thick, viscous liquid. This liquid, resembling honey, is forced under pressure through the finest holes of a metal plate called a spinneret. Imagine a microscopic shower. Emerging from the holes, the thin streams enter a bath of sulfuric acid, where they instantly solidify, turning into endlessly long fibers. These fibers are then washed, bleached, dried, and twisted into yarn, from which fabric is woven. Despite the complex chemical process, the final product is biodegradable and has unique properties. It is extremely soft, hypoallergenic, has natural antibacterial properties, and breathes wonderfully, making it ideal for clothing and bedding. The global bamboo market is colossal and is projected to exceed $100 billion in the coming years. Annually, over 30 million tons of bamboo are harvested worldwide, and this figure is only growing. From kitchen cutting boards and toothbrushes to construction scaffolding capable of supporting the weight of concrete and elements in premium class cars, this giant grass demonstrates its versatility. It is a testament to how nature, multiplied by human ingenuity, can offer sustainable, strong, and beautiful solutions for countless tasks, turning a fast-growing straw into the gold of the modern world. Bamboo grows both in the wild and on specially created plantations. Its natural habitat mainly covers tropical and subtropical regions of Asia, where it is an integral part of local ecosystems. At the same time, thanks to its unique properties and wide range of applications, bamboo is actively cultivated on plantations around the world. It is cultivated for the production of building materials, textiles, paper, interior items, and as a source of biomass. In the wild, there are over 1,000 species of bamboo. It is a perennial evergreen plant belonging to the grass family. Bamboo is known for its extremely fast growth. Some species can grow several tens of centimeters per day. Bamboo blooms very rarely, and after flowering and fruiting, the plant usually dies. Growing bamboo requires certain knowledge and care, including proper planting, regular watering, and choosing the right variety for specific climatic conditions. There are even ornamental types of bamboo that are grown in gardens and at home. Every year, the world recycles millions of tons of wood waste, and a large part of this trash gets a second life in the form of what we see every day at home, at work, or in stores. Particle board. Imagine this: mountains of wood chips, sawdust, and old furniture being transformed into smooth panels capable of holding weight, keeping their shape, and becoming the foundation of modern interiors. But how is a monolithic material with a perfect surface created from a chaotic pile of scraps? In this video, we'll show you every step, from metal separators that pull nails from the waste to giant presses with temperatures over 400 degrees. And if you watch until the end, you'll discover a secret that will change your perception of furniture. It all begins at a huge raw material yard, where the foundation for the future particle board arrives in a continuous stream. This is a place where the idea of rational resource use is brought to life on an impressive scale. Contrary to popular belief, high-quality commercial timber is almost never used for particle board production. Instead, the production philosophy is to give a second life to wood waste, turning what was previously considered a byproduct into a valuable material. Piles of raw material, reaching tens of feet high, are brought here. The base is technological chips, obtained from low-quality wood that is not suitable for lumber production. A huge share consists of waste from sawmills, slab wood, which is the side parts of a log with a rounded surface, board offcuts, and thin strips that remain after log cutting. Woodworking waste, such as shavings and sawdust, generated at furniture and carpentry factories during planing and milling, is also actively used. A separate and important direction is secondary wood. Old wooden pallets, crates, packaging, and even used furniture, after a thorough cleaning process, get a chance for a new life as part of a particle board. Every batch of incoming raw material undergoes strict incoming inspection, as purity is the key to quality. The first stage of cleaning is the removal of metal inclusions. Powerful electromagnetic separators, capable of pulling a steel bolt from a distance of several inches, sift through the stream of raw material, removing nails, staples, and any other metal fragments that could catastrophically damage the expensive shredding equipment. Next, the raw material passes through screening systems to remove mineral impurities, sand, stones, and other debris that act as an abrasive and quickly dull the cutting tools. If whole logs are used in production, for example, 20 feet long, they must pass through a debarking machine. In a huge rotating drum, or with the help of special cutters, the bark is removed from them. This step is critically important, as bark has a different structure, contains a lot of dirt, and significantly worsens the quality of wood chip bonding, as well as negatively affecting the appearance and strength of the final product. The prepared and cleaned wood begins its journey on a conveyor belt hundreds of feet long, which relentlessly carries it to the first stage of mechanical transformation. It disappears into the steel maw of a giant chipper, an industrial monster the size of a small room, capable of swallowing pieces of wood several feet thick. Inside this machine, with a deafening roar that makes the workshop floor tremble, a massive disc equipped with razor-sharp knives rotates. Rotating at a speed of thousands of revolutions per minute, these knives cut into the wood with incredible ease, turning whole pieces into a stream of uniform chips a few inches in size. But this material, despite its uniformity, is only a semi-finished product. The resulting chips are too large, coarse, and non-uniform in shape to create a quality particle board. Their cubic structure would not allow for the creation of a dense and monolithic structure. Therefore, the next step is a finer and more delicate secondary grinding, which takes place in specialized flakers or mills. It is here, in the hum of high-precision equipment, that the very particle that gave the final product its name is born. At this stage, the geometry of the chip becomes crucial, as it is designed with engineering precision. For the outer, face layers of the particle board, which will be responsible for its appearance and smoothness, very fine, thin, and flat flakes are needed. They are produced in knife ring flakers, which literally shave thin flakes from the chips, resembling flakes only a few hundredths of an inch thick. These flakes, having a large surface area, perfectly bond with the resin and form a flawlessly smooth surface, ready for further processing. In contrast, for the inner central layer of the board, which is its structural backbone, larger and thicker flakes are used. They create a strong internal frame that gives the particle board its final rigidity, bending strength, and the ability to securely hold fasteners, such as screws and bolts. The resulting chip mass has varying moisture content, which is unacceptable for quality bonding. Therefore, all the chips are sent to one of the most important stages, drying. Usually, huge drum dryers are used for this. The chips are continuously fed into a rotating drum, where they are blown with hot air or flue gases. The process is strictly controlled by automation. The final moisture content of the chips must be in a very narrow range, from 2 to 6%. If the chips are over-dried, they will not be properly saturated with glue. If they remain too moist, during hot pressing, the excess water vapor can rupture the board from the inside, forming defects. The dried chips are not uniform in size. To create the correct 3-layer structure of the board, they must be sorted. The chip mass passes through a system of mechanical screens or air separators. Heavier and larger chips, intended for the inner layer, settle first. The lighter and finer fraction for the outer layers flies further. This process allows for obtaining 2 or more streams of chips of different geometries, which will be used to form the sandwich of the future board. Now it's time for the key component that will turn the loose mass of chips into a monolithic board, the binder. Most often, these are synthetic resins, mainly urea formaldehyde or melamine urea formaldehyde. The sorted chips enter special continuous mixers. Inside them, the resin is sprayed through nozzles, creating a glue mist that evenly envelops each particle of wood. The dosage of the resin is critically important and is usually from 6% to 10% of the mass of dry chips. Along with the resin, other components may be added. The resinated chips, now sticky and ready for bonding, are finally ready to become a board. They are transported to a massive forming machine, where a continuous chip mat is born from the scattered particles. It is here that the engineering magic of creating a 3-layer structure takes place. The forming machine is a complex system that sequentially and with high precision sprinkles chips onto a moving conveyor belt. First, it creates a perfectly even bottom layer, using the smallest fraction of chips. Immediately after this, a much thicker middle layer, consisting of large and strong chips, is laid on this base. Finally, the entire mat is covered with another layer of the fine fraction, creating a mirror image of the bottom layer. This carefully designed structure, resembling a sandwich, provides the unique properties of the future board. Its smooth and dense outer layers are ideal for further sanding and laminating, while the strong inner layer gives the board the necessary rigidity and the ability to securely hold fasteners. The formed but still loose mat passes through a pre-press, where it is significantly compacted. This pre-pressing removes excess air from it and gives it a shape convenient for loading into the main press. This is the culmination of the entire technological process. The pre-pressed and cut into fragments of a given length mat is fed into a hot press. This can be either a giant multi-opening press of periodic action, which simultaneously compresses a whole stack of boards, or a modern continuous press of the belt type. Inside the press, the chip mass is simultaneously affected by two powerful factors. Huge pressure, reaching tens of kilograms per square centimeter, compresses the chips, leaving no voids between the particles. At the same time, the press platens, heated to a temperature of 400 degrees Fahrenheit, transfer their heat to the mat. This high temperature activates the resin, launching an irreversible polymerization process. The liquid glue instantly turns into an extremely hard and strong polymer, which permanently glues millions of wood particles together. The time spent in the press depends on the thickness of the board and usually lasts only a few minutes. During this short period, the loose mat turns into a hot, hard, and absolutely monolithic particle board. The hot boards after the press cannot be stacked immediately. They need to be cooled gradually to relieve internal thermal stresses and avoid further deformation or warping. For this, they are placed in special star or fan coolers, where they are blown with air for several hours until they are completely cooled and their structure is stabilized. The next step is calibration and sanding, which gives the board a marketable appearance. The boards pass through sanding machines with several heads, where wide abrasive belts remove a thin surface layer, bringing the board to a precise specified thickness and creating a perfectly smooth surface. At the final stage, the large technological boards are cut into standard commercial formats, and their edges are trimmed. The finished product undergoes strict quality control, where its density, bending strength, moisture content, surface quality, and dimensional accuracy are checked. Only quality boards are marked and sent to the warehouse. From there, their path lies to furniture factories, where they will be transformed into familiar household items, silently demonstrating the amazing journey from unnecessary chips to a functional and indispensable foundation of our comfort. Every year, over 100 million small arms are produced worldwide. But only one rifle has truly become a legend: the AK-47, a symbol of simplicity, reliability, and an incredible history. It can be assembled and disassembled in minutes, even in the harshest conditions. And that's precisely why it earned the nickname, the weapon that never fails. In this video, we'll take a first-time look behind the scenes of its production, from a raw steel blank to the final tests at the shooting range. You will see the hidden processes that are usually not shown, and you will understand why the AK-47 has become the most recognizable rifle on the planet. When I entered the factory, I immediately felt that I had stepped into a place with a huge history. The air smelled of metal and oil everywhere, and the sounds of working machines created an atmosphere of important work. In this video, I want to show you how the AK-47 is made, starting from the raw materials and ending with the final assembly. We will see how a rifle, known worldwide for its reliability and simplicity, is born from ordinary materials. Believe me, you won't want to miss this exclusive look at the production process. On the production floor, I noticed how ancient methods are combined with modern technologies. Here, they strive to preserve traditions, but also make the process as efficient as possible. Next to the forging areas stood modern machines controlled by computers. The craftsmen here don't just work with metal. They put their soul into every detail, turning it into a part of a legendary weapon. It seems that every corner of this factory is steeped in history and the pursuit of perfection. The manufacturing of barrels is one of the most important and complex stages. The barrel is the heart of the rifle, and its accuracy is very important. I saw how large metal blanks are turned into hollow tubes with the help of special machines. But the real magic happens later, when spiral grooves are cut inside the barrel. These grooves help the bullet to spin so it flies more accurately. This is a very complex process, requiring enormous precision. Even a small mistake can ruin everything, so attention to detail here is at the highest level. I saw how the masters perform this work with pride and responsibility. Each barrel undergoes numerous checks to ensure it meets all standards. Engineers use special instruments to measure and check the inner surface of the barrel. It really looks like a scientific investigation, because even the slightest defect can affect the accuracy of a shot. They check the barrels with ultrasound, measure the diameter, and look for cracks. All this is done to make every rifle as reliable as possible. At the factory, they use both old methods and new technologies. For example, the stocks for the rifles are still made by hand from wood. The masters choose the best wood, birch or walnut, and process it to be strong and durable. They sand the stocks and cover them with special compounds to make them look beautiful and be strong. This shows that traditions and respect for history are very important here. At the same time, for modern models, polymers are used, which make the rifle lighter and more convenient. Injection molding machines produce plastic stocks with high precision, which helps to reduce weight and improve the weapon's characteristics. This combination of old and new makes the AK-47 truly unique. Quality control is a very important part of the work at the factory. Every detail goes through numerous checks. This is not just a visual inspection, but a real process using ultrasonic tests and magnetic particle inspection. All this is necessary to ensure that there are no defects in the parts that could affect the weapon's performance. Every assembled rifle is checked at a special shooting range to ensure it shoots accurately and reliably. I stood behind protective glass and watched as engineers tested each rifle. First, they checked how all the mechanisms worked, and then they conducted a test firing. This is very important, because even a small problem can cause the weapon to fail at a critical moment. If something goes wrong, the rifle is sent back for rework. Engineers also collect data from the tests to understand what can be improved in the production process. One of the engineers told me that all test results are recorded and analyzed. This allows for continuous improvement of the quality and reliability of the weapon. This process never stops. Every employee at the factory tries to do their part as well as possible. I was amazed that they don't just follow instructions here, but constantly strive to improve every detail, making the AK-47 even better. Applying a protective coating is another important stage of production. This helps to make the weapon durable and protected from external influences. At the factory, they use different coatings: traditional bluing, which makes the metal black and matte, and modern coatings that protect against rust. I watched as workers applied these coatings, and it was clear that they do it with great attention to detail. This is another example of how old and new methods are combined here to create the best weapon. The factory also makes magazines for the rifles. Magazines are an important part of any rifle, and they are given a lot of attention here. They make magazines from durable materials to withstand great loads. Each magazine is checked to ensure that it works reliably and will not fail in combat. I saw engineers inserting magazines into the rifle and checking the feeding of cartridges. This is another important stage that shows how they approach quality here. The most impressive stage is the final testing. In a special shooting range, each rifle is checked by firing it. I stood behind bulletproof glass and watched as engineers fired the rifles, testing them for durability and accuracy. Each rifle goes through a series of tests: single shots, automatic fire, and testing in different conditions. If something goes wrong, the rifle is sent for rework. Engineers collect data from these tests to understand how to improve the weapon. This is a continuous process that helps to make the AK-47 so reliable. When I was leaving the factory, I couldn't stop thinking about the complex history of this weapon. On the one hand, it has become a symbol of struggle and revolutions, and on the other hand, it has been used in wars and destruction. Having seen how much labor and skill is invested in each rifle, I realized that this is not just a weapon, but the result of engineering talent and human labor. Every detail is created with great attention, and this makes the AK-47 something more than just a rifle. It is a symbol of history, traditions, and the pursuit of perfection. The AK-47 is not just a weapon, it is a part of history. It was created to be reliable and easy to use. It can be disassembled and assembled in minutes, even in difficult conditions. This makes it popular among military personnel around the world. The simplicity of its design and high reliability are what make the AK-47 so special. Having seen how it is produced, I understood that every detail matters. Every screw, every barrel, and every stock is created with enormous attention to detail. Every year, over 100,000 kilometers of new rails are laid across the planet. And every single one of them goes through hell first. Fire over 1,500 degrees, the crushing force of rollers, and jets of water that cut metal like glass. From scrap heap to gleaming steel, a rail's journey is like an initiation, where every step decides whether it survives or shatters under the first train. But what makes this steel so perfect that it can handle thousands of tons of pressure every day without bending or cracking? Stick around, and you'll see how the arteries that move the entire world are born. First, you gotta make the steel. A mix of scrap metal, iron ore, coke, and limestone gets dumped into the furnace, the raw ingredients for a future rail. The temperature in the blast furnace hits over 2,700 degrees Fahrenheit. That's 1,500 Celsius. Under that hellish heat, the metal turns liquid, glowing like the sun. Workers keep a close eye on the composition. Even an extra 0.1% of carbon can make the rail too brittle or too soft. After melting, the molten steel is poured into molds, metal forms that create rectangular blocks called ingots or slabs. They don't look like a rail yet, just solid bars a few meters long and over a foot wide. After pouring, each blank is cooled, but not completely. It's kept warm to reduce stress during the rolling process. This stage is the foundation for everything. If the steel comes out bad, even a perfect rolling job won't save it. So quality control here is almost a ritual. Chemists check the composition, metallurgists monitor the temperature, and automatic sensors track the cooling uniformity. Only when every single parameter is locked in does the blank move on into the fiery heart of the rolling mill. In the rolling mill, massive billets, up to 20 meters long, are heated in furnaces to over 2,200 degrees Fahrenheit, 1,200 Celsius. The metal becomes pliable, like dough, but keeps its density and strength. The hot blank is immediately fed into reversing rolling stands. These are huge machines with heavy rollers. It passes through them several times, first to reduce its thickness, then to give it the right shape. Each pass is a squeeze and stretch, gradually transforming the metal from a simple billet into a future rail with its complex profile: the head, the web, and the foot. To get the exact geometry, they use a final sizing roll. It's like the final polish of the shape, with tolerances on this step not exceeding 0.3 of a millimeter. Right after rolling, while the rails are still hot, they go through a cooling process. They're either evenly blasted with air or left to cool on an open rack. It's crucial that the cooling is symmetrical, otherwise the metal could warp. To ensure a smooth, bump-free ride at high speed, individual rails are welded into long sections, up to 400 meters without a single joint. The main method is thermite welding. In a special mold between two rails, a gap of a few millimeters is left. A molten steel mixture, created by the reaction of powdered aluminum with iron oxide, is poured in. The temperature hits a scorching 4,500 degrees Fahrenheit, 2,500 Celsius. This molten metal flows into both parts of the rail and fills the joint area. When it solidifies, it creates a monolithic bond, stronger than the rail itself. After that, the excess metal is trimmed off, and the weld is ground down to a perfectly smooth level, without a single bump. Every joint is inspected with ultrasound or eddy currents to make sure there are no hidden micro cracks. These long rails are easier to transport than you'd think. They're either wound onto special drums or carried on platforms with pivoting supports. And on the construction site, the sections are joined again, this time by welding or using special bolted joints. The result is a continuous rail line that stretches for kilometers without a single click. The same silent glide we've come to expect on high-speed trains. But first, after rolling and welding, the rails are still alive. There's stress left inside the metal, and the grain structure needs to be stabilized. This is where heat treatment comes in, giving the rail its strength, wear resistance, and durability. And it looks almost like a metallurgical spa session. The rail is rapidly heated to high temperatures, around 1800 degrees Fahrenheit, 1000 Celsius. This is done in furnaces, tens of meters long, where the temperature is controlled to the degree. At this heat, the steel's crystal lattice shifts into a new state, austenite. But the main event starts after that. The rail is instantly cooled. Jets of high-pressure water are aimed along the head and web, the very parts the wheel rolls on. The temperature drops in a flash, and a new structure forms in the metal, martensite, an extremely hard, wear-resistant phase. But to avoid brittleness, the rail is slowly heated and cooled one more time. This balances the structure, relieves any extra internal stress, and ensures the rail can handle frost, heat, and thousands of trains a day. In the end, the metal holds its shape and withstands pressures of tens of tons per square inch without deforming. Before a rail hits the road, it goes through a whole series of tough tests, like it's trying to join an army of high-speed transport. In special labs, it's checked for strength, hardness, geometry, and internal defects. First up, ultrasonic testing. High-frequency waves are sent into the rail. If there's a microcrack or void inside, the signal bounces back and flags the problem. Then, hardness measurements along its entire length to make sure the heat treatment was uniform. At the same time, its straightness and profile are checked. Laser sensors scan every inch, detecting even tiny warps that could cause vibration or wear. And finally, bend and impact tests. A piece of the rail is loaded with pressure dozens of times greater than the weight of a train to make sure it can handle any challenge on the route. When the rail has successfully passed all the tests, it's time for its most important journey, to the installation site. But how do you transport giant metal strips over 90 meters long? Regular trucks can't handle it. Here, they use special railway platforms with curved supports that reduce stress and prevent the rail from sagging or vibrating during transit. Sometimes, rails are transported already welded into even longer sections, from 400 to 600 meters. Before installation, the rails are heated or cooled depending on the ambient temperature. This is to compensate for the thermal expansion and contraction of the metal. Otherwise, it would buckle in the heat or gaps would form in the cold. In practice, each rail is laid with these physical changes in mind, usually at a stress-free temperature point. Imagine this. Hidden right under your feet could be a mountain of old car tires. You'd think it's just rubbish, left to rot in a landfill for centuries. But what if I told you that this black rubber gets a second life and becomes the foundation for modern sports stadiums? every single football field uses up to 40,000 tires. Now, multiply that by the more than 13,000 arenas in the US alone, and you get hundreds of millions of old treads, transformed from the road into a green carpet for athletes. How exactly new life is born from dirty scraps? We're about to break it down, step by step. Stick around till the end, and you'll uncover a secret most people never even thought to look for. So today, we're heading to a cemetery. A car tire cemetery. Acres of land piled high with mountains of black rubber rings. These are the silent veterans of the road, having done their thousands of miles, now lying here, seemingly useless. But this isn't the end of their story. It's just the beginning of their amazing reincarnation. We'll follow how these worn-out, dirty pieces of rubber go through a series of brutal, yet high-tech trials to be reborn as the soft, springy heart of a modern sports stadium. This is the story of how the roar of the road turns into the quiet whisper under an athlete's feet. Americans have learned to give a second life to the vast majority of tires. The recycling rate for old tires in the US is now over 85%. That's one of the highest rates for any consumer product. That means over 250 million tires a year dodge the landfill and are sent off for a new life. Some of them are burned as highly efficient fuel, some are used in civil engineering, but a significant and growing number are turned into that very same crumb rubber. In this tire cemetery, a machine that looks like a steel Tyrannosaurus Rex is at work. This is an industrial shredder. A huge loader grabs a whole handful of old tires and dumps them into the machine's steel jaws. Inside, two massive shafts with thick, sharp hooks spin with a deafening screech. They grab the tires with relentless force and, with an incredible crack, tear them to pieces. There's nothing delicate about it. The shredder's job is simply to break the tire's integrity, turning it into rough, palm-sized chunks. At this moment, the first important liberation occurs. Inside, every tire is a steel cord, a strong frame of steel wire. As the tire is torn apart, this cord is released, turning into a shiny web of steel threads mixed with rubber chunks. This chaotic mix of rubber and steel moves along a conveyor belt. And here, a powerful, massive industrial magnet spinning above the stream of shredded material comes into play. Like a fridge magnet, but a million times stronger, it pulls all the steel threads from the rubber mass. With a screech and a clatter, the steel cord sticks to the magnet and is dropped into a separate container. This steel will later be sent off to be melted down, while our cleaned rubber continues its journey. But it's still too big and coarse. The next stop is the granulator. This is something like an angry coffee grinder the size of a car. Inside, sharp blades spin at enormous speed, chopping the large chunks into a smaller fraction, about the size of a fingernail. During this process, another component of the tire is released, the textile cord. These are nylon or polyester fibers that gave the tire extra strength. These light, fluffy fibers need to be removed. To do this, the rubber granules pass through a system of vibrating screens and air separators. Powerful streams of air literally blow away the light textile fluff, leaving only clean, heavy rubber granules. Now we have a clean, but still quite large material. To become the surface of a stadium, it needs to be turned into a crumb. For this, the granules are sent for final grinding, often in what are called cracker mills. These are two massive, grooved steel rollers that rotate towards each other at different speeds. The rubber granules, falling between them, are not so much cut as they are torn and ground into the tiniest particles. As a result of this process, we finally get what this was all about: crumb rubber. It's a uniform, free-flowing mass, like black caviar or coarse sand, where each particle is only a few millimeters in size. This crumb is carefully sifted to ensure a perfectly uniform size and is packed into huge 1-ton bags. Its journey from a dirty tire to a clean, high-tech raw material is complete. And now, let's jump to the place where this black crumb will find its true calling, the construction of a new stadium. Workers roll out huge rolls of artificial turf over a perfectly leveled gravel base. This isn't just a green carpet. It's a backing with long, soft polyethylene blades sticking straight up. But for now, they look sad and limp, pressed against the base. For them to stand up and look like real grass, they need support. And this is where a special machine, looking like a large fertilizer spreader, drives onto the field. A process called infill begins. First, the machine spreads a uniform layer of fine, rounded quartz sand over the entire field. It's heavy and settles right at the base of the carpet, acting as ballast to keep the turf from shifting and helping to stabilize the blades. And following the sand, our main hero is spread onto the field, the black crumb rubber. The machine distributes it just as evenly over the entire surface. And here, the main transformation happens. This crumb fills the space between the blades, forcing them to stand vertically, just like real grass. Secondly, and most importantly, it creates a cushioning layer. When an athlete runs, jumps, or falls, this layer of billions of tiny, springy rubber particles compresses, absorbing the impact energy. It's like running on a billion tiny trampolines. This drastically reduces the strain on athletes' joints and makes falls much safer. The final touch is combing the field. A special machine with a huge brush drives over the turf, thoroughly mixing the sand and crumb rubber and brushing them deep down to the base, making every blade stand perfectly straight. And so, when the work is done, what stands before us is a perfectly green, resilient, and safe field. And none of the players running on it might ever guess that under their feet, between the bright green blades, lie millions of particles of old car tires that have completed their epic journey from the roar of the motorway to the quiet, springy surface of a sports arena, having received a second, much nobler life. To create one standard American football or soccer field, you need, on average, between 20,000 to 40,000 old passenger car tires. Just think about it. A single field completely eats up a whole mountain of rubber waste. And how many of these fields are there in the country? Right now, there are over 13,000 artificial turf fields in the US, at schools, colleges, parks, and professional arenas. And that number is growing every year. Now for some simple maths. Even if we take the minimum figure of 20,000 tires per field, it turns out that over 260 million old tires have found their new home in the surfaces of sports fields across the country. That's almost a year's supply of all the rubber scrap the country generates. Natural grass is a very fussy thing. It needs to be constantly mowed, watered, fertilized, and given time to rest. On average, a natural field can handle no more than 20 hours of play per week. And an artificial turf field, it can operate 24 hours a day, 7 days a week, in rain or shine. Now, let's talk about water. A single artificial turf field can save from 500,000 to 1 million gallons of water every year. That's the amount of water an average family uses in several years. Add to that the savings on fertilizers, pesticides, and lawnmower work, and the benefit becomes obvious. So next time you see a bright green field, know that it's not just a place to play. It's a monument to human ingenuity that solves a waste problem, makes sports safer, and saves precious natural resources, one old tread at a time. Every year, over 3,000 tons of gold are mined worldwide. But you'll be surprised, a significant portion of this shiny treasure doesn't stay in mines or banks, but heads to a place where gold literally turns into art, Dubai. In a city that trades over $129 billion in gold annually, ingots become masterpieces that shine in the 300 shops of the legendary gold souk. What is really hidden behind the glitter of jewelry? Ancient rituals or cutting-edge technology? If you watch until the end, you'll discover a golden secret that almost no one knows. Our journey begins not in a luxury boutique, but in the bustling cargo terminal of Dubai's airport. It is here that tons of gold arrive from over 100 countries around the world, from distant mines in Africa, Australia, and America. These planes are not carrying passengers, but a precious cargo in the form of large, heavy ingots. Part of them is so-called doré gold, unrefined, with impurities of other metals, straight from the mines. Another part consists of standard bank ingots, but they all have a long path of transformation ahead of them. Dubai is not a mining location. It's a giant, incredibly powerful melting pot and production center, the largest gold hub on the planet. The first stop for our gold is a refinery. This is a true high-tech fortress, better protected than a bank. Here, the sacred act of purification takes place. Ingots are loaded into giant induction furnaces. The air is filled with a hum and heat. The temperature inside exceeds 1,900 degrees Fahrenheit, and the solid metal turns into a liquid, dazzlingly bright sun. The liquid gold boils, and impurities float to the surface, which are carefully skimmed off. But this is not enough to achieve perfect purity. Next, chemistry comes into play. The gold goes through complex electrolysis processes, such as the Miller and Wohlwill processes, where an electric current and chemical reactions are used to remove absolutely all foreign metals. The goal is to achieve a purity of 999.9, so-called 4 nines, the highest standard in the world. At the output, we get ingots of pure, almost otherworldly gold, shining with a deep, rich yellow color. But surprisingly, jewelry is rarely made from such pure 24-karat gold. Why? Because it's too soft. A ring made of pure gold could be deformed by a simple handshake. And this is where true jewelry science begins. To make gold strong and give it different shades, it is alloyed with other metals. This process is called alloying. Pure gold is melted again, and a strictly measured amount of ligature, an alloy of copper, silver, palladium, or zinc, is added to it. Do you want the classic yellow gold, so beloved in the East? Add a little silver and copper. Dreaming of romantic rose gold? Increase the share of copper. And for elegant white gold, palladium or nickel is needed. This is how different purities, or carats, are born. In the Dubai market, the most popular are 22 carats. This is 91.6% pure gold and 18 carats. That's 75% pure gold, which are the perfect compromise between purity and practicality. Now that we have a gold alloy of the desired color and strength, the most interesting part begins, the creation of the jewelry itself. And here, Dubai demonstrates all its versatility, combining futuristic technologies with a craft that is thousands of years old. Many pieces begin their life on a computer screen. Jewelry designers create complex three-dimensional models using CAD software. They can draw every detail, every swirl of a future necklace or earrings. Then this digital model is sent to a 3D printer, which, not from plastic, but from a special wax, grows a precise copy of the jewelry layer by layer. It's a wax wonder. Next, this wax model, or wax pattern, becomes the basis for casting. It is dipped into a special plaster-like mixture that hardens, forming a mold. Then this mold is heated. The wax melts out, leaving behind a perfectly accurate hollow impression of the future jewelry. And here it is, the moment of truth. Molten, red-hot gold is poured into this mold under pressure, or with the help of a vacuum. Every minute detail, reproduced with computer accuracy, is filled. When the metal solidifies, the plaster mold is broken, and a rough gold piece is born. But this is just a skeleton. Now master jewelers, whose skills have been passed down from generation to generation, get to work. They grind, polish, assemble individual parts, turning metal into a work of art. Imagine these workshops filled with the buzzing of drills, the quiet tapping of hammers, and the focused faces of the masters. They use techniques that haven't changed for centuries, creating the finest patterns from wire, inlaying pieces with precious stones, engraving complex Arabic ornaments. This is painstaking manual labor that requires incredible skill and patience. Each stone is set by hand, each link of a chain is checked for strength, and, of course, quality control. The government of Dubai is extremely strict about the reputation of its main market. Every piece undergoes a mandatory check in the municipal laboratory. A special hallmark is stamped on it, confirming the carat. This is a guarantee of authenticity. You will never buy a fake in an official Dubai store. This strict control system has created the city's reputation as the most reliable place to buy gold in the world. And so, having gone through this long and complex path, a piece of gold jewelry ends up in the window of one of the more than 380 shops of the legendary gold souk in the Dera district. This is a place where history meets luxury. A market that started in the 1940s as a small group of merchants from India and Iran has turned into a global center of attraction for everyone who appreciates the beauty of gold. Here you can see everything, from modest chains to giant wedding necklaces weighing several pounds, from classic Arabic designs to ultra-modern European styles. The air here is thick with the excitement of bargaining and the enthusiastic exclamations of tourists. This is not just a market, it's a show, an attraction, an open-air museum. This is the journey of gold in Dubai. From a formless piece of metal, mined thousands of miles away, through the fire of furnaces and the hands of talented masters, to a dazzling masterpiece waiting for its owner in the world's capital of glitter. It's a process where modern technologies serve ancient art and strict control guarantees quality. And all this to maintain the loud and absolutely deserved title, City of Gold. Incredible, isn't it? Dubai has firmly established itself as one of the leading global gold trading centers, ranking second in the world in 2023 by trade volume, surpassing the United Kingdom. The total value of gold trade in the UAE that year exceeded $129 billion US, which is 36% more than in the previous year. This highlights the rapid growth and strategic importance of the emirate in the global precious metals industry. Between 20 and 30% of the entire world's gold circulation passes through Dubai annually. Gold trade accounts for almost 30% of the UAE's total non-oil exports, which indicates a successful diversification of the economy. Last year, over 5,400,000 contracts were concluded on the Dubai Gold and Commodities Exchange for a total amount of over $1 billion, $115 billion. Gold and silver futures amounted to 80,000 contracts for a total of over $44 million. The dynamics of the gold market in Dubai are influenced by global economic uncertainty, fluctuations in the US dollar exchange rate, to which the UAE dirham is pegged, and stable demand from investors and consumers. In times of instability, gold is traditionally seen as a safe haven asset for investment. Analysts predict further market growth. The gold bullion market in the UAE is expected to grow at an average annual growth rate of almost 10% until 2031. This will be facilitated by a business-friendly regulatory environment, a developed logistics infrastructure, and the absence of value-added tax on gold. The UAE's entry into BRICS+ in 2024 opens up new opportunities for expanding gold trade with other market giants.
Every second, factories worldwide produce carbon fiber threads 10 times stronger than steel, yet 5 times lighter. Picture this. A strand thinner than human hair supports weights exceeding 400 pounds, more than 2 adult humans hanging from a thread, invisible at arm's length. These black filaments, woven into composites, form invisible to radar bombers, Formula One monocoques surviving 200-mile-per-hour crashes, and prosthetic limbs outperforming natural bone. How does ordinary plastic transform into material stronger than steel through fire? Why do engineers call carbon fiber the black aluminum, revolutionizing everything from spacecraft to tennis rackets? Stick around till the end. You'll discover the jaw-dropping reason carbon fiber doesn't break like metal but unravels like fabric, why recycling it became a technological arms race, and the shocking truth about what happens inside furnaces hotter than volcanic lava when atoms reorganize into crystalline perfection.
The story begins with polyacrylonitrile, pan fiber, the plastic precursor looking like white cotton thread. Massive spinning machines standing 3 stories tall in climate-controlled facilities extrude molten pan through spinnerets containing 50,000 microscopic holes. Each hole, measuring 3/10,000ths of an inch across, thinner than blood cells, produces one continuous filament. Picture spider silk production scaled to industrial extremes. These filaments emerge at speeds reaching 3,000 feet per minute, fast enough to cross football fields in seconds. Chemical baths stretch the fibers, aligning polymer chains parallel to fiber length. This molecular orientation determines everything. Randomly oriented polymers create weak thread. Aligned chains create strength rivaling steel. Workers monitor tension constantly. Variations of 2% cause inconsistent properties requiring entire batches, thousands of pounds worth, to be scrapped. The pan production facility operates 24/7, producing 50 tons daily, enough fiber to circle Earth's equator if laid end to end. Next comes oxidation, the first transformation where chemistry becomes alchemy. Massive ovens, stretching 200 feet long like horizontal tunnels, heat pan fibers to 500 degrees Fahrenheit in pure oxygen atmosphere. Inside these furnaces, oxygen atoms attack carbon-hydrogen bonds in the polymer backbone. Hydrogen burns away as water vapor, leaving behind carbon-nitrogen ladder structures stabilized through cross-linking. This stabilization process takes 90 minutes as fibers crawl through ovens on tensioned rollers. Temperature control matters critically. Too hot, fibers ignite catastrophically. Too cold, cross-linking remains incomplete, causing failure during subsequent heating. The oxidation chamber maintains oxygen concentration at 23% with tolerance of 0.5%. Operators monitor fiber color constantly, watching white pan transform through yellow to dark brown. That color change represents chemical metamorphosis, polymer becoming something fundamentally different, no longer meltable, now heat-resistant enough to survive temperatures that vaporize aluminum. Giant carbonization furnaces, operating at temperatures exceeding 3,000 degrees Fahrenheit, complete the transformation. These aren't ordinary ovens, they're inert atmosphere chambers purged with nitrogen gas, creating environments where oxygen molecules cannot exist. Inside this oxygen-free inferno, stabilized fibers lose nitrogen, hydrogen, and other non-carbon elements through thermal decomposition. Only carbon remains, reorganizing into graphite-like crystalline structures. The process occurs in stages. First, furnaces heat fibers to 2,700 degrees, driving off 90% of non-carbon atoms. The fiber shrinks 25%, density increasing as material compacts. Second stage furnaces push temperatures to 4,000 degrees for graphitization, the process aligning carbon atoms into perfect hexagonal sheets stacked like microscopic playing cards. This crystalline perfection gives carbon fiber its extraordinary properties. Processing takes 3 hours, crawling through furnace sections totaling 1,000 feet long. One power interruption, one oxygen leak, and fibers oxidize catastrophically, burning like magnesium flares, destroying millions in equipment.
Now comes surface treatment, electrolytic oxidation creating reactive sites for resin bonding. The carbon fiber, now black as obsidian and measuring just 0.003 inches diameter, passes through electrolyte baths while electric current flows through it. This electrochemical attack roughens the fiber surface at nanometer scale, creating anchor points where epoxy resins chemically bond. Picture this: untreated carbon fiber in epoxy resin slides apart like oiled rope, strong individually but weak as composite. Surface-treated fiber bonds molecularly to resin, creating integrated structure where fiber and matrix function as single material. Modern aerospace composites achieve interface strengths exceeding 12,000 pounds per square inch, meaning the bond between fiber and resin is stronger than many metals themselves. This step is critical because composite strength depends not just on fiber properties, but on load transfer efficiency from matrix to fiber. Poor surface treatment causes delamination, layers separating under stress, the characteristic failure mode making carbon composites unravel rather than fracture. The sizing application follows, coating fibers with protective polymer layer. Massive rollers submerge fiber tows, bundles containing 12,000 individual filaments, through sizing baths containing proprietary polymer formulations. This coating serves triple purpose: protects fibers during handling, improves resin wetting during composite layup, and provides limited abrasion resistance. Workers wind treated fiber onto spools holding 10 miles of continuous filament. These spools, weighing 200 pounds each, ship to composite manufacturers worldwide. Quality control inspects random samples continuously. Tensile testing machines pull individual fibers until failure, measuring breaking strength, elastic modulus, and elongation. Modern aerospace-grade carbon fiber withstands stresses exceeding 800,000 pounds per square inch, 50 times stronger than structural steel. The fiber stretches only 1.5% before breaking. Steel deforms 300% more. That limited elongation explains why carbon structures crack suddenly rather than bending. No warning, just instantaneous failure when stress exceeds capacity. After arriving at composite manufacturers, fibers get woven into fabrics or used as unidirectional tapes. Automated looms, programmed like textile machines but operating at glacial speeds to prevent fiber damage, weave intricate patterns. Plain weave creates checkerboard appearance, twill weave produces diagonal patterns, satin weave maximizes smoothness for aerodynamic surfaces. Each weave pattern offers different mechanical properties. Engineers select patterns matching stress directions. Picture this: laying up carbon composite resembles origami, with materials costing $300 per pound. Technicians cut fabric patterns, stacking layers in precise orientations. Each ply orientation, 0 degrees, 45 degrees, 90 degrees, contributes specific strength characteristics. A typical aerospace laminate contains 40 plies, each 0.005 inches thick, creating structures 8 inches thick, yet lighter than equivalent aluminum. Between each ply, workers brush epoxy resin, ensuring complete fiber wetting. Air bubbles trapped between layers become stress concentrators, causing catastrophic failure. So layup occurs in clean rooms, maintaining air purity rivaling semiconductor fabs. Curing transforms wet layup into solid composite through heat and pressure. Massive autoclaves, pressure vessels 30 feet in diameter and 100 feet long, create environments combining 300 degrees Fahrenheit and 100 psi pressure. Inside these industrial pressure cookers, epoxy resin chemically cross-links while pressure squeezes out excess resin and air voids, compacting layers into dense laminates. The cure cycle takes 8 hours following computer-controlled temperature and pressure ramps. Heat too fast, resin boils, creating voids. Heat too slow, productivity plummets. Modern autoclaves monitor 200 sensors simultaneously, adjusting conditions to within 1 degree and 0.5 psi. After curing, parts exit as rigid structures, material properties now locked permanently. Non-destructive testing using ultrasound and X-rays searches for defects.
Even microscopic voids or delaminations require part rejection because carbon composites tolerate zero defects. Unlike metals tolerating small cracks through ductility, carbon composites fail catastrophically once cracks initiate. That brittleness demands perfection during manufacturing. This technology emerged from 1960 space race. Thomas Edison experimented with carbon filaments in 1880s for light bulbs. But modern carbon fiber originated when British researcher William Watt developed pan-based process in 1963 at Royal Aircraft Establishment. The breakthrough enabled high-strength fibers commercially viable. Formula One adopted carbon fiber in 1981 when McLaren built the first composite monocoque chassis. Driver John Watson walked away from a 200-mile-per-hour crash at Monza, the carbon tub protecting him despite complete car disintegration. That demonstration convinced aerospace industry. Boeing's 787 Dreamliner, entering service in 2011, uses 50% composite materials by weight. Wings, fuselage sections, tail, slashing fuel consumption 20% versus aluminum equivalents. The B-2 Spirit stealth bomber, revealed in 1989, incorporates carbon composites extensively. The radar-transparent properties, combined with geometric shaping, create aircraft virtually invisible to detection. Today, carbon fiber production exceeds 120,000 tons annually, growing 15% yearly as industries discover applications from wind turbine blades to bicycle frames. Carbon emissions drop by 32% when using carbon fiber in aircraft versus aluminum. Lighter structures require less fuel over millions of flight miles. Industry saves over $68 billion annually through weight reduction in transportation. Wind turbines using carbon fiber blades generate 18% more electricity through longer, lighter blades, impossible with fiberglass. So here's the secret promised. Carbon fiber doesn't break, it delaminates. Unlike metal fracturing through crack propagation, carbon composites fail through layer separation. Impact damage creates barely visible surface dimples, hiding extensive internal delamination, why composites require ultrasonic inspection after any impact. That failure mode makes recycling challenging. You can't melt carbon fiber like aluminum. Heating destroys the crystalline structure that provides strength. Current recycling uses pyrolysis, heating composites to 1,000 degrees in oxygen-free environments, burning away resin while preserving fibers. Recovered fibers retain 70% of original strength, creating secondary markets. From plastic thread to aerospace revolution, cycle completes. Carbon fiber represents humanity's ability to reorganize matter at atomic level, creating materials nature never intended. We've learned to cook polymers in furnaces hotter than volcanoes, aligning carbon atoms into crystalline perfection, stronger than any metal, yet lighter than water. That thread, thinner than hair, doesn't just reduce weight. It enables impossible structures. Aircraft wings spanning 200 feet without internal support. Prosthetics stronger than bone. Spacecraft components surviving forces that pulverize steel. We've engineered the future, one microscopic fiber at a time.
Without nickel, Tesla's electric vehicles wouldn't exist. Every year, over 3 million tons of this silvery metal get extracted from Earth's crust, 70% destined for stainless steel, 30% powering the battery revolution transforming transportation. Picture this. Inside every electric car battery, nickel accounts for up to 80% of cathode weight, storing the electrical energy making 500-mile ranges possible. How does rock buried 2 miles underground become the metal enabling carbon-free futures? How do ancient asteroid impacts create deposits worth billions? Stick around till the end. You'll discover why this metal, discovered in 1751, became overnight the most critical resource for climate solutions, and the shocking environmental price we pay for every kilowatt-hour stored. The story begins in Sudbury, Canada, ground zero for one of Earth's largest meteorite impacts. 2 billion years ago, a 6-mile-wide asteroid slammed into primordial crust with force equaling 6 billion Hiroshima bombs. That cataclysmic collision melted rock 60 miles deep, concentrating nickel-rich magma into deposits mining companies extract today. Standing at crater's edge feels like visiting Earth's wound that never healed. Modern mining descends through vertical shafts, plunging 7,000 feet, deeper than 6 Empire State Buildings stacked vertically. Massive cage elevators, traveling at speeds exceeding 30 miles per hour, drop miners into darkness in under 4 minutes. That's falling through bedrock older than complex life itself. Underground, temperatures reach 120 degrees Fahrenheit from Earth's geothermal heat, requiring industrial air conditioning, pumping cold air through 40-mile tunnel networks. Next comes extraction, where explosive specialists drill blast holes following nickel-bearing veins. Charges containing ammonium nitrate, industrial explosive used in quantities measured by tons, fracture solid rock with controlled violence. The deafening thunder from underground blasts shakes surface buildings miles away, rattling windows in synchronized waves every afternoon at precisely 4 o'clock shift change. Giant load-haul dump machines, nicknamed LHDs, and standing tall as double-decker buses, scoop 50 tons per bucket. Picture mechanical mastodons navigating tunnels barely wider than their frames. Operating in perpetual darkness, illuminated only by headlamps, drivers maneuver 60-ton machines through labyrinths where wrong turns mean hours backtracking. Every shift, these machines transport 15,000 tons of ore, weight equivalent to 75 blue whales, through underground highways to crushing stations. Surface processing begins where jaw crushers, standing 4 stories tall with opening widths matching garage doors, pulverize boulders into gravel-sized with bone-rattling vibrations felt through steel-toed boots. Hydraulic jaws generate courses exceeding 15,000 pounds per square inch. Operators monitor crack propagation. Rocks splitting wrong create jams requiring dangerous manual intervention with jackhammers. Conveyor systems stretching 8 miles, longer than Central Park, transport crushed ore to grinding mills. Inside rotating drums 30 feet in diameter, 25-ton steel rods tumble with ore, creating grinding cacophony resembling continuous thunder. Processing 12,000 tons hourly, that's loading freight trains non-stop. This powder, finer than beach sand, flows to flotation cells, where chemicals separate nickel sulfides from waste rock using bubble physics. Nickel concentrate emerges containing 20% metal, ready for the real challenge: purification. Next comes roasting, a pyrometallurgical inferno where concentrate gets heated in massive kilns to 1,400 degrees Fahrenheit. At these temperatures, sulfur burns away as sulfur dioxide, leaving behind nickel oxide mixed with iron. Picture industrial-scale barbecuing where the meat is rock and smoke contains compounds requiring scrubbing before atmospheric release. The roasted material, now crumbly and porous like volcanic pumice, moves to smelting furnaces, where temperatures climb to 2,600 degrees Fahrenheit. Electric arc furnaces, consuming power equivalent to small cities, enough electricity to run 12,000 homes, melt oxide into liquid matte. This molten mixture, containing 60% nickel and 40% other metals, glows white-hot like captured starlight. Every 2 hours, furnaces tap this liquid fire into ladles holding 200 tons. The purification process intensifies with converting, where oxygen blasted through molten matte at supersonic speeds burns away remaining sulfur and iron. Massive Peirce-Smith converters, rotating horizontal cylinders 40 feet long, operate like blast furnaces lying sideways. Inside these rotating drums, chemical warfare occurs. Oxygen attacking sulfur bonds, creating temperatures hot enough to vaporize copper. This step is critical because timing determines purity. Blow too long, nickel oxidizes wastefully. Too short, impurities contaminate final product. Operators monitor color changes in flames shooting from converter mouths. Blue flames means sulfur burning, yellow indicates iron removal, clear white signals nickel ready. That visual chemistry, unchanged for centuries, guides decisions affecting millions in product value. After converting, nickel matte achieves 78% purity, but battery manufacturers demand 99.9%. After converting, the real magic begins, electro-refining. Here, physics and chemistry converge in massive electrode halls housing thousands of cells. Impure nickel anodes, cast into plates weighing 300 pounds each, suspend in electrolyte baths containing nickel sulfate and sulfuric acid. Electric current flowing through these baths, think industrial-scale electroplating, dissolves nickel atoms from anodes, transporting them through liquid to deposit on pure nickel starter cathodes. Picture this: over 10 days, nickel migrates atom by atom across 6-inch gaps. Impurities like cobalt, copper, iron stay behind, falling as sludge to cell bottoms. This sludge, later processed separately, contains precious metals including platinum, gold, palladium, making waste worth more than many ores. Temperature control matters critically. Too hot, dendrites form, metal crystals bridging electrodes causing shorts. Deposition slows uneconomically. Electro-refining requires surgical precision in industrial setting. Computer systems monitor voltage, amperage, temperature across 15,000 individual cells simultaneously. Operators adjust current by milliamps. Modern refineries achieve nickel purity of 99.99%, only one impurity atom per 10,000. That's purity rivaling semiconductor-grade silicon. After 10 days, workers crane lift finished cathodes, now coated with 400-pound nickel deposits from baths. Mechanical strippers peel nickel from starter sheets like removing wallpaper. These pure nickel sheets, called cathodes, get melted into pellets for battery manufacturers, or alloyed with chromium and iron for stainless steel. The energy intensity staggers. Producing 1 ton of battery-grade nickel consumes 50 megawatt-hours, enough electricity to power average American homes for 60 days. This industry transformed radically in 15 years. Back in 2010, nickel prices averaged $7 per pound, used primarily for stainless steel. Battery applications consumed less than 5% of global production. That all changed when Elon Musk's Master Plan 2 announced Tesla's battery gigafactories in 2016. The breakthrough came when battery chemistry shifted from cobalt-heavy NCAs to nickel-rich NCMs, nickel-cobalt-manganese cathodes containing 80% nickel. Suddenly, every electric vehicle needed 110 pounds of nickel. Global demand exploded. Prices spiked to $9 per pound by 2022. Indonesia, containing 21% of world's reserves, transformed from minor player to dominant producer. Today, battery applications consume 43% of new nickel production. By 2035, International Energy Agency projects batteries will consume 75%, driven by 200 million electric vehicles requiring 23 million tons cumulatively. Carbon emissions drop by 18% when recycling nickel versus mining virgin ore, equivalent to removing 3 million cars annually. Industry saves over $22 billion yearly through recycling. Processing costs drop 31% because smelting scrap requires half the energy of complete ore processing. So here's the secret promised. Nickel is humanity's transition metal, literally bridging fossil fuel era to electric future. But here's the dark truth. Extracting nickel for just one EV battery produces 8 tons of CO2 emissions. That electric car carries invisible environmental debt, requiring 35,000 miles of driving before breaking even with efficient gasoline vehicles. The green revolution isn't free. It's an energy trade-off where extraction today enables emission reductions tomorrow. From asteroid impacts to electric highways, cycle completes. We're mining ancient cosmic collisions to power climate solutions. Nickel doesn't solve pollution, it relocates it, concentrates it, transforms it into manageable problem. That's not failure, that's engineering reality. Every solution creates new challenges. The question isn't whether mining nickel harms Earth, it does. The question is whether preventing catastrophic climate change justifies temporary scars.
Per million, because even one microcrack can destroy a signal that's racing for thousands of miles at the speed of light. What is this magic? How does ordinary sand turn into transparent threads, thinner than a hair, but stronger than steel? Watch closely. At the end of this video, you'll learn a secret you've never heard before. To create a thread capable of transmitting light at a speed of over 186,000 miles per second, you have to start with sand. But not just any sand, only special, extremely pure quartz sand, where the main substance is silicon dioxide. For fiber optic production, sand with a silica content of over 99.9% is used, which means in 1 million parts, there's only 1 part of impurities. Imagine this. In every pound of raw material, no more than a few millionths of an ounce of impurities. And this is critical because even 1 billionth of an inch of foreign metal or organic matter can cause light scattering or absorption in the fiber optic cable. And then the signal, which was supposed to travel 60 miles without amplification, simply disappears. Raw material for fiber optic cable isn't just washed or filtered, it's purified at the molecular level. Manufacturers often use vapor phase chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and deposited as pure vapor. And only then is it converted back into glass. Add to this strict control of temperature, humidity, and air currents in clean rooms, and you'll get an idea of how far this is from an ordinary sandy beach. Production laboratories look more like National Aeronautics and Space Administration sterile zones than a glass workshop, and all for the sake of ensuring there's not a single defect in every yard of the future fiber. Because when you're transmitting light over thousands of miles, even one microscratch can cost you signal quality. A large, transparent glass cylinder that will later be melted and drawn into a very thin thread. This is the fiber optic preform. This huge glass rod is made using a method called vapor deposition. In a large furnace, air is mixed with very pure gases. These are different substances that turn into vapor when heated. These vapors hit the inner surface of a transparent tube, which is heated very intensely. When the vapors touch the hot wall of the tube, they deposit and turn into tiny droplets of glass, like dew collecting on leaves in the morning. Gradually, these droplets collect, layer by layer, until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it collapses into a dense solid rod, and this is our preform. The preform is placed in a special furnace that heats up very intensely. The temperature inside it reaches approximately 4,700 degrees Fahrenheit. This temperature is so high that the glass becomes soft and starts to melt, like caramel on a stove. When the end of the preform melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and a thin thread is formed from it. This thread, the optical fiber, is drawn at a speed of approximately 1,000 feet per minute. Imagine that. It's faster than a cyclist moving through the city. It's important for the thread to be of uniform thickness throughout its length. The thickness of an optical fiber is usually around 125 microns, or approximately 0.005 inches. That's very, very thin. For comparison, the average human hair is about 100 microns thick or less. To keep this diameter under control, special instruments are used during the process. They look at the thread in real time and measure its thickness. If the thread starts to become thicker or thinner, the system automatically changes the drawing speed or the furnace temperature to correct it. After the optical fiber has been drawn from the preform and has become a thin, transparent thread, it needs to be protected. The fiber is very thin and fragile. If left unprotected, it can easily break, cracks will appear, or dirt will get on it. Therefore, immediately after drawing, the fiber is coated with a special protective layer. A thin thread is pulled from the furnace. After the furnace, the thread immediately goes into a coating machine. This is a special device that clothes the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. It's like a small tube, or nozzle, inside which there's molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly applied to it. The polymer has very low viscosity, so that the coating is thin and even, but dense enough to protect the fiber. This coating layer usually consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks and allows the fiber to bend. The secondary coating is harder and more rigid, protecting against external influences, dust, and scratches. These two layers are applied sequentially, one after the other, to provide reliable protection. After applying the liquid coating, the coated fiber passes through special forming rollers. They regulate the thickness and evenness of the layer, pressing the coating uniformly along the entire length of the fiber. These rollers are very precisely calibrated so that the layer is not too thick or thin. After the polymer has been applied and shaped, the fiber passes through a zone of ultraviolet light. Here, the polymer instantly hardens under the influence of ultraviolet lamps. This is a process called polymerization. Anyone who gets their nails done knows how this happens. Ultraviolet lamps emit light of a specific wavelength that activates chemical reactions in the polymer. Thanks to this, the coating quickly becomes solid, while retaining its elasticity and ability to protect the fiber. This is a very fast process. The coating solidifies in fractions of a second, literally. This method does not heat the fiber, so it doesn't damage it. This provides very strong and durable protection. The entire machine is equipped with sensors and control systems. They constantly measure the coating thickness, fiber feed speed, and uniformity of application. If the coating layer is too thin, or there are defects, the system either stops the process or adjusts the parameters to avoid defects. At the end of all this technological magic, a spooling module, rotating with a hum resembling the sound of a jet engine, only in miniature. The fiber, like transparent silk, lies down smoothly and precisely, coil after coil. It shimmers in the light of the lamps, reflecting cold blue and white hues. The spool moves smoothly, to the left, then to the right, with millimeter precision, as if an artist is painting pictures with movement. One wrong angle, and everything will go haywire, so the system automatically adjusts the rotation speed and fiber tension with surgical precision. Around are sensors, lasers, cameras. They carefully ensure that the fiber lies flat, doesn't twist, and doesn't create tension. With every minute, more and more layers appear on the spool. Imagine, in a few hours, there are already several feet of thin, almost invisible fiber there. And all this, without a single break, without a single scratch. Because even a micro crack, and the light signal will get messed up, like a radio wave in a storm. Before cable assembly begins, the fiber from the spool is carefully wound onto a production line. Since one cable usually contains several fibers, individual threads are combined into ribbons or modules. For ribbons, the fibers are arranged parallel in a single plane, for example, 12 pieces, and glued together with a special resin. This makes them easier to work with during connection. For bundles, the fibers are twisted into a spiral strand and placed in a plastic tube. These ribbons or bundles are then placed into buffer tubes, thin, flexible plastic channels that provide space for the fiber's slight movements. This is important because when the cable's temperature changes or it's bent, the fiber slightly expands or contracts, and the buffer tube helps prevent it from being damaged. A gel that repels water and absorbs vibrations can also be added inside these tubes. Around the buffer tubes, strengthening elements are added. Fiberglass or Kevlar, very strong threads that protect the cable from stretching. Metal wire, for additional mechanical strength or grounding. A central strength member, a rigid element in the center that maintains the cable's shape. These reinforcements are needed so the cable can withstand tension, impacts, bending, and remain intact for decades. All of this is wrapped in an outer jacket. This is a dense plastic or polyethylene pipe, resistant to ultraviolet light, moisture, rodents, and temperature fluctuations. The cable is tested. The bandwidth of each fiber is checked, as is its bending strength and resistance to moisture. Then it's wound onto large drums, marked, and technical documents are added, and it's ready for transportation and installation. Imagine this. Every year, the world cranks out over 100 million tons of nuts and bolts, the invisible heroes of our industrial world. They hold together our bridges, our planes, our ships, and even our tallest skyscrapers. But few people know that behind every single one lies a process with precision down to 1,000th of an inch. We're talking metal cleaned in acid, forged under massive presses, hardened at over 2,000 degrees, and tested to its breaking point. So what makes an ordinary bolt strong enough to hold hundreds of tons? Stick around, and you'll learn the secret that turns a simple piece of steel into a part the whole world depends on. A high-volume nut and bolt plant isn't just a factory. It's a high-tech powerhouse where raw steel becomes the hardware that holds our world together. The whole thing is a complex, multi-stage marathon of machining, stamping, heat treating, and non-stop quality control. It all starts with the raw material. High-quality steel wire rod comes in, but it's dirty. First, it needs a serious cleaning to get rid of rust and scale. The most common way to do that? A chemical bath. We're talking a process called acid pickling, where the steel gets a dip in sulfuric or hydrochloric acid. This stuff eats away all the grime, leaving the metal surface perfectly clean and ready for what's next. After the acid bath, the wire is thoroughly rinsed with fresh water to get every last drop of acid off. Then it's dried. For an even deeper clean, some plants use sandblasting or mechanical grinding. You might even see a process called electrocleaning, which zaps the surface to level it out and boost its rust resistance. On the big production lines, they combine everything: mechanical scrubbing, a chemical dip, a rinse, and a dry. And they don't just eyeball it. Quality control uses visual checks and special instruments to make sure that surface is perfectly clean. Before it moves on, the metal gets a temporary rust preventive coating to keep it pristine during storage and handling. The main ways to make a bolt are cold forming and turning. Cold forming is the real workhorse here. That's where a machine takes the metal wire and shapes it under massive pressure, all without heat. The wire feeds through a series of dies that hammer it into the shape of a bolt. First, the round shank, then the head, usually a hex head so you can get a wrench on it. The beauty of cold forming is that it's incredibly precise, makes the steel stronger, and wastes almost no material. Once the head and body are formed, it's time for the threads. Here, they use a method called thread rolling. Instead of cutting the threads, the bolt blank is forced between special dies that literally press the threads into the metal. This process makes the threads incredibly strong and durable. Some of these high-speed lines can churn out hundreds of bolts a minute. For nuts, they often use hot forging. Steel blanks are heated up to a blistering 2,200 degrees Fahrenheit. That's about 1,200 Celsius, making the metal soft and pliable. Then, a press forges the iconic hex shape. After that, a hole is punched through the middle, and the internal threads are cut on special machines called tappers. Just like bolts, nuts go through heat treatment to make them tough and wear-resistant. Heat treating is where a bolt gets its backbone. It's a two-step process, quenching and tempering. First, in quenching, the bolts are heated up and then rapidly cooled. This makes the steel incredibly hard, but also brittle. So the next step is tempering. They're reheated to a lower temperature, which gets rid of the brittleness but keeps all that strength. This is how bolts get their specific grade or property class. After heat treating, every batch goes through brutal quality control. Sample bolts are checked for size, strength, thread accuracy, and any surface defects. We're talking micrometers, go-no-go gauges, and special optical sorters. Any parts that are out of spec are either rejected or sent back for reprocessing. To fight off rust, most bolts and nuts get a protective coating. This could be zinc plating, hot dip galvanizing, or special zinc flake coatings. This is what keeps them from rusting away, especially out in the elements. The finished products are then sorted by size and strength, boxed up, and prepped for shipping. Modern plants have automated lines cranking out hundreds of thousands of these a day. The parts travel on conveyors to automatic sorting machines that use optical sensors to check every last one. Anything that's damaged or not up to snuff gets kicked out. This makes sure only top quality hardware makes it to the packaging line. From there, the nuts and bolts go into automated bagging lines with inline scales and counters that measure out the exact quantity for each package. This could be small plastic bags, cardboard boxes, or bulk bins, depending on what the customer needs. The packages are labeled with all the key info: size, grade, manufacturer, and date. For big industrial orders, they're often packed in bulk bags or large containers to make shipping and storage easier. The whole process is automated to ensure the packaging is sealed tight to keep out moisture, dust, and prevent any damage in transit. Even though most of it is automated, there's still a human touch. For special kits or custom orders, workers will manually check the quality of the packaging, assemble the right mix of nuts and bolts, box them up, and get them ready to ship out. This flexibility allows them to meet specific customer needs with pinpoint accuracy. After packaging, the products go through one last check to make sure the labels are right and the packages are sealed. Then, they're sorted in the warehouse by order and prepped for dispatch. And it's not just standard stuff. Many plants also make custom fasteners based on a customer's specific blueprints, which is crucial for specialized industries like aerospace, automotive, or heavy construction. The global market for fasteners is on a steady climb, and it's all driven by a few key things. First up, construction. As countries spend more on infrastructure, we're talking bridges, roads, and new buildings, the demand for these steel connectors goes through the roof. Second, the automotive and machinery industries. Every car, truck, and piece of factory equipment is held together by hundreds of high-quality fasteners. As those industries grow, so does the need for top-grade nuts and bolts. For example, in Europe, car production is expected to climb, which directly boosts the demand for metal products, including fasteners. At the same time, the steel industry itself is getting smarter, using digital tech and automation to produce better, more specialized products. Of course, the cost of raw materials like iron ore and energy can affect things. But at the end of the day, as long as we're building, driving, and manufacturing, the demand for nuts and bolts isn't going anywhere. Every hour, over 1 billion square feet of glass are produced worldwide. but only one of them has clothed a giant that pierced the sky. Imagine a building taller than 3 Eiffel Towers, covered in glass with an area equal to 5 football fields. This is the Burj Khalifa, a symbol of human ambition. But what if I told you that it all started with sand, and a secret recipe that is still kept under wraps? Watch until the end, because something will be revealed that you've never heard of before. A property that turns glass into a source of life in the very heart of the desert. Imagine this. Dubai, a city that grew out of the desert, decides to surprise the world. Sheikh Mohammed bin Rashid Al Maktoum, the ruler of Dubai, sought to transform his country into a global tourist destination and reduce its dependence on oil revenues. And so, among ambitious projects, the idea of building a tower taller than anything humanity had ever seen was born. Construction began in 2004, and on January 4th, 2010, the world held its breath as the Burj Khalifa, originally named Burj Dubai, officially opened its doors. The height? A staggering 2,717 feet. That's almost 3 Eiffel Towers stacked on top of each other. 163 floors piercing the sky. The cost of this giant, about $1.5 billion. And now let's get to the main point. It's glass attire. How do you dress such a colossal structure? After all, the exterior surface of the Burj Khalifa is covered with glass and metal, and the area of this glazing is, imagine this, equal to the area of 5 football fields, or, to be more precise, about 1,528,000 square feet. That's an incredible number, and each panel had to be not just beautiful, but also functional. Have you ever wondered what it's like to live and work behind glass in a place where the air temperature can reach 122 degrees Fahrenheit? It's a real challenge. Therefore, the architects and engineers from the American company Skidmore, Owings and Merrill faced an incredibly difficult task. They had to create glass panels that would protect from the scorching sun and unbearable heat, yet allow enough light to pass through, and offer incredible views of the Persian Gulf. This is a true engineering feat. So, how did they do it? Each glass panel of the Burj Khalifa is a complex multi-layered sandwich. The outer layer is glass-coated with a thin layer of metal. This coating reflects the sun's rays, preventing them from heating the interior. The next layer is an air gap, which serves as additional thermal insulation. And finally, the inner layer is strong laminated glass for safety. Imagine how well thought out every detail had to be. The production process of these panels is a story in itself. The glass for the tower was manufactured at specialized factories, particularly in Syria. Each panel underwent strict quality control. It was tested for strength, resistance to temperature fluctuations, and wind loads. And the winds up there, at that height, can be quite strong. Engineers developed a special window frame design capable of withstanding the extreme weather conditions of the desert. So, how does the creation of one of the more than 26,000 glass panels for the Burj Khalifa begin? It all starts with fire and sand. At the core of everything is ordinary quartz sand of the highest quality, soda ash, and limestone. But don't think it's that simple. The proportions of these components are a trade secret, the first step towards creating super strong and functional glass. This mixture is loaded into a giant melting furnace, the size of a small house. The temperature inside? Over 2,700 degrees Fahrenheit. It's a real inferno, where the loose mixture turns into a red-hot, viscous, dazzlingly orange lava. And then, one of the most spectacular stages begins. The float glass process. The molten glass mass is continuously poured from the furnace onto a perfectly flat surface of molten tin. Yes, you heard that right. A huge bath filled with liquid, silvery metal. The glass, being lighter than tin, spreads over its surface like oil on water, forming a perfectly smooth, impeccably flat sheet of a given thickness. No distortions, no defects. It's like a fiery river, slowly flowing and solidifying. Then this endless glass ribbon enters a long tunnel for controlled cooling, or annealing. This is a critically important stage. If the glass cools too quickly, internal stress will simply shatter it into pieces. Therefore, over a few hundred feet, the temperature gradually and very slowly decreases. This relieves the stress and makes the glass stable. Now we have a giant sheet of transparent glass. But for the Burj Khalifa, this is not enough. It's time to give it superpowers. The panels are sent to vacuum chambers for the application of a special coating. This is the heart of the technology. In an almost complete vacuum, using a process called magnetron sputtering, the thinnest layers of metals, most often silver, are applied to the surface of the glass. Layer by layer, atom by atom. The thickness of these layers is measured in nanometers. It's thousands of times thinner than a human hair. It is this coating, invisible to the eye, that will reflect solar radiation and ultraviolet rays, protecting the tower's interior from the desert heat. Incredible, isn't it? But the glass must also be safe. Therefore, it undergoes a tempering process. The glass sheets are heated again to a temperature of about 1,150 degrees Fahrenheit, almost to the softening point, and then sharply cooled with powerful streams of cold air. This thermal shock creates incredible internal stress. The surface is compressed, while the inner layers remain in a state of tension. As a result, the glass becomes 5 times stronger than ordinary glass. If such a panel does break, it will shatter into thousands of small, safe crumbs without sharp edges. And that's not all. Remember the sandwich? Now it's time to assemble it. They take 2 sheets of glass, one tempered with a solar control coating, which will be the outer layer, and one simply tempered or laminated, which will be the inner layer. A special spacer frame is installed between them, creating a hermetically sealed air gap. This air gap is a key element of thermal insulation. This entire structure, called an insulated glass unit, is sealed around the perimeter. That's it! A high-tech panel, ready to withstand winds, heat, and time, has been created. Each such panel undergoes dozens of quality checks. Lasers scan it for the slightest scratches, sensors check for airtightness and coating quality. Only after this does it get a one-way ticket to Dubai, to become part of the sparkling mosaic on the body of the giant. And now imagine the installation. How do you lift and install thousands of these heavy glass panels at a height of hundreds of feet? It was a real choreography on the construction site, where 12,000 workers from different parts of the world worked simultaneously. In total, 22 million man-hours were spent on the construction of the tower. Special cranes lifted the panels to the required floor, and then a team of highly skilled installers, like mountaineers, secured them to the facade. It was a job that required incredible precision, courage, and coordinated actions. An error at such a height is simply unacceptable. And so, panel by panel, the tower was dressed in its sparkling glass attire. Each element was part of a giant puzzle, perfectly fitted to its neighbor. And the shape of the building? It's not accidental. Architect Adrian Smith was inspired by the shape of the desert flower Hymenacalis, which grows in the region. The Y-shaped floor plan not only maximizes views, but also ensures the stability of the structure. And did you know that the glass of the Burj Khalifa has another amazing property? It collects condensate. In the hot and humid climate of Dubai, this is a real lifesaver. The condensate collection system gathers the moisture that forms on the glass panels and directs it to a special reservoir. This water is then used to irrigate the plants on the complex's territory. Imagine, about 15 million gallons of water a year are collected this way. That's a whole lake. The story of the Burj Khalifa is not just a story about the construction of the tallest tower. It's a tale of human ambition, of the courage to dream and bring those dreams to life. It's a story of how an oasis of technology and innovation can be built in the middle of the desert. Every glass panel that glitters in the sun is a testament to the incredible work of thousands of people who contributed their efforts to create this architectural marvel. So the next time you see photos or videos of the Burj Khalifa, remember this incredible story about how molten sand gives birth to glass, how it is transformed into high-tech panels, and how these panels, one by one, create a sparkling facade that has conquered the sky. It's truly impressive, isn't it? It's a story that inspires and proves, for human genius, nothing is impossible. The largest gasoline production plant in the United States is Marathon Petroleum's facility in Galveston Bay, Texas. It's a true giant, processing 631,000 barrels of crude oil every day. That's about 26.5 million gallons every single day, a staggering number. Let's dive into the atmosphere of oil refining production. It all began long before the era of hybrids, electric cars, and climate summits. Back in the days when America was still smoking and roaring, the world needed fuel, and Texas provided it by the spoonful. On the coast of the Gulf of Mexico, in the Texas city of Texas City, a decision was made back in 1931 to build a plant that would refine oil into liquids that make cars and airplanes roar. By 1933, the plant was operational. At that time, it belonged to Republic Oil, and a little later, it was taken over by Amoco, which eventually became part of British Petroleum. Those were wild times. Every day, a new record. Gallons of gasoline flowed like a river, and the plant gradually expanded. It survived World War II, the oil crises of the 70s, and even an explosion in 2005 when 15 workers died at a neighboring facility, a tragedy that forced a complete overhaul of safety in the entire oil refining region. Have you heard about it? And so, in 2013, the giant changes hands. Marathon Petroleum Corporation buys the plant. And they don't just buy it, they integrate it with their own refinery located nearby. Thus, a single gigantic system is born, the Galveston Bay Refinery, which since then has been processing over 630,000 barrels of crude oil every day. To imagine the scale, that's over 26 million gallons of fuel per day, and the complex covers nearly 1,000 acres. Over 1,500 people work there, not counting contractors and specialists who service the units. It's like a small industrial city, only instead of coffee shops, there are reactors instead of fountains, cooling towers, and instead of a park, thousands of pipelines. Galveston Bay is the pulse of the U.S. fuel infrastructure. It operates 24 hours a day, 7 days a week, without stops or breaks. It's not just gasoline that's born here, they also produce jet fuel, diesel, fuel oil, petroleum coke, and even propylene for the chemical industry. Everything that can flow, burn, and work is squeezed out of every drop of crude oil. Interestingly, the plant's location is strategic. The nearby port allows for receiving tankers from all over the world and a network of pipelines and railways for sending products all over America. Roughly speaking, if you're filling up your tank somewhere in the US, there's a chance that at least a drop of that fuel passed through the furnaces of Galveston Bay. And although the world is changing today, and green energy is being talked about from every microphone, the Galveston Bay Refinery is not giving up its position. Marathon Petroleum is investing hundreds of millions of dollars in modernization, filtration, and reducing harmful emissions. Because as long as the planet is still roaring with engines, this Texas giant remains at the heart of the American highway. We are heading to a territory where it doesn't smell of flowers, but where pipes roar, signal lights flash, and black gold is turned into gasoline. Galveston Bay Refinery, one of the largest plants in the US, and production there begins not with the push of a start button, but with thousands of miles of logistics, pressure, and thermal alchemy. The first drop of oil in this story doesn't yet have the smell of gasoline. It's in its raw form, viscous, dark, with impurities, water, sulfur, and metals. It's delivered by tankers through the port of Texas City, or pumped through pipelines that stretch for thousands of kilometers. This plant can receive over 1 million barrels of crude oil per week. That's an insane amount. The oil goes into huge tanks, so-called crude tanks. Each such tank can hold 500,000 barrels. Imagine that, that's more than 20 million gallons. Here it is stored for several days, where it settles and is heated to a temperature of about 140 degrees Fahrenheit to reduce viscosity and facilitate pumping. Next, the oil goes through desalters. These are special units that remove water, salts, and mechanical impurities. Because salts are death to metal reactors, they cause corrosion and form dangerous deposits. Here, the oil is mixed with fresh water and electrical energy, creating an emulsion that forces the impurities to separate. This is, essentially, industrial cleaning. After this, the main stage, the atmospheric distillation unit. A tower 230 feet high, where oil heated to 650 degrees Fahrenheit is fed in, and vapors rise to the top. And here the magic begins. Heavy fractions like diesel, kerosene, and fuel oil settle at the bottom, while lighter ones, the gasoline fraction, naphtha for petrochemicals, rise to the top. You can imagine this tower as an oil elevator, where each floor is a separate product. The temperature in the column plays a key role. At each height, its own condensation point. Heavy components stop faster, light ones fly further. All this works in real time with control over every degree and every drop. But no, this isn't gasoline yet. What has been collected are raw fractions that are then sent to other units. Vacuum distillation, catalytic cracking, hydrotreating, and only then to blending. That is, mixing to meet the standards for gasoline, diesel, and jet fuel. By the way, gasoline itself is not a single component, but a mixture of dozens of fractions that are chemically and physically stitched together into a precisely calibrated formula, with an octane number, ignition temperature, volatility, aromatics, all according to standard. But let's go back. After the atmospheric tower, many heavy fractions are sent to a vacuum column, where they are distilled under reduced pressure, so as not to burn them to a crisp. From there come components for lubricants, bitumen, and even raw material for plastics. Then even deeper, catalytic cracking, where molecules are literally broken into smaller ones, turning heavy fuel oil into light gasoline. And only when this black magic is complete does the collection of fractions, mixing, adding additives begin, and at the end, storage tanks with the finished product, which again await tankers, pipelines, and rail cars. After all the formidable reactors, furnaces, and towers, where crude oil has been given a good heating, the crucial stage arrives: final blending. This is no longer a turbulent boiling or flowing in pipes. It's like a chemical kitchen, where a complex dish with a taste of power and precision is prepared from a few simple ingredients. Each fraction obtained from previous processes has its own properties. One is light, volatile, with a low octane number. Another is heavier, dense, resistant to temperatures and pressure. From these, like from puzzle pieces, petrochemical technologists assemble the required mixture. This is called blending. And this is the moment when gasoline essentially is born. It is not mixed randomly. Everything happens according to precisely calculated formulas. The fractions are fed into mixing tanks, where every drop is controlled by automation. Machines know exactly how much of what to supply to get the desired grade of gasoline at the output, with a certain octane number, resistance to detonation, and stability during storage. But even the most precise mixing is not the end. Special additives are added to the gasoline composition. These are small in volume, but powerful in effect substances. It is they that help the fuel work better, not destroy engines, not rust in tanks, not evaporate too quickly, not clog injectors, not pollute the atmosphere. Additives are introduced in microscopic doses, literally a few ounces per gallon, but modern fuel is impossible without them. When everything is ready, the gasoline goes into finishing tanks. These are giant steel containers located next to railway lines, truck ramps, and port pipelines. There, the fuel can be stored for days or weeks, waiting for its time. Then, shipment, tankers, rail cars, barges. And so, the fuel hits the road. Maybe this very batch of gasoline will be hissing in the tank of your car in a few days. Maybe it will power a combine, a truck, a boat, or an airplane. But whatever the case, this gasoline has come a long way. From dark, raw mud to perfect, transparent fuel. It is clean, stable, ready to burn, but only when you say, "Start your engine." Every year, the world lays down over 1 billion tons of asphalt, the material that modern civilization would literally grind to a halt without. But few people know that every foot of road is the result of a complex alchemy of stone, fire, and oil. It all starts with an explosion in a quarry and ends with a hot, black mass steaming under the wheels of a roller. In this video, you'll see how asphalt is born, from blasting rock to the final roller that polishes a new road. And if you stick around to the end, you'll learn a secret that most drivers don't even know exists. Almost nothing goes to waste. That crushed old asphalt is then added to the new mix back at the plant. On average, new asphalt laid on our roads contains about 22% recycled material. The payoff here is huge, both economically and for the environment. First, it drastically cuts down on the need to quarry new stone and produce new bitumen, which saves natural resources and energy. Second, it makes the final product cheaper, saving billions of dollars from road maintenance budgets. So, every car trip you take is a journey on a complex piece of engineering that not only withstands massive loads, but is also a prime example of an industrial ecosystem where the old is constantly reborn into the new, closing the loop and making the country's infrastructure a little more sustainable. The story of asphalt doesn't start on the road. It starts in two completely different places. The first is a quarry. It's a massive wound on the face of the earth where rock is blasted out. It all begins with a loud explosion that shakes the ground for miles. Huge boulders break away from the rock face. Then, giant haul trucks with wheels taller than a person move in and haul these stone boulders to the primary crusher. This is a metal monster that crushes massive boulders into smaller chunks with its steel jaws and incredible force. But that's just the beginning. The stone then goes through a whole series of crushers and screens, giant vibrating sieves. The goal isn't just to crush the rock, but to carefully sort it by size. The result is entire mountains of clean, sorted stone, which we call aggregate. You've got everything here, from large, fist-sized rocks to fine crumbs and even dust, like sand. Each size is stored in its own separate pile. It's like in your kitchen, where you have flour, sugar, and salt, each ingredient separate, waiting for its turn. This is the skeleton of the future asphalt, making up 95% of its mass. The second place where asphalt is born is an oil refinery. When crude oil is processed into gasoline, diesel, jet fuel, and other light products, a thick, black, viscous substance is left at the very bottom of the distillation tower. This is bitumen. In its normal state, at room temperature, it's as hard as a rock. You can shatter it with a hammer. But if you heat it up, it becomes a liquid, like thick syrup. It's this property, being solid when cold and liquid when hot, that makes it the perfect glue for our stone skeleton. Bitumen is the soul of asphalt. It's black heart that holds everything together. Now, let's head over to the asphalt plant. This is where all the ingredients come together. From a distance, it looks like a complex tangled metal jungle. Tall silos, endless conveyor belts, pipes, tanks, and a central tower with smoke rising from it. It's a real factory that works like a single, well-oiled machine. Different sizes of aggregate are fed from separate bins onto a conveyor belt. But not just randomly. The whole process is controlled by a computer. An operator in a control booth inputs the exact recipe for the asphalt. Depending on where it's going to be used, a busy highway or a quiet side street, the recipe will be different. The computer knows exactly what percentage of large stone, medium, small, and dust is needed for the perfect mix. It's like baking a complex cake, where every gram counts. This mix of stones begins its journey up a long, inclined conveyor and enters the heart of the plant, the drying drum. This is a huge, long tube that slowly rotates, set at a slight angle. From one end, a powerful burner blasts a roaring pillar of fire inside, like a jet engine. The temperature inside hits 300 degrees Fahrenheit. The stone, slowly tumbling inside this drum, heats up, and most importantly, gets completely dried out. Moisture is the #1 enemy of good asphalt. Even a single drop of water can prevent the bitumen from sticking properly to the stone's surface. So, the stone has to be bone dry. After the drying drum, the hot, moisture-free stone is carried up by an elevator to the very top of the central tower. There, it passes through another set of screens for a final quality check on the sorting, and then falls into hot storage bins. Meanwhile, in special insulated tanks, our black glue, the bitumen, is being heated up. It's also brought to a high temperature to make it fluid and runny. And now comes the climax. The computer gives another command. A weighhopper, with incredible accuracy, measures out the required amount of hot stone of each size from the different bins. Then, a precisely measured amount of hot liquid bitumen is sprayed into this superheated stone mix. This entire mass, stone and bitumen, is dropped into a mixing chamber, called a pug mill. It's like a giant kitchen mixer, but instead of whisks, it has 2 powerful shafts with metal paddles. These paddles churn the hot mass with enormous force, and in less than a minute, every single stone, every grain of sand, is coated in a thin, shiny film of black bitumen. Out of the chamber comes the finished asphalt, a uniform, steaming black mass with a characteristic oily smell. Now this hot, freshly made product needs to be stored until it's shipped out. It's lifted and dumped into special insulated storage silos. They're like giant thermoses that can keep the asphalt hot for many hours, sometimes even days. Dump trucks pull up under these silos. With a loud clang, a gate opens and several tons of hot asphalt pour into the truck's bed with a roar and a cloud of steam. The bed is always covered with a tarp to keep that precious heat in during transport to the paving site. At the construction site, the final act begins. The dump truck slowly unloads the hot mix into the hopper of a special machine, an asphalt paver. This machine, moving forward slowly, evenly spreads the asphalt over the road surface, forming a perfectly level layer of a specific thickness. At the back of the paver is a heavy, heated plate called a screed. It does the initial compaction and gives the surface its first pass of smoothness, but the asphalt is still soft and loose. To make it strong, it needs to be compacted. Right behind the paver follows a whole team of heavy road rollers. First come the large steel drum rollers, which use their immense pressure to squeeze the air out of the asphalt mix and force the stones to lock together tightly. Then, pneumatic tire rollers might be used, which knead the surface, making it even denser. And in the final stage, smooth steel drum rollers pass over it again to give the road its final, smooth finish. As the asphalt cools, the bitumen turns from a liquid back into a solid. It permanently glues all the stones together, turning the loose mix into a strong, waterproof monolith. After a few hours, the road that was recently hot and soft becomes hard and ready for traffic. And that's the whole point. From the explosion in the quarry to the heavy roller on the road, every stage of this process is designed to create a durable, reliable surface that will withstand thousands of cars every single day. Imagine a metal that's lighter than steel, stronger than aluminium, and can withstand temperatures at which other materials simply burn up. A metal used to build aircraft that conquer space and implants that serve people for a lifetime. Sounds like science fiction? But this is titanium, one of the most mysterious metals on Earth. It starts with tiny grains of ilmenite and rutile and ends up as parts for supersonic jets and spacecraft. But few people know. Behind the gleam of titanium lies a manufacturing secret so dangerous and energy intensive, that it's rarely spoken of. If you watch till the end, you'll learn something that will forever change your perception of this metal. The story of titanium production begins in the late 18th century when, in 1791, a British clergyman and amateur mineralogist named William Gregor discovered a new metal in the mineral ilmenite, which is now the main source of titanium. Initially, this metal was called menaconite, but later, in 1795, the German chemist Martin Klaproth rediscovered the element in the mineral rutile and named it titanium, in honor of the mythical Titans, giants of ancient Greek mythology. However, the pure metal was first successfully isolated only in 1825 by the Swedish chemist Berzelius, though at that time it was contaminated with impurities and practically unsuitable for industrial use. The first attempts at industrial production of titanium began only in the 20th century. In 1910, the American chemist Matthew Hunter obtained a small amount of pure titanium, and the real breakthrough came in 1925 when Dutch scientists Van Arkel and de Boer developed a method for producing high-purity titanium, paving the way for its widespread application. From the mid-20th century, titanium production developed intensively, especially in the USA, where the metal became indispensable in aviation, the space industry, and military applications. The production of titanium starts with the mining of titanium-bearing raw materials, mainly the minerals ilmenite and rutile, which contain titanium oxides. These ores are found in placer or lode deposits and are widespread across the globe, particularly in Australia, Canada, China, Norway, and South Africa. After mining, the ore undergoes a complex multi-stage processing. First, it is enriched, separating the titanium minerals from the waste rock to obtain ilmenite or rutile concentrates. Then, the concentrates are subjected to chlorination, which results in the formation of titanium tetrachloride, a volatile substance that is purified by distillation. This process allows for the removal of impurities and the production of a high-purity intermediate product. Next, the titanium tetrachloride is reduced with magnesium or sodium in special reactors at high temperatures in an inert atmosphere, producing titanium sponge, a porous metallic powder. This titanium sponge is then pressed, melted, and cast to obtain ingots or billets for further processing. The production of titanium is energy-intensive and expensive due to the complexity of the technological processes and the need to work in high-purity conditions. The main industrial method for producing titanium is the Kroll process, which remains the global standard. It involves the chlorination of titanium ore, purification of titanium tetrachloride, and its reduction with a metal, allowing for the production of high-quality metal for aviation, space technology, medicine, and other industries. Thus, titanium production begins with the mining of ilmenite and rutile, goes through complex chemical reactions and physical processing to transform natural minerals into a high-tech metal that combines lightness, strength, and corrosion resistance. The initial stages of titanium production are based on a complex, multi-step technological process that begins with the extraction and preparation of titanium-bearing raw materials, mainly ilmenite and rutile. These minerals contain titanium oxides, which must be converted into chemically pure titanium tetrachloride. To do this, the titanium ore concentrates are chlorinated in fluidized bed reactors at a temperature of 1,800 degrees Fahrenheit, where carbon and chlorine gas react with the raw material to form titanium and carbon monoxide. This tetrachloride contains impurities of other metals, which are removed by distillation to obtain high-purity technical titanium. The next key stage is the reduction of titanium tetrachloride to metallic titanium. The most common industrial method is the Kroll process, in which titanium tetrachloride reacts with magnesium in a vacuum chamber at high temperature. The result is titanium sponge, a porous metallic powder containing impurities of magnesium and magnesium chlorides. This reaction mass is subjected to vacuum distillation to remove impurities, after which the titanium sponge is pressed and remelted into solid ingots or slabs. The resulting titanium ingots are then used to produce alloys, rolled products, sheets, and complex parts. The entire process requires strict control of purity, temperature regimes, and safety, as titanium actively reacts with oxygen and nitrogen when heated. Just look at how incredible it is. A porous, light, and seemingly fluffy mass of metal. This is titanium sponge. It looks nothing like a regular metal bar, but more like a piece of metallic sponge or foam, only made of titanium. But this fluffy material is the first step towards creating strong and reliable titanium ingots, which are then used in aviation, medicine, and other high-tech industries. First and foremost, titanium ingots can be used to create titanium alloys, mixtures of titanium with other metals that enhance its properties. To obtain an alloy, alloying elements are added to the molten titanium, most often aluminium, vanadium, molybdenum, iron, or niobium. These additives change the metal's structure, increasing its strength, heat resistance, corrosion resistance, and improving its workability. The production of alloys usually takes place in vacuum arc furnaces, where the metal is melted at high temperatures in a protective atmosphere to avoid oxidation. To achieve a homogeneous composition, the alloy is remelted several times, after which it is cooled and prepared for further processing. The next stage is rolling. Ingots or slabs of titanium and titanium alloys are heated to a certain temperature to make the metal more malleable and are passed through special rollers. Rolling allows for reducing the metal's thickness, giving it the desired shape and size, as well as improving its structure and mechanical properties. The result is various types of rolled products: strips, ribbons, wire, and bars. Rolling can be hot or cold, depending on the requirements for the final product. From these rolled products, sheet metal is made. Thin, flat blanks that are widely used in construction, aviation, medicine, and other industries. Titanium sheets are distinguished by their high strength and corrosion resistance, and are also easily subjected to further processing, cutting, bending, and stamping. The production of sheets requires precise control of thickness and surface quality, so after rolling, they are often subjected to additional processing, such as polishing or anodizing. To create complex parts, various methods of processing titanium and its alloys are used. These can include mechanical milling, turning, grinding, as well as modern technologies such as additive manufacturing using laser powder bed fusion. Additive technologies allow for the creation of parts with complex geometries that are impossible to produce with traditional methods. This is especially important for the aviation and medical industries, where lightweight, strong, and precise components are required. Furthermore, to enhance their performance characteristics, titanium products can undergo heat treatment, annealing, quenching, or aging. These processes change the internal structure of the metal, improving its strength, hardness, and fatigue resistance. In aviation, titanium is used for 15% of the weight of a modern passenger aircraft, significantly reducing its overall weight and increasing fuel efficiency. In the medical field, about 70% of implants, such as artificial joints and dental prostheses, are made from titanium or its alloys due to their biocompatibility and durability.
More than half of Earth's entire weight is iron, 32% of the planet's mass. Earth's core is a gigantic ball of molten iron the size of the moon. But iron rules on the surface too. Every second, humanity produces 60 tons of steel, 2 billion tons per year. That's more than all other metals combined. 95% of all metal used by civilization is iron and steel. Without iron, there'd be no skyscrapers, bridges, ships, cars, or trains. How do fiery rivers of molten metal at 3,600 degrees emerge from red ore in city-sized quarries? You'll see explosions in quarries, blast furnaces as tall as 30-story buildings, converters where oxygen turns pig iron into steel in minutes, and rolling mills where 1,000-ton slabs get rolled into paper-thin sheets. Watch to the end. The finale shows why iron holds the world together. This is the story of the metal that built civilization. The Lebedensky Quarry in Russia is one of the planet's largest iron ore quarries. Depth, nearly 2,000 feet. Width, 3 miles. From the edge, you can't see the bottom. A gigantic wound in the earth from which 100,000 tons of iron ore are extracted daily. Excavators as tall as 10-story buildings scoop rock with buckets holding 1,800 cubic feet. One bucket is like a small house. Dump trucks with 360-ton capacity haul ore up the spiral road. Wheels taller than a person. But before loading the ore, it needs to be blasted. Drilling rigs create holes 65 feet deep. Tons of ammonium nitrate explosive are packed into these holes. The explosion? Earth trembles. A wall of rock tall as a skyscraper crashes down. A dust cloud rises 3,000 feet. After the dust settles, excavators begin work. The ore is reddish-brown, sometimes almost black. Magnetite and hematite, iron oxides. Iron content ranges from 30 to 60%. The rest is waste rock. The ore goes to a processing plant. Massive cone crushers grind bus-sized chunks. The noise can be heard for miles. Ore gets crushed to fist size, then to gravel, then smaller. It enters ball mills, steel drums 20 feet in diameter, 33 feet long. Inside are hundreds of tons of steel balls. The drum rotates, balls drop, grinding ore into fine powder. After 8 hours of grinding, you get reddish-brown dust. It's mixed with water, creating pulp, liquid slurry. This slurry passes through magnetic separators. Magnetite sticks to magnetic drums. Waste rock washes away. The concentrate contains 65 to 70% iron. From this, they make pellets, granules the size of walnuts. Wet concentrate gets rolled into balls on special drums, then fired at 2,400 degrees Fahrenheit. Pellets harden, becoming rock solid. These pellets are raw material for blast furnaces. Each plant produces millions of tons of pellets yearly. They're loaded onto trains and shipped to steel mills. A blast furnace is a steel tower 330 feet tall, 46 feet in diameter, 30 stories of pure metal and fire, lined inside with 3-foot-thick fireproof brick. Internal volume, 176,000 cubic feet. Iron ore pellets, coke, and fluxes like limestone or dolomite are loaded from the top, in layers, like a layered cake, several hundred tons at a time. From below, through tuyères, openings in the walls, hot air is blown in. Air temperature, 2,200 degrees Fahrenheit. Pressure, 4 atmospheres. Coke ignites. Temperature in the furnace's lower section reaches 3,600 degrees Fahrenheit. Pellets slowly descend, heating up. Different reactions occur at different heights. First, moisture leaves the ore. Then, at 930 degrees, iron oxide reduction begins. Carbon from coke strips away oxygen. At 1800 degrees, ore becomes spongy iron. At 2700 degrees, iron melts. Drops of molten metal flow down. At the furnace bottom, molten pig iron accumulates, an iron alloy with 4% carbon. Pig iron temperature at the furnace bottom is 2,700 degrees Fahrenheit. It glows blindingly white with an orange tint. Pig iron is denser than slag, so it stays at the bottom. Slag, molten impurities and fluxes, floats on top. Every 4 hours, they open the tap hole, an opening in the furnace's sidewall. Pig iron tapping is a fire show. A stream of molten metal flows down channels. Sparks fly dozens of feet. The brightness requires dark glasses to watch. Pig iron flows into massive ladles on railroad cars. One ladle holds 300 tons. It's a locomotive made of molten metal. The ladle gets covered to prevent cooling and shipped to the steelmaking shop. One blast furnace operates continuously for years. Stopping is catastrophic. Metal would solidify inside. The furnace produces 10,000 tons of pig iron daily. That's like 100 railroad cars. Major steel mills have 10 to 15 blast furnaces. But pig iron isn't steel yet. It's brittle due to high carbon content. Steel is needed, an alloy with less than 2% carbon. Pig iron gets poured into a converter, a massive pear-shaped vessel 33 feet tall, lined with fireproof brick. It holds 350 tons of molten metal. The converter tilts, pig iron pours in, steel scrap is added for cooling. The converter returns to vertical position. An oxygen lance, a tube 20 inches in diameter, lowers from above. Oxygen flow begins. A jet of pure oxygen at 150 pounds per square inch pressure strikes the molten metal. Violent reaction begins. Oxygen oxidizes carbon, silicon, manganese, impurities in pig iron. These exothermic reactions release enormous heat. Temperature rockets to 3,200 degrees Fahrenheit. Metal boils and churns. Flame tongues several feet high shoot from the converter mouth. Sparks and molten drops fly everywhere. The blowing process takes 20 minutes. In this time, 350 tons of pig iron become steel. Carbon burns down to 1% or less. The converter tilts, steel pours into a ladle. The molten metal glows blindingly white at 2,900 degrees Fahrenheit. Alloying elements get added to the ladle. Manganese, chromium, nickel, molybdenum, depending on the steel grade needed. They mix it by blowing argon through. Then steel gets cast. There are two methods. First, continuous casting. Molten metal pours into a crystallizer, a water-cooled copper mold. Below, a solidifying blank emerges, a slab 8 inches thick, 6.5 feet wide. It glows red, surface temperature around 1,800 degrees Fahrenheit. Gas cutters slice the slab into 33-foot lengths. One slab weighs 25 tons. Second method, casting into ingot molds. Steel forms. This creates ingots up to 50 tons. These ingots and slabs are semi-finished products. They go to rolling mills. There begins the final transformation, turning thick blanks into thin sheets, rails, or beams. Slabs heat in reheating furnaces to 2,200 degrees Fahrenheit, red hot. Then they go to the rolling mill. It's a line of dozens of rolls, steel cylinders 3 feet in diameter weighing dozens of tons. Rolls rotate toward each other. The red-hot slab enters between rolls. They squeeze and roll it. The slab gets thinner and longer. It passes through the next pair of rolls, even thinner, dozens of times. An 8-inch thick slab becomes a sheet 1 to 2 millimeters thick. Length grows from 33 feet to over half a mile. Rolling speed on finishing mills reaches 50 miles per hour. Red-hot steel ribbon flies through the mill, sparks flying everywhere. Temperature drops to 1,400 degrees Fahrenheit, metal darkens. The strip cools with water, winds into giant coils weighing 20 to 30 tons. This is hot-rolled steel, the foundation for car bodies, appliance housings, building structures. Global steel production is 2 billion tons yearly. China produces over 1 billion tons, half the world's output. India, Japan, the US, Russia are other major producers. Steel is infrastructure's backbone. 95% of metal structures are steel, from skyscrapers to tin cans, from tankers to paper clips.
Iron and steel are civilization's skeleton.
Iron is the oldest metal after copper and bronze. The Iron Age began 3,000 years ago. First, iron came from meteorites, ready-made metal fallen from the sky. Egyptian pharaoh Tutankhamun was buried with a meteorite iron dagger. Smelting iron from ore was learned by Hittites in Asia Minor around 1200 BC. They kept the secret for centuries, but technology spread. Iron weapons were stronger than bronze. Iron plows worked soil better than wooden ones. Civilizations with iron defeated civilizations without iron. Medieval times, iron was made in small furnaces. The Industrial Revolution began with blast furnace invention in the 18th century. Early furnaces used charcoal. Later, they switched to coke from coal. The 19th century brought the converter process, rapid pig iron to steel conversion. Bessemer, Martin, Thomas, names that changed the world. The 20th century was steel century. Skyscrapers, bridges, ships, automobiles. Without steel, there'd be no modern world.
And so, traveling from explosions in 2,000-foot-deep quarries through giant crushers and magnetic separators, through 300-foot-tall blast furnaces at 3,600 degrees and converters where oxygen burns out carbon in 20 minutes, through rolling mills where 8-inch slabs become millimeter-thin sheets, steel emerges, the metal that built civilization. 2 billion tons per year, 60 tons every second. The metal everything around us is made from. Every skyscraper, every bridge, every car, every ship. It's iron, mined from red ore, remelted in fire, rolled into sheets. More than half of Earth's weight is iron. The planet's core is molten metal. And on the surface, iron rules. 95% of all metal is iron and steel. From nails to bridges, from paper clips to skyscrapers, iron holds the world together. Without iron, humanity would collapse back to the Stone Age. No machines, no electricity, no internet. Everything's built on iron. From fiery rivers of molten pig iron in blast furnaces to steel beams holding up skyscrapers, iron is the foundation, the base, civilization's skeleton. Metal of the gods that became metal of the masses. The most abundant, most important, most irreplaceable. Iron, the metal that holds the planet together.
Every year, over 4 million tons of steel wire rope are produced worldwide, and it's these thin, shining threads that hold up bridges, elevators, lifts, and ships. But what if I told you that before becoming a rope, every wire goes through real torture acid, flame, a press, and a tension capable of tearing steel apart? In this video, we'll show you how a piece of rough wire rod is born into a perfectly smooth metal thread, capable of withstanding thousands of tons of load. And at the end, you'll learn something that even the manufacturers themselves keep hidden. To create a steel cable capable of holding up a bridge hundreds of feet long, it all starts with the right alloy. Most often, it's carbon steel with a carbon content of around 0.6%, which provides both strength and elasticity. Sometimes chromium, nickel, or molybdenum are added for corrosion resistance and increased load capacity, especially for cables that need to work outdoors for decades. The metal is delivered to the factory in the form of huge steel slabs plates measuring 10 by 2 by half a foot and weighing up to 10 tons. They are heated in furnaces to 2,200 degrees Fahrenheit until the steel becomes plastic, almost like rubber. Then these red-hot billets are passed through rolling mills, turning them into long, thin rods with a diameter of approximately 0.25 inches. These are called wire rods. These wire rods are then cooled under controlled conditions. either in air or in special baths, so that the metal structure is dense and the internal stress is uniform. Next, a short storage stage. The metal is weighed, checked for hardness, flexibility, and the presence of microcracks. Only after this is each coil sent to the main section wire drawing, from which the future cables will be formed. After the steel wire rods have been cooled and checked for quality, they proceed to the wire drawing workshop. This process transforms the thick rods into thin but incredibly strong wire, which will become the foundation for bridge cables. Imagine a steel rod as thick as your finger, just off the billet. Its surface is rough, as if covered in a layer of sand or rust. This is scale a hard and brittle crust that appears during hot rolling. To prevent it from interfering with further metal processing, it needs to be removed. To do this, the wire rod is first lowered into a bath of acid solution, usually sulfuric or hydrochloric acid. In this solution, the scale seems to flake off the metal, just like old paint peels off after being treated with solvent. Then the wire is rinsed with a large amount of water under pressure to wash away all traces of acid and dirt. To the touch after this, the metal becomes smooth and cool, like a freshly polished stone. But that's not enough. Next, the wire goes through degreasing. It's submerged in special alkaline solutions that remove any oils that might have gotten onto the surface. And only then is the clean, smooth wire, shiny and dry, ready for the next stage drawing. Now the wire needs to be pulled through a hole smaller than the wire itself to stretch it out and make it thinner, but a thick end simply won't fit through. So, it's first sharpened. This process is called pointing. The wire is fixed in a special mechanism that resembles strong metal vice jaws. One end of it is inserted into a device similar to a small press or crusher, where the steel casing is gradually squeezed and stretched into a cone shape. This way, the wire is essentially machined into a pointed tip. Imagine a pencil sharpened at one end, only it's not graphite but cold, shiny metal. This sharpened end then easily fits into the first opening of the drawing machine, a small metal die. To the touch, such a sharpened part becomes thin, like a shoelace, but remains elastic and strong. This is where the drawing process begins, which will turn the rough wire rod into a thin steel wire for the cable. Picture a shining metal strand, about the thickness of a pencil, being gradually pulled through a series of metal rings. Each of these rings is a drawing die, looking like a coin with a hole in the middle, but made of super hard material, like tungsten carbide. The holes in each die are slightly smaller than the previous ones. The whole system is arranged in a line, like beads on a thread. The wire passes through the first ring, and it compresses it, stretches it, reducing its diameter. Next, the following ring, even smaller, and the same thing happens again. The entire wire is pulled by a powerful drawing machine, resembling giant toothed rollers or high traction rollers. It constantly pulls the wire forward, maintaining tension, and thus forcing it to pass through the dies. To the touch, after several passes, the wire becomes thinner and longer, like a silvery strand of hair. The surface is smooth, cool, with a clear metallic sheen. Importantly, this entire process happens without heating. The metal remains cold. That's why it's called cold drawing. The steel gets stronger in the process. Its structure becomes denser and more durable, like a muscle that's been trained. And so, ring after ring, an ordinary wire rod transforms into a high-precision wire for a future steel cable. The steel thread that has just passed through a series of drawing dies has become thinner and stronger, but at the same time stressed, like a stretched string with fatigue hidden inside. The metal has accumulated internal stresses, microscopic defects that reduce its ability to bend or stretch further without cracking. Yes, this wire has become brittle. To release this stress, the wire passes through a special thermal furnace. It's not visible from the outside, It's a long metal tunnel structure, inside which the temperature reaches over 1,000 degrees Fahrenheit. In such heat, resembling the middle of a bonfire, the wire slowly moves through the furnace, either lying on moving rollers or suspended. It gradually heats up to the required temperature and then slowly cools down. The whole process takes anywhere from a few minutes to an hour, depending on the thickness and grade of the steel. To the touch, the wire after this stage is just as smooth and shiny, but it no longer breaks. Inside the metal, its crystalline structure has rearranged itself. The stresses are relieved, plasticity is restored. Now it's ready for the next series of drawings, and it will become even thinner, stronger, and more durable. It's like giving your muscles time to recover before the next workout. In the final stage, the wire undergoes a final quality control, and this is definitely not a simple visual check. A long, almost continuous strand of shiny metal moves at a speed of tens of feet per second through the inspection unit. There, it's met by special sensors. This could be laser equipment that non-contact measures the wire's diameter with an accuracy of thousandths of an inch. Nearby devices that determine strength. A portion of the batch is selected for mechanical testing. The wire is clamped in hydraulic jaws and pulled until it breaks. This determines its tensile strength and breaking load. If the wire holds up, it's ready for work at heights of hundreds of feet, supporting the weight of a car bridge. The surface is checked separately for microcracks, burrs, corrosion. High-resolution cameras or even eddy current testing are used here, which can see beneath the top layer of metal. And only the wire that has passed all these tests gets the green light. It will become part of a steel cable capable of withstanding years of loads and harsh weather. This is the final touch that guarantees what arrives at the construction site is reliable, like steel itself. After inspection, the quality wire is neatly wound onto large spools. The wire passes through guide rollers and tensioning mechanisms that ensure the coils lie tightly, but not too tightly. All this happens on high-speed winding machines. Spools come in different sizes. For thin wire, they might weigh hundreds of pounds. For thicker wire, a ton or more. Then these spools head to the next stage, the actual twisting into cables. But even before this, they are sometimes coated with an anti-corrosive compound or lubricant so the wire isn't damaged during storage and transport. Spools of wire are usually moved using forklifts, cranes, or special carts because the weight of even one spool can reach several hundred pounds or more. Manual labor is out of the question here. Otherwise, the risk of injury would be too high.
Every second, 441 nuclear reactors worldwide generate electricity for 1 billion people. But here's what keeps engineers awake at night. Each reactor core operates at temperatures reaching 3,600 degrees Fahrenheit, hot enough to melt concrete, vaporize water instantly, and turn steel into liquid. The only barrier between civilization and nuclear catastrophe is a single steel vessel forged from a 600-ton ingot without a single weld. Picture the weight of 4 blue whales compressed into one seamless cylinder, standing guard over controlled atomic fire. How does humanity forge the largest single-piece objects ever created? How do engineers ensure steel survives conditions that would liquefy most metals? Stick around till the end. You'll discover why only one company on Earth can manufacture these reactor vessels, the jaw-dropping reason welds are forbidden, and the shocking truth about what happens when forging goes wrong at the atomic scale. The story begins at Japan Steel Works in Muran, Japan, the only facility worldwide capable of forging complete reactor pressure vessels from single steel ingots. This monopoly isn't marketing, it's physics. Their forging press, standing 12 stories tall and weighing 14,000 tons, generates forces equivalent to stacking 70 statues of liberty on a dinner plate. That's the mechanical advantage required to shape 600 tons of glowing steel.
The facility consumes enough electricity to power 25,000 homes during forging operations. Backup generators the size of locomotive engines ensure power never interrupts mid-forge. A single unexpected cooling would create internal stresses shattering the vessel like glass. The plant operates 3 shifts daily, yet completes only 4 reactor vessels annually. Each vessel requires 8 months from raw steel to finished product. That's longer than human pregnancy, applied to metalworking requiring tolerances measured in thousands of inches across objects 30 feet tall. Next comes steel creation, where metallurgists blend iron with precise amounts of manganese, nickel, chromium, molybdenum, elements chosen for neutron resistance and high temperature strength. The recipe, classified by nuclear regulatory agencies, creates alloy capable of withstanding 50 years of continuous neutron bombardment without becoming brittle. Standard steel exposed to reactor conditions becomes fragile within months. Reactor-grade steel must maintain ductility for half a century. Electric arc furnaces, consuming megawatts of power, melt 300 tons of scrap and alloys at 3,000 degrees Fahrenheit. Molten steel flows into massive ladles lined with refractory bricks capable of containing liquid metal without dissolving. Workers add deoxidizers and desulfurizers, removing impurities at parts per million levels. Even microscopic inclusions, trapped oxides, sulfides, or air bubbles become crack initiation sites under reactor pressures exceeding 2,200 pounds per square inch. That's pressure crushing car engines like soda cans. Giant molds assembled from water-cooled copper plates standing 20 feet tall receive the molten pour. Liquid steel enters from bottom up through ceramic pipes, filling the mold cavity in controlled flow, taking 40 minutes. Technicians monitor fill rates continuously. Turbulence during pouring traps gas bubbles, creating voids. After filling, the ingot, now a glowing cylinder weighing 600 tons, solidifies over 72 hours under computer-controlled cooling. This cooling phase determines everything. Cool too fast, thermal stresses create internal cracks invisible to naked eyes but catastrophic under reactor operation. Cool too slow, large crystals form, weakening the structure. Thermocouples embedded throughout the mold measure temperature at 300 points simultaneously. The ingot shrinks 5 inches in diameter while cooling, enough movement to crack the mold if thermal expansion isn't calculated precisely. Workers strip the mold after 3 days, revealing a steel cylinder glowing dull red at 800 degrees. Now comes forging, the ancient art of shaping hot metal, scaled to industrial extremes. The 600-ton ingot, reheated to 2,300 degrees Fahrenheit in furnaces large as houses, glows brilliant orange. At these temperatures, steel becomes plastic, not liquid, but deformable under immense pressure. Picture clay that weighs as much as a jumbo jet. Overhead cranes operating at weight limits requiring structural reinforcement throughout the building lift the glowing ingot onto the press bed. The press ram, a solid steel cylinder 6 feet in diameter, descends with force exceeding 14,000 tons. That's pressure equivalent to balancing 30 fully loaded Boeing 747s on a car hood. Under this incomprehensible force, 600 tons of steel deforms, spreading like bread dough, forming into a thick-walled cylinder. Each press cycle compresses the ingot 3 inches, then retracts. The process repeats hundreds of times over weeks. The forging process requires balletic precision at colossal scale. After each press cycle, massive manipulators rotate the workpiece 7 degrees. Computer systems track rotation angle to within 0.1 degrees. Because uneven forging creates thickness variations leading to stress concentration, the ingot must be reshaped uniformly, ensuring wall thickness varies less than 1% across the entire vessel. This step is critical because reactor vessel integrity depends on grain structure. Each press cycle compresses and elongates metal crystals, aligning them perpendicular to stress directions. This crystallographic texture increases strength 30% over cast steel. Between press cycles, the workpiece returns to furnaces for reheating. Temperature drops to 1,800 degrees during forging, making steel too stiff to deform further. The ingot cycles between press and furnace 60 times, spending cumulative hours at extreme temperatures requiring constant atmospheric monitoring to prevent oxidation. After rough forging establishes basic geometry, precision machining begins. The forged cylinder, now weighing 450 tons after material redistribution, moves to vertical lathes with cutting surfaces 20 feet in diameter. Carbide tools, costing thousands of dollars and lasting mere hours, remove steel and continuous spiral cuts. Metal shavings, glowing red from friction heat, pile like metallic spaghetti. Picture this. Machinists target wall thickness of 8.7 inches with tolerance of plus or minus 0.05 inches. That's maintaining consistency thinner than a penny across surfaces 40 feet in circumference. Ultrasonic sensors scan continuously, creating three-dimensional maps of wall thickness. Any thin spot becomes pressure concentration point, and at 2,200 psi operating pressure, stress concentrations cause catastrophic rupture. Modern reactors operate at pressures where even microscopic flaws propagate into fractures within microseconds once initiated. Quality control transcends normal manufacturing standards, entering realm of nuclear safety protocol. Ultrasonic inspection systems, using sound waves at frequencies beyond human hearing, detect internal flaws smaller than grains of rice. Technicians scan every cubic inch of the 450-ton vessel, searching for voids, inclusions, or crystal boundary irregularities. This inspection process alone takes 6 weeks of round-the-clock work. Next comes stress relief heat treatment at 1,100 degrees for 48 hours. This annealing process allows internal stresses from forging to dissipate through autolytic diffusion. Without stress relief, residual tensions from manufacturing cause cracks years later during operation. After heat treatment, hydrostatic pressure testing subjects the vessel to 3,300 psi, 50% beyond operating pressure. Workers flood the interior with water, then pump pressure until the vessel expands measurably. Any weakness reveals itself through leakage or deformation. Passing this test certifies the vessel can contain reactor core meltdown scenarios. This wasn't always possible. Back in 1955, early reactor vessels used welded construction, multiple curved plates joined by fusion welding. The Windscale reactor fire in Britain that year released radioactive iodine when welded seams failed under thermal stress. Investigation revealed welds created heat-affected zones where crystal structure changed, becoming brittle under neutron bombardment. The breakthrough came when Robert Withrich at Combustion Engineering proposed seamless forging in 1963. However, no forge press existed powerful enough. Japan Steel Works developed their 14,000-ton press in 1967 specifically for reactor vessels, recognizing the strategic importance. By 1975, all new reactor designs mandated seamless forgings. Today, the safety record speaks volumes. 0 pressure vessel failures in commercial reactors using forged construction. The few accidents that occurred, 3 Mile Island, Chernobyl, and Fukushima, involved cooling system failures, not vessel integrity. Those forged steel shells contain disaster, preventing far worse outcomes. Carbon emissions avoid 48 billion tons annually through nuclear power generation versus coal, equivalent to removing every car, truck, and plane from operation for 3 years. Nuclear energy costs drop 62% per kilowatt-hour versus solar with battery storage. A single reactor vessel forged today will generate electricity for 80 years, powering 3 million homes throughout its lifetime. So here's the secret promised. These vessels can't be welded because neutron radiation does something insidious to metal. It transmutes atoms.
High-energy neutrons knock atoms from crystal lattice positions, creating vacancies and defects. Over decades, accumulated damage makes steel brittle. Welds, where crystal structures merge imperfectly, accumulate damage faster. The heat-affected zone becomes embrittlement accelerator. Seamless forging eliminates this Achilles heel entirely. Every atom in the vessel exists within continuous crystal structures aligned through forging. There are no boundaries to fail, no weak points to fracture. From 600-ton ingots to civilization's guardians, cycle completes. We've engineered the ultimate containment, steel vessels standing between humanity and atomic fire for generations. These aren't just industrial products, they're monuments to engineering paranoia in the best sense. Over-engineering driven by understanding that failure means catastrophe. That forged steel cylinder represents humanity's ability to harness cosmic forces while building redundant safety margins into physical structures. We've learned to respect the atom's power by building cages worthy of containing it.
Every year, over 40 million tons of asphalt are laid worldwide, and almost a quarter of it is made from old pavement. Imagine, the road you're driving on right now might contain pieces of a highway that trucks were speeding on just yesterday. This isn't just about saving billions of dollars. It's one of the most large-scale examples of the circular economy in the world. Explosions in quarries, giant crushers, hundreds of degrees of heat in the drums of factories, and complex recipes more precise than culinary ones. And all of this to create a black, hot mess that transforms into a smooth road. But the real secret of asphalt is hidden deeper, and you'll find it out if you watch until the end. Almost nothing goes to waste. This crushed old asphalt is then added to the new mixture at the plant. On average, the new asphalt laid on roads contains about 22% recycled material. This has a colossal economic and environmental effect. First, it significantly reduces the need to mine new stone and produce new bitumen, which saves natural resources and energy. Second, it makes the final product cheaper, which allows for saving billions of dollars from road maintenance budgets. Thus, every car trip is a journey on a complex engineering product that not only withstands huge loads, but is also a vivid example of an industrial ecosystem where the old is constantly reborn into the new, closing the loop and making the country's infrastructure a little more sustainable. The story of asphalt begins not on the road, but in two completely different places. The first place is a quarry. It's a huge wound on the body of the earth, where stone is mined. It all starts with a loud explosion that shakes the ground for miles around. Huge boulders break off from the rock face. Then, giant dump trucks, with wheels taller than a person, come into play and haul these stone boulders to the primary crusher. This is a metal monster that, with its steel jaws and incredible force, crushes huge boulders into smaller pieces. But this is just the beginning. Then this stone goes through a whole series of crushes and screens giant vibrating sieves. The purpose of this process is not just to crush the stone, but to carefully sort it by size. The result is entire mountains of clean, sorted stone, which is called aggregate. There's everything here, from large stones the size of a fist to fine crumb, and even dust similar to sand. Each fraction is stored in a separate pile. It's similar to how in your kitchen you have flour, sugar, salt, each ingredient separate, waiting for its time. This is the skeleton of the future asphalt, which makes up 95% of its mass. The second place where asphalt is born is an oil refinery. When gasoline, diesel, jet fuel, and other light products are made from crude oil, a thick black viscous substance remains at the very bottom of the distillation column. This is bitumen. In its normal state, at room temperature, it's as hard as a rock. You can break it with a hammer. But if you heat it, it becomes liquid, like a thick syrup. It is this property of being solid when cold and liquid when hot that makes it the perfect glue for our stone skeleton. Bitumen is the soul of asphalt. It's black heart that binds everything together. And now, let's move to the asphalt concrete plant. This is the place where all the ingredients meet. From a distance, it looks like a complex, tangled metal construction set. Tall tower silos, endless conveyor belts, pipes, tanks, and a central tower from which smoke rises. It's a real factory that works as one cohesive organism. Different fractions of aggregate from separate bins are fed onto a conveyor belt. But not just like that. The whole process is controlled by a computer. An operator in a cabin enters the precise asphalt recipe. Depending on where the asphalt will be used, for a busy highway or a quiet side street, the recipe will be different. The computer knows what percentage of large stone, how much medium, how much small, and how much dust is needed for the perfect mix. It's like baking a complex cake where every gram matters. This mixture of stones begins its journey up a long inclined conveyor and enters the heart of the plant, the drying drum. This is a huge long tube that slowly rotates, installed at a slight incline. From one of its ends, a powerful burner blasts a roaring pillar of fire inside, like in a jet engine. The temperature inside reaches 300 degrees Fahrenheit. The stone, slowly tumbling inside this drum, heats up and, most importantly, is completely dried. Moisture is the main enemy of good asphalt. Even a drop of water can prevent the bitumen from adhering reliably to the surface of the stone. Therefore, the stone must be absolutely dry. After the drying drum, the hot moisture-free stone is lifted by an elevator, similar to a lift for bulk materials, to the very top of the central tower. There it passes through a system of screens for a final control sorting and enters bins for hot materials. In parallel with this, in special insulated tanks, our black glue bitumen is heated. It is also brought to a high temperature to become fluid and liquid. And now comes the climax. The computer gives another command. A weigh hopper with incredible accuracy measures out the required amount of hot stone of each fraction from different bins. Then, a precisely measured amount of hot liquid bitumen is injected into this red-hot stone mixture. This entire mass stone and bitumen enters a mixing chamber, called a pug mill. It's like a giant kitchen mixer, only instead of whisks, it has two powerful shafts with metal paddles. These paddles mix the red-hot mass with enormous force, and in less than a minute, every little stone, every grain of sand is covered with a thin, shiny film of black bitumen. The finished asphalt emerges from the chamber, a uniform, steaming black mass with a characteristic oily smell. Now this hot, freshly prepared product needs to be stored until shipment. It is lifted and poured into special insulated storage silos. They are like giant thermoses that can keep the asphalt hot for many hours, and sometimes even days. Dump trucks drive up under these silos. With a loud clang, a gate opens, and several tons of hot asphalt pour into the truck's bed with a roar and a cloud of steam. The bed is necessarily covered with a tarp to preserve the precious heat during transport to the paving site. At the construction site, the final act of this play begins. The dump truck slowly unloads the hot mixture into the hopper of a special machine and asphalt paver. This machine, slowly moving forward, evenly distributes the asphalt over the road surface, forming a perfectly level layer of a given thickness. At the back of the paver is a heavy, heated plate called a screed. It does the initial compaction and gives the surface its initial smoothness, but the asphalt is still soft and loose. To make it strong, it needs to be compacted. Immediately behind the paver follows a whole team of heavy road rollers. First come the large steel drum rollers, which with their enormous pressure squeeze the air out of the asphalt mixture and force the stones to fit more tightly together. Then, pneumatic tire rollers may be used, which knead the surface, making it even denser. And in the final stage, smooth steel drum rollers pass over it again to give the road its final smoothness. As the asphalt cools, the bitumen turns from a liquid state back into a solid. It permanently glues all the little stones together, turning the loose mixture into a strong, waterproof monolith. After a few hours, the road, which was recently hot and soft, becomes hard and ready for traffic. And that's the whole point. From the explosion in the quarry to the heavy roller on the road. Every stage of this process is aimed at creating a durable, reliable surface that will withstand thousands of cars every day. Every year, the world melts over 1 billion tons of pig iron. But where does all that fiery metal come from? Imagine a giant furnace as tall as a 35-story skyscraper that never sleeps. Its guts glow like the Earth's core, and the temperature hits 3,600 degrees Fahrenheit. That's 2,000 Celsius. This is a blast furnace. They don't just melt metal here. They give birth to the heart of industry. But there's a secret that only the guys standing at the tap hole know. If you stick around to the end, you'll find out what's really happening in the center of this burning fortress, and why it changes everything. Imagine a colossal tower, taller than a 35-story skyscraper. The ground beneath your feet vibrates slightly from its relentless work, and the air is filled with a hum, like the breathing of a giant beast. At night, its top glows, pushing back the darkness. This is a blast furnace, a massive vertical smelter, where 24 hours a day, 7 days a week, the magic of turning ore into metal happens non-stop. Why blast furnace? The name comes from the process itself, and it's no accident. The whole secret to a blast furnace is the constant blast of incredibly hot air that fuels the fire and kicks off all the necessary reactions. If you were to slice a blast furnace open, you'd see it looks like a stretched out bottle. Every part of it has a name and a purpose. The walls of the furnace are lined with special refractory bricks, capable of withstanding temperatures that would melt solid rock. This is a true fortress, built to tame fire itself. So what do they feed into this fiery throat? The process is like cooking from a very strict recipe. The mix of ingredients loaded into the furnace is called the charge. Here are its main components: iron ore, fuel, coke, and fluxes. These three ingredients are loaded into the furnace in precisely measured layers. A layer of coke, then a layer of ore with fluxes, then coke again, and so on. Every few minutes, a new batch weighing tens of tons is sent into the furnace. The iron ore is the foundation of it all. They usually don't just use raw ore dug from the ground, but specially prepared sinter or pellets. These are baked clumps of fine ore, or rolled balls of ore concentrate. The main goal is to have as much iron oxide in the raw material as possible, from which the oxygen will later be ripped out. Coke is coal that's been cooked in special ovens without access to air. After this treatment, it becomes strong, porous, and burns with an immense amount of heat. But that's not its only role. The carbon that makes up coke is the real magician that turns ore into metal. The flux is most often ordinary limestone. Why is it needed? The ore and coke always have useless impurities, so-called gangue. The limestone helps to bind these impurities, forming an easily meltable slag. So, the charge is loaded. What's next? This is where it gets interesting. Two streams move towards each other. From the top, the layers of the charge slowly descend, and from the bottom, a hurricane of superheated gases rushes up to meet them. It all starts at the bottom, in the hearth. Through special pipes called tuyères, air heated to a scorching 2,200 degrees Fahrenheit, 1 to 200 Celsius, is blasted into the furnace under huge pressure. That's hotter than volcanic lava. Meeting the red-hot coke, the oxygen in the air instantly ignites. The temperature in this zone skyrockets to 3,600 degrees Fahrenheit, 2,000 Celsius. This creates carbon dioxide. But as it rises higher and passes through new layers of coke, it turns into another gas, carbon monoxide. And this gas is the real oxygen thief. As this searing hot stream of gas rises up the furnace shaft, it envelops the chunks of ore and begins to greedily rip the oxygen from them, leaving behind reduced, spongy iron. The reduced iron continues its journey downward into hotter and hotter zones. It passes through the glowing layers of coke and, like a sponge, begins to soak up its carbon. And here's where something amazing happens. Pure iron melts at a very high temperature of 2,800 Celsius, 1,530 Celsius. But soaking up carbon dramatically lowers that melting point. That's why a blast furnace doesn't produce pure iron, but an alloy of iron and carbon, pig iron, which becomes liquid at just 2,200 Celsius, 1,200 Celsius. Roughly every 40 to 60 minutes, enough liquid products have collected in the bottom of the furnace. It's time for the climax, a truly mesmerizing sight. A furnace worker, the keeper, uses a special drill to punch open a hole in the furnace wall, the tap hole. First, they tap the slag. It's lighter than the iron, so it floats on top. It's a molten, lava-like mass that flows into special ladles. And then they open the iron tap hole, and a dazzling, sparking stream of molten metal erupts with a roar. This is the River of Fire. The temperature of this stream is around 2,700 degrees Fahrenheit, 1,500 Celsius. It flows down special troughs, bathing everything around in a blinding light, and fills giant ladles that look like railway tankers. Each of these ladles holds hundreds of tons of liquid metal. From here, the pig iron will be sent to its next stage, either poured into molds or, more often, sent for further processing into steel. A blast furnace is an amazing operation that produces more than just pig iron. The byproducts are just as important. The blast furnace slag, which we've already mentioned, becomes a valuable raw material for making cement, building blocks, and road aggregate after it's cooled and crushed. The blast furnace gas that comes out of the furnace isn't just released into the atmosphere. It's cleaned of dust and used as fuel to heat the very same air that's blasted back into the furnace. It's a closed-loop system that makes the process more economical. Without a doubt, metallurgy is a serious challenge for the environment. However, modern technologies are constantly evolving. When blast furnaces are modernized, powerful filters and cleaning systems are installed to capture dust and harmful gases. Scientists and engineers around the world are working on creating green technologies, like using hydrogen instead of coke, to make metal production cleaner. But for now, the blast furnace remains the king of metallurgy. And every time you see a bridge, a skyscraper, or a train, remember these fiery giants and the people who tame rivers of fire to give the world a strong and reliable foundation. For 75 years, from the late 19th century to the 1970s, the USA was the undisputed world leader in the production of pig iron, steel, and rolled products. During this period, the American iron and steel industry wasn't just a sector of the economy, it was the key, or barometer, of the American economy. In the 1920s, for example, the country produced about half of the world's pig iron. Imagine that. Every other ton of this strategic metal in the world was born right here in American furnaces. Every year, the world produces over 130 million tons of glass. But few people know that behind every clear window, bottle, or skyscraper facade lies a true symphony of fire, air, and light. Imagine a river of molten sand flowing over a mirror of tin, giving birth to perfectly flat sheets of glass so smooth they can reflect the clouds. But there's another kind of glass, one that's alive, with a soul, created by the breath of a craftsman and the fire of a furnace. Stick around to the end, and you'll see how ordinary sand travels through a 3,000-degree journey to become the transparent marvel our world is made of. While the vast majority of architectural glass today is born from a perfectly flat, fiery river flowing over molten tin in the float process, the true soul of the material is revealed in the methods that give it character and uniqueness. This journey from a simple, transparent sheet to a work of decorative art is a fascinating one. To create glass with individuality that carries the mark of a human touch, craftsmen still turn to techniques that have existed for centuries. A glassblower dips his long, hollow pipe into a furnace where a mass of sand and other minerals boils at 2,000 degrees Fahrenheit. He gathers a honey-like ball of glowing glass on the end of the pipe and, skillfully rotating it, begins to blow air into it. The initial bubble, born from his breath, gradually transforms into an elongated, shining hollow cylinder. Thanks to the force of gravity and skillful swinging, this cylinder can reach several feet in length. After the ends of the cylinder are cut off, it's sliced lengthwise and placed back in the furnace. There, under the heat, it slowly unrolls like a scroll, and the craftsmen smooth it into a flat sheet. Glass born this way is never perfectly flat. It's alive, retaining subtle waves, tiny air bubbles, and fine lines that tell the story of its fiery birth. This glass has a watery, organic quality that can't be replicated by a machine. But the creation of unique glass doesn't stop at forming the sheet itself. Other methods transform ordinary sheets into complex decorative elements. Fusing allows artists to literally paint with glass. Different colored pieces of glass are arranged on a base sheet and sent into a kiln, where at 1500 degrees Fahrenheit, they melt together into a single piece, creating bright, painting-like compositions. Closely related is the process of slumping, or bending, where a flat sheet of glass is heated until it becomes soft and sags under its own weight, taking the shape of a ceramic or metal mold placed beneath it. This allows for the creation of curved panels and three-dimensional glass sculptures. Modern technologies add even more possibilities. Lamination allows for baking colored films, fabrics, or even thin sheets of metal between two layers of glass, creating endless variations of color and texture. Sandblasting and chemical etching remove the top layer of glass, making it matte and creating intricate patterns on its surface, from simple geometric shapes to photorealistic images. In this way, by combining ancient crafts with cutting-edge technology, modern production transforms simple glass into an expressive architectural material capable of shaping light, color, and space. In today's world, where tons of used glass containers are collected daily, the journey from the recycling bin to a new bottle isn't just remelting. It's a high-tech odyssey driven by computers and light. Imagine a mountain of crushed glass, dozens of feet high, where clear, green, and brown shards are mixed with labels, caps, and ceramic contaminants. Turning this chaos into pure raw material is a job for a whole complex of smart machines. It all starts with mechanical crushing, where steel hammers turn bottles and jars into fragments a few inches in size. This stream of glass, like a moving river, embarks on a journey through a labyrinth of sorting systems. First, powerful magnetic separators pull out any steel contaminants, and then eddy current systems literally shoot aluminum caps and foil into separate containers. Powerful blasts of air blow away light paper labels and plastic residue. But the hardest task is yet to come. Removing impurities that are almost identical to glass in weight and size, like pieces of ceramic, stone, or porcelain. These enemies of glass don't melt at standard temperatures and turn into defects in new products, so their removal is critically important. This is where optical sorting comes into play. The glass fragments are accelerated on a conveyor belt to high speed and fly through a scanning zone. For a split second, each fragment is illuminated by a bright light, and high-speed cameras take hundreds of pictures. A computer system, with lightning speed, analyzes the images, identifying foreign bodies by their transparency, structure, and shape. As soon as the system spots an opaque piece of ceramic, it instantly calculates its trajectory and commands a battery of air jets. A precise, sniper-like puff of compressed air knocks the unwanted element out of the mainstream, sending it to waste. This process is repeated thousands of times a minute. At the same time, an equally important sorting by color takes place. The same optical systems analyze the spectrum of light passing through each fragment. The machine distinguishes between crystal clear, rich green, and deep brown glass. Depending on the set program, the system can, for example, select only clear glass, knocking out all colored fragments with air jets, or separate the stream into 3 distinct color fractions. The result is a perfectly clean, color-sorted raw material, cullet, ready for a new life without any loss of quality, which is the pinnacle of the modern circular economy. This raw material can then be used to make flat glass. The birth of modern flat glass is a symphony of fire and precision, a spectacular process that turns ordinary raw materials into perfectly transparent sheets. It all begins in a massive melting furnace, the fiery heart of the plant that runs continuously for years. Into this furnace, which resembles a lake of molten fire, a carefully measured mix, or batch, is loaded, consisting of pure quartz sand, soda ash to lower the melting temperature, and limestone for stability. A significant amount of cullet, or crushed recycled glass, is added to this to help speed up the melting process. Inside the furnace, at hellish temperatures approaching 3,000 degrees Fahrenheit, these solid components slowly transform into a uniform, viscous liquid. The melting process is strictly controlled to ensure all particles are completely dissolved and gas bubbles are removed, creating a flawlessly pure melt. From the furnace, this stream of glowing orange molten glass, resembling a river of lava, flows smoothly into a bath of molten tin. This is the culmination of the process known as the float process. The tin bath, stretching for hundreds of feet, has a perfectly smooth, mirror-like surface. Since glass is lighter than tin and doesn't mix with it, it spreads out over the surface, forming a perfectly flat ribbon of uniform thickness. Gravity levels it from the bottom, and surface tension smooths it from the top, creating impeccable optical quality. The speed at which this ribbon is pulled from the bath determines its final thickness with pinpoint accuracy. After forming a perfectly flat surface, the glass ribbon, still very hot but now solid enough to hold its shape, enters the calmest but most critical stage, annealing. It enters a long tunnel known as an annealing layer. If glass is cooled too quickly, its surface will contract faster than its interior, leading to massive internal stresses that will make it brittle and prone to shattering. In the layer, however, the glass temperature is slowly and controllably reduced over several hundred feet, from over 1,000 degrees down to room temperature. This process allows the entire sheet, both surface and core, to cool evenly, relieving all internal stresses. From the other end of the layer emerges a single, flawless, continuous ribbon of perfectly transparent, stress-free glass, ready for automatic cutting into huge sheets that will become the windows, facades, and doors of our world. Every year, dozens of nuclear submarines are launched into the world's waters, giants capable of diving to depths of over 2,000 feet and remaining invisible for months. These are truly underwater cities, with a reactor at their heart, hundreds of tons of steel and titanium alloy, and incredible silencing systems that absorb sound. But how is such a machine born from cold metal? What secrets does its construction process hide, where even a microscopic crack can cost lives? Watch carefully. In the finale, you will learn what is usually hidden behind the 7 locks of military archives. A nuclear submarine is a complex engineering creation, the development of which begins long before the first sheet of metal hits the machine tools. It all starts with computer-aided design. At this stage, several key parameters are considered: the size and shape of the hull, the power supply system, weaponry, and noise reduction measures. The length can range from approximately 300 to 560 feet, depending on the class, and this directly affects the diving depth. The most advanced submarines can descend to 1,968 to 2,460 feet, and some experimental models, even over 3,000 feet. Based on the initial designs, physical models of the submarine are created, which are tested in special water tunnels. This helps engineers see how the hull shape affects maneuverability, water resistance, and noise level. In parallel, computer modeling allows predicting how the submarine will behave underwater at different speeds and maneuvers. After simulations, when all calculations match up, the blueprints are sent to production. This is where the most interesting part begins: the actual assembly. For the construction of nuclear submarines, special materials are used that can withstand high pressure at great depths and provide protection against corrosion. Usually, these are high-quality steel or titanium alloys. Steel is cheaper and easier to produce, and it withstands pressure and impacts well. Titanium has the advantage of high strength, lightness, corrosion resistance, and being non-magnetic, which makes it harder to detect the submarine. However, titanium is more difficult to process and weld, as its melting point is higher, about 3,092 degrees Fahrenheit versus approximately 2,552 degrees Fahrenheit for steel. Before construction begins, the metal sheets undergo heat treatment. They are heated, rapidly cooled, and treated with special anti-corrosion compounds. The hull of a modern submarine is usually made of modular sections. This makes construction easier. Metal sheets are cut by giant laser and plasma devices with millimeter precision. Then, each sheet is bent under a press to give it the required shape. Often, some hull elements have a spherical or cylindrical structure. The sections are assembled separately. These are huge rings, or compartments, which are later joined in the final stage. This division into sections allows for working on different parts of the submarine in parallel, speeding up the construction process. When all the parts are ready, one of the most critical stages begins: welding the hull. The welds must be extremely strong. Even a microscopic crack at depth can cause a catastrophe. Therefore, automated electron beam welding is used, which allows for creating the most uniform seams possible. Additionally, each seam is checked with ultrasonic scanners and X-rays. Most nuclear submarines have a double hull. A strong inner hull withstands high pressure at great depth, while an outer hull provides a streamlined shape, improves hydrodynamics, and helps reduce the likelihood of detection. Ballast tanks, which regulate the submarine's buoyancy, are usually located between the hulls. To keep the submarine as stealthy as possible, it is covered with anechoic layers. These are polymer tiles that absorb sound waves, as well as composite materials with micropores that reduce the acoustic signature, and noise-dampening coatings applied to the propellers and power plants. When all the hull sections are ready, their joining begins. Giant cranes move the compartments into special docks, where they are connected using bolted joints and welding. Next, the hull is tested for leaks by filling it with compressed air and checking for any escape. And strength tests are conducted in a hydrostatic tank, where pressure similar to deep sea diving conditions is simulated. After assembling and checking the hull strength, the key element is installed: the nuclear reactor. This is the heart of the submarine, allowing it to stay underwater for months or even years. A nuclear reactor is not just an engine, but a whole complex of energy and auxiliary systems that occupies a significant part of the submarine. Modern nuclear submarines use reactors that operate on the principle of heating water to produce steam. The fuel, usually enriched uranium-235 or uranium-238, is located in the reactor core. During the nuclear reaction, heat is released, which heats water in a closed loop. The hot steam is directed to turbines, which generate electricity and drive the propeller. The reactor is delivered in special protective containers and installed by a crane through an upper hatch in the hull. Inside, a compartment is provided for it, surrounded by materials that minimize radiation. Emergency cooling systems and sealed barriers are also located there. The reactor is mounted on a shock-absorbing platform that reduces vibrations and impacts during the submarine's movement. Then, heat exchangers and steam generators are installed, which are responsible for the circulation of the coolant, and turbines and electric generators are mounted. The functioning of all the submarine systems depends on their operation. Finally, the reactor compartment is sealed with multi-layered lead and composite panels to protect the crew from radiation. To check the readiness of the structure, the first startup of the reactor is carried out in test mode. The power is gradually increased, the radiation level in the compartments is monitored, and the cooling systems are tested at maximum loads. When the reactor is already installed and the submarine has a fully formed hull, it is still not ready for service. Inside, there are still only empty corridors and compartments, So the next stage is the installation of control systems, life support, weaponry, and crew quarters. Sonar systems are mounted in the bow and along the hull. They track enemy ships and scan the seabed. A computer system and automated combat control stations are also installed, ensuring maneuvering accuracy. Of course, weapon systems are also mounted. Torpedo tubes are located in the front part of the submarine, and they usually have automated reloading mechanisms for quick preparation of new shots. On strategic submarines, missile silos with hydraulic locks and pressure control systems are installed in the central part, which allow for launching missiles even at great depths. Since the crew can spend months underwater, the submarine must be as autonomous as possible. For this, nuclear submarines are equipped with oxygen generation systems, carbon dioxide removal, heating, ventilation, and a sufficient supply of water. If you've seen capsule hotels, then inside a submarine, there is something similar: sleeping capsules for the crew to rest. In addition, there are dining areas with significant food supplies and a command center with control panels, maps, and communication equipment. After arranging the living area, the submarine is almost ready to go to sea, but a series of complex tests are still ahead, which must prove that it can withstand colossal pressure, remain inconspicuous, and is maneuverable in extreme conditions and capable of performing combat missions. Such checks last from 6 months to 2 years and include both factory testing and combat training for the crew. First, the submarine is checked again for leaks. All electrical and navigation systems are tested, and the reactor is started up again. After this, the submarine goes to the open sea for the first time, where stabilizers, hydraulic cylinders, and steering mechanisms are checked. Sharp turns, dives, emergency maneuvers are practiced, and the maximum speed is determined, usually 25 to 35 knots, which is about 29 to 40 miles per hour. Then the submarine descends to periscope depth, about 65 feet, to assess stability. At greater depths, the operation of the ballast tanks under load is checked, and the submarine is gradually brought to its maximum permissible depth, which is about 1,968 feet, depending on the class. The reactor is necessarily tested under maximum load. When the submarine confirms its seaworthiness and reliability, they move on to testing the combat systems. The first shots are usually performed with training torpedoes, without a warhead. On strategic submarines, a launch of one ballistic missile may be conducted with a launch-dive-disarm in the air trajectory. On tactical submarines, the launch of cruise missiles like the Tomahawk or its analogs is checked. In addition, the submarine enters a special zone with hydroacoustic sensors, where specialists measure the noise level at different speeds and check the effectiveness of the noise-dampening coating. Finally, the submarine undergoes a simulated combat mission, during which the crew demonstrates its readiness for real service. Every year, thousands of combat vehicles are produced worldwide, capable of changing the course of history. In terms of weight, that's hundreds of thousands of tons of steel, aluminum, and composites, transformed into something that has to withstand fire, explosions, and impacts. Imagine armor thickness of over 5.5 inches, an engine with 1,500 horsepower, and a cannon that hits a target from 2.5 miles away. But the most important part isn't the numbers. Hidden inside every tank are technologies that aren't written about in open sources. Watch until the end, and you'll find out what's usually kept behind the closed gates of defense plants. Every painting begins with a sketch, and a tank with a design project. The design must take into account the integration of modern materials, armor, electronic systems, and weaponry. The key materials are high-strength steel, composite materials, aluminum, as well as special armor. First, the hull is planned and manufactured. It's made from high-strength armored steel, which can protect the entire crew from enemy fire. The steel must undergo heat treatment to increase its strength. In some places, the hull is reinforced with composite armor made of special multi-layered materials. Their composition is classified, but it can be ceramics, metal alloys, and plastics. The steel plates are cut using a laser to ensure high dimensional accuracy. the armor thickness varies depending on the part of the hull. For example, in the front section, it can reach 14 centimeters. The panels are joined by machines, specialized welding robots, which immediately and thoroughly check the seams for strength, as they must withstand great loads and explosive impacts. Then, special modules, protective screens, and mountings for fuel tanks are attached, and it is treated with an anti-corrosion coating. Some tanks are even equipped with reactive armor. The tank's turret is the second most important part, because it handles the fire control functions and contains the main armament. It's made from materials similar to the hull, but with a more complex shape. For the turret, thick armored plates are used, which are bent and stamped by special giant machines to get the precise shape. In some places, the armor thickness can reach 12 centimeters, and with the composite layer, even more. The engine is manufactured separately. The Honeywell AGT 1500 operates on the principle of a gas turbine, almost like the engines of aircraft. It has a power of 1,500 horsepower and can run on various types of fuel. The main materials for the engine are titanium alloys, which are capable of withstanding high temperatures, up to 2,200 degrees Fahrenheit. Also, heat-resistant steel for shafts and combustion chambers, and composite materials for some elements. The rotor blades are cut from titanium plates using laser and water jet systems. The stator parts are also manufactured separately and coated with an anti-corrosion coating. The compressor, which forces air into the combustion chamber, is made of lightweight alloys to ensure high performance. The chamber is made of heat-resistant steel, capable of withstanding temperatures over 2,000 degrees Fahrenheit. Its inner walls are coated with a special ceramic layer to prevent overheating. Each element is checked for its ability to withstand extreme rotations of up to 50,000 revolutions per minute. After manufacturing and checking all the parts, the assembly process begins. The main engine body is assembled from several sections that are connected to the compressor, combustion chamber, and turbine. The shaft connects the turbine to the compressor and ensures the transfer of energy. A cooling system is added to the engine, which uses air and oil to reduce heat during operation. A unique filtration system is also installed, which cleans the air of dust and sand, which is especially important for operation in deserts or steppes. The engine is installed on a test stand, where it is checked for maximum power, temperature regime, and fuel consumption. Tests are conducted for long-term operation under high load. The engine is installed on the tank chassis for testing in real conditions. Its operation is tested on various types of fuel, including jet kerosene and diesel. At this stage, all previously manufactured parts are joined into a single structure. First of all, the engine is installed in the hull along with the transmission. After that, the components of the running gear are added, including tracks, shock absorbers, rollers, and suspension, which allow the tank to withstand high loads on rough terrain. I was shocked by how it all looked. It's just so massive and powerful. During the integration process, special attention is paid to the installation of the turret with all its systems. The turret is mounted on a special bearing ring that ensures its smooth rotation of 360 degrees. After this, a 120mm cannon, stabilization, and aiming systems are integrated into the turret. Thermal imagers, laser rangefinders, night vision devices, and other electronic equipment for the crew are also installed. The fire control systems are connected to a central computer that synchronizes data from all sensors. The ammunition is located in a special compartment with blast-proof panels, which ensures the crew's safety in the event of shell detonation. Next, auxiliary systems are installed, such as the air conditioning system, which ensures the crew's comfort in extreme conditions, as well as systems for protection against weapons of mass destruction. Elements of additional armor, including composite and modular blocks, are added to the hull. For each tank, protection options are individually selected depending on the assigned tasks. The next step is the installation of all electronic systems. All cables are placed in special channels for protection against mechanical damage. Each tank has to go through multiple levels of testing. First of all, the tank is checked for the tightness and strength of the hull. In special chambers, the hull is subjected to high pressure to ensure there are no leaks or cracks. To do this, the hull is filled with compressed air or liquid, and the outer surface is covered with a special solution to detect even the smallest defects. This stage is especially important, as the hull must withstand the pressure of a blast wave and provide protection for the crew. Special attention is paid to checking the running gear. The tank is driven over obstacles that simulate real combat conditions: hills, pits, marshy areas, and sandy roads. On test ranges, the tank overcomes slopes of up to 60 degrees, which allows for checking its stability and maneuverability. The tracks are checked for their ability to withstand constant impacts and friction over a long period of time. The suspension is tested for its ability to soften impacts during high-speed movement. The tank's weapon systems also undergo intensive testing. The 120mm smoothbore cannon is checked for accuracy and stability of firing on the move. For this, targets are set up at various distances on the test range, including targets located at a distance of up to 4,000 meters. In addition to the cannon, machine guns and grenade launchers are checked. An important stage is testing the fire control system, which must accurately synchronize data from the laser rangefinder, thermal imager, and onboard computer. The electronics of the system are tested separately. On special test stands, communication, navigation, and surveillance systems are checked. Special attention is paid to night vision systems to ensure a clear image in complete darkness or a smokescreen. The onboard computer is checked for information processing speed and its ability to operate in extreme conditions, such as high temperature, vibration, and humidity. The final stage is armor testing. On special ranges, the tank's hull is fired upon with various types of weapons: anti-tank missiles, shaped charge projectiles, and grenades. This allows for evaluating the effectiveness of the composite armor and additional protective screens. The armor must stop projectiles and minimize the effects of a blast wave. And only after completing all multi-level checks are the finished machines handed over to the military. Every hour, over 100,000 airplanes take off around the world, but only one of them is a true ghost of the sky. It has no tail, leaves no trace on radars, and costs more than gold. The creation of the B-2 Spirit cost the United States $60 billion, and over 40,000 specialists from 600 companies worked on each unit. Its assembly took more than a year, with special hangars, laser-like surgical precision, and materials you can't buy in any store. But what this plane hides is still a secret. And if you watch until the end, you'll find out what it was really created for. The design of the B-2 Spirit strategic bomber began in 1979, when the Cold War was reaching its peak. It was then that the United States Department of Defense initiated the Advanced Technology Bomber program, with the goal of creating a new generation aircraft, capable of penetrating the most advanced Soviet air defense systems while remaining invisible to radars, and delivering nuclear or conventional weapons over intercontinental distances. Leading American aerospace corporations participated in the competition: Northrop, Boeing, Lockheed, and Rockwell. After a lengthy stage of development and testing, in October 1971, the Northrop-Boeing consortium was declared the winner. It was their project that received the designation B-2 and the name Spirit. Unlike previous strategic bombers, the B-2 was built on a unique flying wing design, which provided a minimal radar cross-section and significantly better flight characteristics. In the mid-1980s, the B-2's design had to be significantly changed. The mission profile was adapted for low-altitude flights with terrain following, which allowed for even more effective penetration of Soviet air defenses. This led to a 2-year delay in its first flight and an increase in the program's cost by $1 billion. By 1989, About $23 billion had been spent on the B-2's development, and even specialists from the Massachusetts Institute of Technology were involved in the work, assessing the aircraft's effectiveness under conditions of strict secrecy. The first public showing of the B-2 Spirit took place on November 22, 1988 at Plant 42 in Palmdale, California, which is where it was assembled. The first flight of the B-2 took place on July 17, 1989. Initially, the United States Air Force planned to order 132 aircraft, but after the end of the Cold War and the collapse of the USSR, as well as due to the extremely high cost, the series was reduced first to 75 and then to 21 units, including a prototype, 5 pre-production, and 15 production machines. Almost all B-2s received their own names in honor of American states, emphasizing their uniqueness and symbolic significance for the country. Thus, the B-2 Spirit became not only a technological breakthrough, but also a symbol of American military might at the turn of the 20th and 21st centuries. The production of the B-2 Spirit began not with the manufacturing of individual parts, but with the creation of a completely new industrial ecosystem capable of meeting the unique requirements for technology, materials, and assembly precision.